continuing from the estimation of atoms in the observable universe, it's important to delve deeper into the methodologies and challenges that scientists face in these calculations. The task is not only about counting the atoms in stars, but also includes the atoms in interstellar and intergalactic mediums, planets, and other celestial bodies. Advanced observational techniques. One of the key tools in astrophysics is spectroscopy, which involves analyzing the light spectrum emitted or absorbed by objects in space. Different elements absorb and emit specific wavelengths of light, and by studying these spectral lines, astronomers can determine the chemical composition of distant stars and galaxies. This analysis provides essential data for estimating the number of atoms in various types of celestial bodies. Cosmic microwave background. The cosmic microwave background radiation is a crucial element in understanding the early universe. This radiation is the remnant heat from the Big Bang, now cooled to just a few degrees above absolute zero. By studying the tiny temperature fluctuations in the CMB, cosmologists can determine the density fluctuations that grew into galaxies and large-scale structures in the universe. These fluctuations help estimate the total mass of ordinary matter shortly after the Big Bang, which in turn helps in calculating the number of atoms. Baryon acoustic oscillations. Another method involves the study of baryon acoustic oscillations. These are regular, periodic fluctuations in the density of the visible baryonic matter protons and neutrons of the universe. Baryons serve as a standard ruler for measuring the scale of the universe, because the scale of these fluctuations is well understood from the physics of the early universe. By measuring the scale and distribution of these fluctuations, cosmologists can infer the amount of matter in the universe, and hence the number of atoms. Challenges and uncertainties. Despite the progress in these areas, the task of counting atoms is fraught with challenges. The universe is not only vast, but also filled with regions that are inaccessible to direct observation. For example, much of the matter in the universe is dark matter, detectable only by its gravitational effects and not by electromagnetic radiation. Hence, the estimates of the total number of atoms are based on the observable universe, which might only be a fraction of the entire universe if it is indeed infinite. Additionally, the efficiency of data collection and the limitations of current technology can also skew the accuracy of these estimates. The distances involved are so vast, and the positions of celestial bodies change over time. This means that observations are snapshots of the past, and the universe might have changed significantly since the light from those objects began its journey to us. Future prospects. As technology advances, especially with projects like the James Webb Space Telescope and other next-generation observatories, astronomers expect to improve their measurements of the universe's composition. These improvements will likely refine our understanding of the total number of atoms, revealing more about the universe's earliest moments and its long-term fate. In sum, the endeavor to count the atoms in the universe is an ongoing challenge that blends cutting-edge technology with deep theoretical insights. Each advance brings us closer to understanding not just the scale of the universe, but also the fundamental principles that govern it. The speed of light is not merely a constant, but a critical component that influences the fundamental structure of our universe. Its implications extend beyond the realms of physics into the very way we perceive time and space. The concept of light speed serving as a cosmic speed limit comes from Einstein's theory of relativity, which posits that nothing can move faster than light in a vacuum. This principle has profound implications for understanding causality and the structure of space-time. When discussing the speed of light, one must consider its role in the causality principle in physics. Causality means that an effect cannot occur from a cause that is not in the back-past light cone of that event. Essentially, information or a causal effect cannot travel faster than light, which helps to prevent paradoxes such as the grandfather paradox in time travel scenarios. This underlines why the speed of light is not just a physical limit, but a boundary of causal connectivity in the universe. Further exploring the implications of light's constant speed, it becomes apparent how this affects the measurement of distances in astronomy. Astronomers rely on the speed of light to gauge how far away celestial objects are from us. For instance, when we say a star is 8 light-years away, we mean it takes light 8 years to travel from that star to Earth. This method of using light-years as a distance measurement reflects not only the vastness of space, but also the finite, though incredibly fast speed at which light travels. Moreover, the speed of light is central to the phenomenon of time dilation, a prediction of Einstein's special relativity. As an object moves closer to the speed of light, time as experienced by the object slows down relative to a stationary observer. This effect has been confirmed by experiments involving precise measurements of time elapsed for particles traveling at high speeds and for clocks onboard satellites in orbit. Such observations have indispensable implications for GPS technology, where even nanosecond inaccuracies can lead to errors in positioning. In addition to time dilation, the speed of light also influences the contraction of lengths in the direction of motion, known as length contraction. At speeds approaching that of light, objects are measured to be shorter in the direction they are moving from the perspective of a stationary observer. This effect, though imperceptible at everyday speeds, becomes significant at velocities close to light speed and must be considered when designing high-speed spacecraft or conducting high-energy physics experiments. The invariance of the speed of light has led to the development of technologies that rely on its properties. For example, in methods such as light-based ranging and LiDAR, as well as in the synchronization of time across the internet and communication networks, the speed of light provides a critical standard for timing and distance measurement. In summary, the speed of light serves as a cornerstone in the architecture of modern physics, influencing how we measure space and time, the behavior of objects at high velocities, and the fundamental interactions between energy and mass. Its constancy and limit are not just abstract concepts, but have real-world applications that affect various technologies and our understanding of the universe's structure. The implications of the speed of light extend into the realm of black holes and the event horizon, a critical boundary where the escape velocity equals the speed of light. Black holes are regions of space-time exhibiting gravitational effects so strong that nothing, not even particles and electromagnetic radiation such as light, can escape from inside it. The concept of an event horizon is intrinsically linked to the speed of light. It represents the threshold beyond which the gravitational pull is so intense that light cannot get out. Delving deeper into the nature of black holes, the speed of light plays a crucial role in defining the Schwarzschild radius, which is the radius of a sphere such that, if all the mass of an object were to be compressed within that sphere, the escape velocity from the surface would equal the speed of light. Calculating this radius involves directly using the speed of light, showing how it's intertwined with the fundamental properties of these massive objects. Furthermore, the constancy of the speed of light underpins the theoretical framework of general relativity. Einstein's field equations, which describe how matter and energy interact with the geometrical structure of spacetime, rely on the invariance of the speed of light. These equations suggest that spacetime is curved by matter and energy, and this curvature dictates the motion of objects and the propagation of light. Thus, the speed of light is not just a speed limit, but a fundamental descriptor of the universe's geometry. This constancy also impacts the universe's expansion. Observations of distant galaxies show that they are moving away from us, and the farther a galaxy is, the faster it appears to be receding. This observation, explained by the Hubble law, suggests that the universe is expanding at speeds that can approach the speed of light for the most distant galaxies. Here, the speed of light again becomes a crucial factor in understanding not only the mechanics of this expansion, but also its implications for the observable universe. It limits the portion of the universe we can see and interact with, as beyond a certain point, galaxies recede at a speed greater than the speed of light due to the expansion of spacetime itself, making them unreachable and unobservable. Moreover, the speed of light influences the cosmic microwave background radiation CMB, the remnant heat left over from the Big Bang. The uniformity and the slight anisotropies irregularities in the CMB carry information about the early universe's conditions. The fact that light travels at a constant speed allows cosmologists to calculate how long the light from the CMB has been traveling and thus to estimate the age of the universe. These measurements, again reliant on the speed of light, provide a cornerstone for the Big Bang theory and the subsequent evolution of the cosmos. The role of the speed of light in modern physics and cosmology is indeed profound. It not only defines the boundaries of causality and the observable universe, but also continues to challenge our understanding of the fundamental nature of time, space, and matter. As we probe deeper into the cosmos and back in time towards the moment of the Big Bang, the speed of light remains a key tool in unlocking the mysteries of the universe's origins, structure, and eventual fate. The influence of the speed of light extends into the domain of quantum mechanics, particularly in the context of quantum entanglement and the transmission of information. Quantum entanglement is a phenomenon in which particles become interconnected, so that the state of one particle instantaneously influences the state of another, regardless of the distance separating them. This seemingly instantaneous connection challenges our classical understanding of the speed of light as a limit to how fast information can travel. Despite initial appearances, quantum entanglement does not actually violate the speed of light constraint because no usable information is transmitted between entangled particles faster than light. The changes in states are correlated, but determining the state of one particle instantaneously changes the known state of the other. However, this does not allow for communication faster than light, adhering to the principle of causality upheld by the theory of relativity. The speed of light also plays a pivotal role in the fundamental constants of nature, particularly in the fine structure constant, denoted as alpha. This dimensionless constant characterizes the strength of the electromagnetic interaction between elementary charged particles. It combines the speed of light, the elementary charge, and the Planck constant. The fine structure constant is crucial for calculations in quantum electrodynamics, influencing the probabilities of photon absorption and emission, and the spectral lines of atoms and molecules. In addition to theoretical physics, the speed of light has practical implications in technology, particularly in the realms of telecommunications and computing. Fiber optic cables, which are the backbone of modern internet and telecommunications infrastructure, use pulses of light to transmit data over long distances at speeds close to that of light in a vacuum. The understanding and application of the speed of light in such technologies are crucial for optimizing data transmission rates and reducing latency, which is essential for high-speed real-time communications across the globe. Moreover, the synchronization of systems in GPS technology is heavily reliant on the precise measurement of the speed of light. GPS satellites transmit signals that must be timed extremely accurately to determine a position on Earth to within a few meters. Small errors in timing can lead to significant discrepancies in positioning, and because these signals travel at the speed of light, even nanosecond inaccuracies can be critical. Additionally, the speed of light finds applications in areas such as the synchronization of financial markets, where trading algorithms often operate on the scale of microseconds. The speed at which trades can be executed and information can be transmitted is bounded by the speed of light, influencing how trading systems are designed and where servers are physically located to minimize time delays. In scientific research, the speed of light is crucial for experiments involving the Large Hadron Collider LHC, where particles are accelerated to near light speeds. Understanding the implications of relativity and the speed of light is essential for correctly interpreting the results of particle collisions, which can reveal the nature of fundamental particles and forces. Thus, the speed of light not only shapes our understanding of the universe and the fundamental laws of physics, but also impacts a wide array of practical applications, from quantum computing and telecommunications to satellite navigation and high-energy physics experiments. Its influence permeates through various fields, highlighting its central role in both theoretical explorations and everyday technologies. Speed, in its most basic scientific definition, measures how fast an object is moving and is usually expressed as the distance traveled per unit of time. In the context of the universe, speed helps us understand the motion of planets, stars, galaxies, and particles of light. Among all speed measures, the speed of light in a vacuum, precisely 299,792 kilometers per second, holds a particularly eminent position due to its fundamental role in the laws of physics, as described by Albert Einstein's theories of relativity. This specific speed, 299,792 kilometers per second, is not just a random value. It is the ultimate speed limit of the universe, according to current physical theories. Light speed is the threshold beyond which traditional laws of physics start to break down, and it represents the maximum speed at which all energy, matter, and information in the universe can travel. This limitation is deeply embedded in the fabric of the universe and is reflected in the structure and behavior of everything within it. The significance of the speed of light extends beyond its definition as a speed limit. It is integral to the structure of Einstein's special theory of relativity, which fundamentally changes our understanding of time and space. According to this theory, as an object moves closer to the speed of light, time as experienced by the object slows relative to a stationary observer. This phenomenon, known as time dilation, has been experimentally confirmed by observing the decay rates of particles moving at high speeds and by precise timing of clocks aboard fast-moving spacecraft. Moreover, the constancy of the speed of light leads to the conclusion that the laws of physics are the same for all observers, regardless of their relative motion. This principle of invariance has profound implications, suggesting a universality of physical laws throughout the cosmos. It also underpins the general theory of relativity, which extends the principle to include gravitational effects, describing gravity not as a force, as Newton did, but as a curvature of space-time caused by mass and energy. The speed of light also serves as a critical tool for astronomers and cosmologists. It acts as a cosmic ruler in the method of astronomical distances. The concept of a light year, which is the distance light travels in 1 year, is used to express astronomical distances. This unit allows scientists to convey the vast expanses between stars and galaxies in terms that are more comprehensible than using standard units like kilometers or miles. Thus, the speed of light underlies our understanding of the size and scale of the universe. Furthermore, the fixed speed of light is crucial in technologies that depend on precise measurements of time and distance, such as the Global Positioning System (GPS). GPS satellites must account for the speed of light in their signals to achieve accuracy in positioning. Any deviation or error in these calculations can lead to significant errors on the ground. Thus, understanding and using the constant speed of light is vital for navigation technologies that impact a wide range of sectors, from military to civilian applications. In quantum mechanics, the speed of light plays a role in phenomena such as the entanglement and the uncertainty principle. While quantum entanglement does not transmit information faster than light, it shows how particles can be interconnected in ways that are not entirely understood within the framework of classical physics. This underscores the still mysterious and unexplored aspects of quantum mechanics, where the speed of light remains a boundary for information transfer. The speed of light also influences our understanding of the universe's expansion. Observations indicate that the universe is expanding at an accelerating rate, with distant galaxies moving away from us faster over time. This expansion can approach the speed of light for the most distant galaxies, which leads to observable effects such as redshift, where light from these galaxies shifts towards longer wavelengths as it travels towards us. Ultimately, the speed of light, 299,792 kilometers per second, is more than just a speed limit. It is a fundamental constant that informs our understanding of the universe. It shapes the laws of physics, dictates the structure of space and time, influences how we measure our universe, and even challenges our deepest scientific principles, continually encouraging new research and discoveries in cosmology, quantum mechanics, and relativity. The implications of the speed of light extend into the deeper theoretical realms of physics, influencing our understanding of the universe's most extreme environments and the fundamental nature of reality itself. One significant area where the speed of light plays a crucial role is in the study of black holes and the concept of the event horizon. The event horizon of a black hole is defined as the boundary around a black hole beyond which no light or other forms of radiation can escape. The escape velocity at this boundary equals the speed of light. This means that within this boundary, even light, which is the fastest moving thing in the known universe, the implications of the speed of light extend into the realm of black holes and the event horizon, a critical boundary where the escape velocity equals the speed of light. Black holes are regions of space-time exhibiting gravitational effects so strong that nothing, not even particles and electromagnetic radiation such as light, can escape from inside it. The concept of an event horizon is intrinsically linked to the speed of light. It represents the threshold beyond which the gravitational pull is so intense that light cannot get out. Delving deeper into the nature of black holes, the speed of light plays a crucial role in defining the Schwarzschild radius, which is the radius of a sphere such that, if all the mass of an object were to be compressed within that sphere, the escape velocity from the surface would equal the speed of light. Calculating this radius involves directly using the speed of light, showing how it's intertwined with the fundamental properties of these massive objects. Furthermore, the constancy of the speed of light underpins the theoretical framework of general relativity. Einstein's field equations, which describe how matter and energy interact with the geometrical structure of space-time, rely on the invariance of the speed of light. These equations suggest that space-time is curved by matter and energy, and this curvature dictates the motion of objects and the propagation of light. Thus, the speed of light is not just a speed limit, but a fundamental descriptor of the universe's geometry. This constancy also impacts the universe's expansion. Observations of distant galaxies show that they are moving away from us, and the farther a galaxy is, the faster it appears to be receding. This observation, explained by the Hubble law, suggests that the universe is expanding at speeds that can approach the speed of light for the most distant galaxies. Here, the speed of light again becomes a crucial factor in understanding not only the mechanics of this expansion, but also its implications for the observable universe. It limits the portion of the universe we can see and interact with, as beyond a certain point, galaxies recede at a speed greater than the speed of light due to the expansion of space-time itself, making them unreachable and unobservable. Moreover, the speed of light influences the cosmic microwave background radiation, the remnant heat left over from the Big Bang. The uniformity and the slight anisotropies irregularities in the CMB carry information about the early universe's conditions. The fact that light travels at a constant speed allows cosmologists to calculate how long the light from the CMB has been traveling and thus to estimate the age of the universe. These measurements, again reliant on the speed of light, provide a cornerstone for the Big Bang theory and the subsequent evolution of the cosmos. The role of the speed of light in modern physics and cosmology is indeed profound. It not only defines the boundaries of causality and the observable universe, but also continues to challenge our understanding of the fundamental nature of time, space, and matter. As we probe deeper into the cosmos and back in time towards the moment of the Big Bang, the speed of light remains a key tool in unlocking the mysteries of the universe's origins, structure, and eventual fate. The historical journey of understanding light, from philosophical musings to precise scientific measurements, reflects a fascinating evolution of thought and technology. Aristotle, an ancient Greek philosopher, posited that light was the presence of something, but not a movement. To him, light filled the space between the source and the observer almost instantaneously. This view held sway until the 17th century, when the nature of light began to be questioned more rigorously. The 17th century marked significant shifts with the work of figures like Johannes Kepler and René Descartes, who theorized light's propagation involving some kind of motion. Descartes suggested that light was instantaneous, reflecting Aristotle's influence. But he introduced the idea that it behaved like a wave. The true nature of light began to crystallize through the work of Isaac Newton and Christian Huygens. Newton's Optics, published in 1704, proposed that light was composed of particles or corpuscles, which explained reflection and refraction phenomena. In contrast, Huygens advocated for a wave theory, where light propagated through a medium called the luminiferous ether. Despite their differing views, both theories advanced the understanding of light significantly. The debate between the particle and wave theories continued until the 19th century, when Thomas Young's double-slit experiment provided strong evidence for light's wave nature. This experiment, demonstrating interference patterns, was pivotal, aligning scientific consensus more towards the wave theory. In parallel with theoretical developments, the speed of light attracted great scientific interest. The first successful attempt to measure the speed of light was made by Danish astronomer Ole Romer in 1676. Romer observed the motions of Jupiter's moon Io and noticed discrepancies in its eclipses, which he correctly attributed to the finite speed of light affecting the light travel time from Jupiter to Earth. His calculations brought the speed of light to public scientific consciousness, although his estimated speed was lower than the actual value. The next major advancement came from James Bradley in 1728 through the phenomenon of stellar aberration. Bradley observed that the apparent position of stars shifted due to Earth's motion relative to the speed of light. His measurements were more accurate than Romer's and brought the calculated speed of light closer to its true value. The most precise early measurements of the speed of light were conducted by Hippolyte Fizeau in 1849. Fizeau used a toothed wheel to measure the time it took light to travel a specific distance and back. This method, ingenious for its simplicity and effectiveness, marked a significant step forward in experimental physics, yielding results very close to the modern value. Albert Michelson further refined the measurement in 1879 using a rotating mirror rather than a toothed wheel, which allowed for even greater accuracy. His experiments, repeated over several decades, gradually improved the precision of the speed of light measurement. The culmination of these efforts and the definitive shift from mechanical views of light to electromagnetic theory were synthesized by James Clerk Maxwell. Maxwell's equations, formulated in the 1860s, described light as electromagnetic waves traveling at a constant speed in a vacuum. This theoretical leap was validated by Heinrich Hertz's experimental demonstration of electromagnetic waves, reinforcing the wave theory of light. Albert Einstein's 1905 theory of special relativity then redefined the understanding of light within the framework of physics. He postulated that the speed of light in a vacuum is constant and is an upper limit for motion. This insight was revolutionary, showing that light's speed is a critical constant of the universe, affecting the fundamental principles of time and space. These historical perspectives, from the philosophical to the experimental, not only illuminate the evolving understanding of light, but also reflect broader shifts in scientific thinking and technological capability. Each breakthrough, from Aristotle's initial theories to Einstein's revolutionary ideas, was built upon the findings of previous scholars, showcasing the cumulative nature of scientific discovery. Continuing from the profound shifts brought about by Einstein's theory of relativity, the understanding of light has been further nuanced and expanded in the 20th and 21st centuries, particularly through the integration of quantum mechanics. After Einstein established that light was quantized into particles known as photons in his explanation of the photoelectric effect in 1905, the dual nature of light, both particle and wave, became a central tenet in physics. This duality was a foundational element of quantum mechanics, a new theoretical framework that emerged in the early 20th century to describe phenomena at microscopic scales. The quantum theory of light was further developed by scientists like Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, who introduced concepts such as wave-particle duality and uncertainty principles. These ideas were initially perplexing because they challenged classical intuitions about how particles and waves behave. In quantum mechanics, photons are described not just by their speed and particle-like interactions, but also by their wave functions, which determine the probabilities of finding them in certain states. One of the landmark experiments that further elucidated the nature of light and supported quantum theory was the demonstration of Bell's theorem experiments in the 1960s and 70s. These experiments, based on John Bell's theorem, tested the peculiar quantum phenomenon known as entanglement. They showed that particles like photons could affect each other's states instantaneously over large distances, a phenomenon that Einstein famously derided as spooky action at a distance. The results of these experiments not only supported the standard interpretations of quantum mechanics, but also deepened the understanding of the fundamental properties of light. Another significant advancement in understanding light came with the development of laser technology in the 1960s, based on the principles of stimulated emission first postulated by Einstein. The laser, an acronym for light amplification by stimulated emission of radiation, emits light coherently, allowing for a range of applications from precise cutting and welding to data storage and retrieval, and even in medical surgeries. The invention of lasers also led to new types of experimental setups to test the properties of light at both particle and wave levels. In the realm of cosmology, light's properties have been used to probe the most distant corners of the universe. The study of cosmic microwave background radiation, as mentioned previously, relies heavily on understanding light's speed and its interaction with matter. Additionally, observations of gravitational lensing, where light from distant galaxies is bent around massive objects like other galaxies or black holes, have provided direct evidence of Einstein's general theory of relativity and insights into the distribution of dark matter. Modern experiments continue to push the boundaries of how we understand light. One of the cutting-edge areas of research involves the use of light in quantum computing and quantum encryption. Photons are ideal for these applications due to their speed, small mass, and the ease with which they can be entangled. These technologies promise to revolutionize computing and communications, offering new levels of processing power and secure communication channels. Thus, the journey from the philosophical musings of ancient thinkers like Aristotle to the high-precision experiments of the modern era highlights not only the progression in our understanding of light, but also the profound ways in which this understanding reshapes technology, society, and our conception of the universe. Each discovery about light has peeled back a layer of the natural world, revealing interconnections that are at once beautiful, complex, and profoundly fundamental. Delving deeper into the implications of modern research on light, we find that advancements in photonic technologies not only enhance our understanding of quantum mechanics, but also have practical applications that could revolutionize several industries, including telecommunications, healthcare, and computing. One of the most promising fields of application for light-based technology is in telecommunications, where the use of fiber optics has dramatically transformed the landscape. Fiber optic cables, which transmit data as light pulses, offer a much higher bandwidth than traditional metal cables. This technology harnesses the principle of total internal reflection, allowing light to be efficiently transmitted over long distances with minimal loss of signal. The increasing demand for high-speed internet and data services continues to drive innovations in fiber optic technology, including the development of new types of optical fibers that can carry more data or reduce energy costs. In healthcare, laser technology has been a game changer in numerous medical procedures, offering high precision with minimal invasiveness. Lasers are used in a wide range of medical applications, from corrective eye surgery, where they reshape the cornea to correct vision defects, to the targeted destruction of tumors. Furthermore, advances in photodynamic therapy (PDT) represent a significant leap forward in treating cancer. PDT involves the use of light-sensitive drugs that, when activated by specific wavelengths of light, produce singlet oxygen to kill nearby cells. This method is particularly valued for its ability to precisely target cancerous cells while sparing the surrounding healthy tissue. The field of computing has also seen revolutionary changes with the advent of optical computing, where photons replace electrons for processing and transmitting information. Optical computers promise faster processing speeds and lower heat production compared to traditional electronic computers. While still largely experimental, optical computing could dramatically reduce the energy consumption of data centers, which is a crucial factor given the global push towards sustainability. Furthermore, light plays a critical role in the burgeoning field of quantum communications and cryptography. Quantum key distribution (QKD) uses photons to securely transmit information, with the security of these communications guaranteed by the fundamental principles of quantum mechanics. Any attempt to eavesdrop on the quantum communication would necessarily alter the quantum state of the photons, thus alerting the communicating parties to the presence of the eavesdropper. This application of light is at the forefront of efforts to develop unhackable communication systems. In scientific research, advanced light-based technologies such as super-resolution microscopy have pushed the boundaries of cellular biology by allowing scientists to observe processes at the molecular level in unprecedented detail. Techniques like STED, stimulated emission depletion microscopy, and PALM, photoactivated localization microscopy, use the unique properties of fluorescent molecules and sophisticated light manipulation to bypass the diffraction limit of conventional light microscopy. This capability has opened new avenues in neuroscience, developmental biology, and nanotechnology, among other fields. Lastly, the study of light continues to impact our understanding of the universe through astrophysics and cosmology. Techniques such as spectroscopy, which analyzes the light from celestial objects to determine their composition, velocity, and distance, remain fundamental to our study of the cosmos. The upcoming generations of telescopes, equipped with advanced light-capturing technologies, are set to explore the early universe, examine the atmospheres of distant exoplanets, and perhaps unravel more about dark matter and dark energy. Through all these developments, light remains a central pillar in science and technology, continuously expanding our capabilities and understanding of the world around us. Each new discovery in light not only adds a chapter to the rich history of scientific inquiry, but also provides new tools that can be applied across various fields of human endeavor. The speed of light, approximately 299792 kilometers per second in a vacuum, is a fundamental constant in physics that has profound implications across various scientific domains, particularly in the realms of cosmology and the theoretical limitations it imposes on space travel, as well as its effects on our understanding of time and space. Limitations in cosmic travel. The finite nature of light speed sets a universal speed limit, beyond which conventional matter or information cannot travel. This restriction is deeply embedded in the framework of special relativity, which asserts that as an object approaches the speed of light, its relativistic mass increases, requiring ever greater amounts of energy to continue accelerating. Practically, this means that reaching or exceeding the speed of light with current technology or any foreseeable technology is impossible. Consequently, interstellar travel presents enormous challenges, as even reaching our nearest stellar neighbor, Proxima Centauri, located about 424 light-years away, would take over 4 years at the speed of light, a speed unreachable for any manned spacecraft with current propulsion technology. Moreover, the energy required for propelling a spacecraft to a fraction of the speed of light is astronomically high. Current propulsion technologies, such as chemical rockets, are vastly inadequate for such tasks. Even theoretical propulsion methods, like nuclear pulse propulsion or antimatter engines, would require energy amounts that are currently beyond our capacity to produce or store safely on a spacecraft. This immense energy requirement highlights a significant barrier imposed by the speed of light, making practical and rapid interstellar travel a formidable challenge. Effects on time and space. The implications of light speed extend beyond travel limitations to the very core of how we perceive time and space. According to Einstein's theory of relativity, as an object moves closer to the speed of light, time as experienced by the object's occupants would slow down relative to stationary observers. This phenomenon, known as time dilation, has been experimentally confirmed using precise measurements from atomic clocks on fast-moving jets and satellites. Time dilation implies that for astronauts traveling at near-light speeds, a journey might seem to take only a few years, while decades or even centuries could pass on Earth. Spatial dimensions are also affected by high-speed travel. Length contraction, another prediction of special relativity, posits that objects physically contract along the direction of motion as they approach light speed. From the perspective of a stationary observer, a spacecraft moving close to light speed would appear shorter, though this effect would not be observed by those within the spacecraft due to the relativistic nature of the phenomenon. The speed of light also influences how we observe and understand the universe. The concept of the observable universe is bounded by the light that has had time to reach us since the Big Bang, approximately 13.8 billion years ago. Objects beyond this light horizon are not observable, not because they do not exist, but because their light has not yet had enough time to reach us. This horizon limits our view of the universe and shapes our understanding of its size and structure. Furthermore, the constant speed of light in vacuum conditions is used as a tool for measuring astronomical distances. Techniques such as the light-year distance metric are pivotal in mapping the cosmos. The constancy of light speed also underpins the use of standard candles, objects whose luminosities are known, and standard rulers, objects whose sizes are known in cosmology, enabling scientists to determine distances to far-off galaxies, and thereby constraining the rate of expansion of the universe. In essence, the speed of light is not just a speed limit, but a fundamental feature that shapes the structure of the universe and the nature of time itself. Its implications touch on every aspect of cosmology and relativistic physics, presenting both profound challenges to our ambitions of cosmic exploration and a framework through which the universe can be understood in a comprehensive, albeit humbling way. Continuing from the profound implications of light speed on cosmic travel and the structure of time and space, let's delve deeper into the emerging theoretical and practical approaches that could potentially mitigate the limitations imposed by the finite speed of light, and explore further how these limitations influence our understanding and strategies for future space exploration and cosmological studies. Advanced propulsion technologies. Scientists and engineers are actively researching propulsion technologies that could one day enable faster-than-current space travel, significantly cutting down the travel time to distant celestial bodies. One such theoretical concept is the Alcubierre drive, which proposes the manipulation of space-time itself to achieve effective faster-than-light travel. By expanding space-time behind the spacecraft and contracting it in front, the Alcubierre drive would allow a spacecraft to ride a warp bubble and reach destinations faster than light would in normal space-time without violating the principles of relativity. Another promising area of research is the concept of photonic propulsion, which involves the use of powerful lasers to propel spacecraft at much higher speeds than conventional rocketry. This method could theoretically propel lightweight probes to a significant fraction of the speed of light, potentially enabling interstellar missions to nearby star systems within a human lifetime. Quantum entanglement and information transfer. In the realm of quantum physics, the phenomenon of entanglement might offer some intriguing possibilities. While quantum entanglement does not allow for the transfer of matter or energy faster than light, it could potentially enable the instantaneous transfer of information across vast distances, a concept often referred to as quantum teleportation. Although practical applications are still in nascent stages, this could revolutionize communication across space, ensuring almost real-time data transfer between Earth and distant spacecraft or colonies, radically changing how missions are monitored and managed. Cosmological insights from light speed constraints. The constant speed of light not only sets a universal speed limit, but also provides cosmologists with a tool to probe the very fabric of the universe. The cosmic microwave background radiation, CMB, for instance, is a relic from the early universe that has traveled at the speed of light, offering a snapshot of the cosmos at approximately 380,000 years after the Big Bang. Analysis of the CMB's minute temperature fluctuations helps scientists map the distribution of matter and energy in the early universe, leading to better understanding of the universe's large-scale structure and the dynamics of its expansion. Additionally, the phenomenon of gravitational lensing, where light from distant galaxies is bent around massive objects like other galaxies or black holes, relies on the speed of light as a constant to calculate the mass of the intervening objects and the geometry of space-time around them. These observations are critical for testing theories of general relativity and for searching for dark matter, which indirectly influences how light travels through space. Educational and philosophical implications. Educationally, the implications of light speed encourage a deeper understanding of physics and the universe, fostering a greater appreciation for the limits of human reach and the boundless opportunities for discovery. Philosophically, the unattainable nature of light speed invites contemplation on our place in the universe, the nature of time, and the pursuit of knowledge. It questions the limits of human advancement and the ethical dimensions of future technologies that might one day break the light speed barrier, either physically or effectively through space-time manipulation. In sum, while the speed of light imposes significant limitations on cosmic travel and influences our understanding of time and space, it also opens up a myriad of scientific, technological, and philosophical areas for exploration. The pursuit to overcome these limitations not only drives technological innovation, but also deepens our understanding of the fundamental laws that govern the universe. Beyond the Alcubierre drive, there are several other theoretical concepts and speculative ideas that scientists and physicists have proposed for achieving faster-than-light FTL travel. These concepts, although highly theoretical and not without substantial scientific and technological challenges, stretch our current understanding of physics and offer intriguing possibilities for future space exploration. Here are some of these concepts. Wormholes. Also known as Einstein-Rosen bridges, wormholes are hypothetical tunnels through space-time that could connect two distant points in the universe directly. If traversable wormholes exist or could be created, they could theoretically allow for instantaneous travel between these 2 points, effectively bypassing the light speed barrier. The concept relies on solutions to the equations of general relativity that permit space-time to fold in such a way. However, keeping a wormhole open requires exotic matter with negative energy density, which has not been found to exist in any observable form. Tachyons. Tachyons are hypothetical particles that move faster than light. According to certain interpretations of special relativity, these particles would have imaginary mass and could theoretically transmit information or travel faster than light. However, no experimental evidence supports the existence of tachyons, and their theoretical basis remains highly speculative, with numerous paradoxes and issues in consistency with known physics. Quantum tunneling. While not a method of travel per se, quantum tunneling is a quantum phenomenon where a particle tunnels through a barrier that it classically shouldn't be able to pass. Some speculative theories suggest that if similar principles could be applied on a macroscopic scale, it might be possible to tunnel through space-time itself, emerging at another location faster than light would in normal space. This concept remains purely theoretical and faces significant scientific hurdles. Warp field mechanics. Inspired by the Alcubierre drive, this concept involves the manipulation of space-time itself to move a spacecraft. The idea here is to create a region of contracted space-time in front of the ship and an expanded region behind it, allowing the ship to move towards its destination faster than light relative to the surrounding space, without locally breaking the light speed barrier. This approach relies on generating and controlling negative energy densities, which is beyond current technological capabilities. Photon-based propulsion. While not inherently faster than light, Concepts like the photonic laser thruster aim to propel spacecraft to significant fractions of the speed of light. This method involves bouncing photons back and forth between a spacecraft and a stationary emitter, gradually building up momentum. Over long durations, such a system could potentially accelerate a spacecraft to speeds approaching that of light, significantly reducing travel times to distant stars compared to conventional propulsion technologies. Each of these concepts faces not only technological challenges, but also deep theoretical questions about their feasibility and the nature of reality. They challenge current understandings of physics, requiring exotic matter, enormous energy, or breakthroughs in our understanding of quantum mechanics and general relativity. As such, while they provide fascinating insights and inspiration for science fiction, their practical realization, if at all possible, lies far in the future. These concepts continue to stimulate both theoretical research and the imaginations of those keen on exploring the possibilities of what might lie beyond our current scientific limitations. The concepts of quantum tunneling and wormholes, while distinct in their physical interpretations and theoretical foundations, share a thematic connection in the sense that both involve overcoming classical barriers or constraints in unconventional ways. Here's a breakdown of each concept and how they metaphorically relate to each other. Quantum tunneling. Quantum tunneling is a quantum mechanical phenomenon where a particle violates classical mechanics by passing through a potential barrier despite not having enough energy to overcome the barrier in the classical sense. This effect is possible because of the wave-like nature of particles, as described in quantum mechanics, where there is a non-zero probability of finding a particle on the other side of a barrier, even if its energy is less than the height of the barrier. Quantum tunneling is a well-established phenomenon and has practical applications, including in the operation of tunnel diodes and the nuclear fusion reactions in stars. Wormholes. Wormholes, or Einstein-Rosen bridges, are theoretical passages through space-time that could connect two distant regions of the universe. The concept arises from solutions to the equations of general relativity, specifically those that describe black holes. A wormhole would consist of two mouths connected by a throat, potentially allowing travel between the mouths faster than light could travel through normal space-time. However, the existence of wormholes is purely speculative, and numerous theoretical challenges, such as the need for exotic matter to stabilize the wormhole throat, remain unresolved. Conceptual relationship. Both quantum tunneling and wormholes relate to the idea of bypassing normal paths or barriers. Quantum tunneling. Here, the barrier is a potential energy barrier at the quantum scale. Particles tunnel through this barrier, appearing on the other side without having surmounted the barrier in the conventional, classical way. Wormholes. In this case, the barrier is the vast distance between 2 points in spacetime. A wormhole provides a shortcut through this classical barrier, hypothetically allowing for travel or communication that is faster than would be possible by traversing the space in the standard manner. Metaphorical link. Metaphorically, both quantum tunneling and wormholes deal with achieving an end result that bypasses conventional physical limitations. Quantum tunneling does so on a subatomic scale by exploiting the probabilistic nature of quantum mechanics, while wormholes would do so on a cosmic scale by bending the fabric of space-time itself. Despite these thematic similarities, it's important to note that the underlying physics and scales of these phenomena are vastly different. Quantum tunneling is a well-documented quantum effect observable in the laboratory, whereas wormholes remain a speculative theoretical construct without empirical evidence. The connection between them is more philosophical and conceptual, highlighting the intriguing ways that physics allows for shortcuts in different contexts. Time dilation is a consequence of Einstein's theory of relativity, which tells us that time as measured by a clock depends on the relative velocity of that clock to an observer. If a clock moves relative to you, it will appear to tick slower than a clock at rest with respect to you. This phenomenon becomes significant at speeds close to the speed of light, and has profound implications for high-speed travel and the functioning of modern technology, such as GPS systems. A striking illustration of time dilation is given by the twin paradox, a thought experiment in Einstein's special relativity. In this scenario, one of two identical twins travels on a high-speed journey into space, while the other remains on Earth. Due to the effects of time dilation, the traveling twin would age slower than their sibling who stayed behind. This is not just theoretical. It has practical implications and has been tested and confirmed by experiments involving precise measurements of time for fast-moving particles and astronauts in space. For instance, astronauts on the International Space Station ISS, which orbits Earth at about 28,000 kilometers per hour, experience time slightly differently than people on Earth. Although the effect is minuscule, with astronauts aging about 0.0005 seconds less for every 6 months in orbit, it is a real effect of the velocities involved in their travel relative to the Earth's surface. Moreover, time dilation is crucial for the accuracy of the Global Positioning System GPS, which relies on a constellation of satellites orbiting the Earth. These satellites carry highly accurate atomic clocks that are synchronized with those on the ground. However, due to their relative motion with respect to observers on Earth and their position in a weaker gravitational field, another aspect of relativity known as gravitational time dilation, these clocks experience time differently. If these effects were not accurately accounted for, GPS systems would fail in their navigational calculations by about 10 kilometers each day. The system's software corrects the time in the satellite clocks to match the time observed on Earth's surface, ensuring the high accuracy and reliability of location data that we depend on. In summary, the concept of time dilation is not just a curious detail of theoretical physics. It has tangible effects on high-speed travel and essential technologies. Understanding and applying the principles of time dilation ensures the functionality of systems like GPS, and deepens our understanding of how motion affects the passage of time, as evidenced by the aging discrepancy in the twin paradox. Diving deeper into the implications of time dilation, particularly in the context of the twin paradox, reveals more about the nature of time and space as described by relativity. The twin paradox highlights a crucial aspect of special relativity, the difference between symmetric and asymmetric time experiences for observers in different inertial non-accelerating frames. The traveling twin undergoes a journey involving acceleration and deceleration, especially when reversing direction to return home, which breaks the symmetry of the situation. According to general relativity, acceleration can be indistinguishable from gravitational effects, adding complexity to the scenario and further affecting time dilation. This leads to another profound implication of relativity: gravitational time dilation, another form of time dilation predicted by Einstein's theory of general relativity. This phenomenon occurs because the presence of a massive object can warp spacetime, causing time to pass slower near the mass. The GPS satellites, while being affected by velocity-related time dilation due to their speed, are also influenced by gravitational time dilation because they are in a weaker gravitational field far from the Earth's surface compared to clocks on the ground. This dual influence requires precise adjustments. The onboard atomic clocks in GPS satellites are pre-adjusted to tick slower than ground clocks, counteracting the effects of reduced gravitational time dilation and ensuring synchronization with systems on Earth. It is fascinating to note that these relativistic effects, though small when dealing with everyday speeds and Earth's gravity, become significant and observable with current technology. For instance, experiments using highly accurate atomic clocks at different elevations have demonstrated gravitational time dilation on Earth itself. Clocks at higher altitudes, experiencing slightly weaker gravity, run faster than those at lower altitudes. Moreover, modern experiments in physics continue to test and confirm these effects with increasing precision. For example, the Haffel-Keating experiment in 1971 involved flying atomic clocks around the world in commercial airliners and comparing the elapsed time against clocks that remained stationary. The results were consistent with the predictions of relativity. showing that the flying clocks lagged behind the stationary ones by a few nanoseconds. These concepts have not only theoretical implications, but also practical applications in various fields of science and technology. Engineers and scientists must consider relativistic effects not only in GPS technology, but also in fields like particle physics and cosmology. For instance, in particle accelerators, particles moving at speeds close to the speed of light exhibit significant time dilation, affecting their decay rates and behavior. The exploration of time dilation thus serves as a powerful reminder of how relativity continues to shape our understanding of the universe, influencing both the vast cosmos and the technologies we use in everyday life. It underscores the interconnectedness of space, time, and velocity in the fabric of the universe, challenging our intuitive perceptions and inviting deeper inquiry into the fundamental nature of reality. Time dilation plays a critical role in particle physics, particularly in the behavior and observation of subatomic particles moving at relativistic speeds. Here are several key examples where time dilation is not just a theoretical curiosity, but a practical necessity for understanding and predicting experimental outcomes. Lifetime of muons. Muons are subatomic particles similar to electrons, but with a much greater mass. They are unstable and decay into electrons and neutrinos with a mean lifetime of about 22 microseconds in their rest frame. However, muons can be created in the upper atmosphere by cosmic rays striking atomic nuclei. These muons travel towards the Earth at speeds close to that of light. Due to time dilation, the muons' lifetimes as observed from the Earth are significantly extended, allowing them to reach the surface of the Earth before decaying. This effect has been confirmed by many experiments and is a classic demonstration of time dilation. Without accounting for time dilation, the number of muons detected at Earth's surface would be much fewer than what is actually observed. Particle accelerators. In particle accelerators, such as the Large Hadron Collider, particles are accelerated to speeds close to the speed of light. At these high velocities, time dilation becomes significant. For instance, particles like protons in the LHC have lifetimes that are effectively extended due to their high speed. This means they can travel much longer distances around the accelerator ring than they would in their rest frame before decaying. This extension in lifetime is crucial for conducting experiments over sufficient durations to study particle interactions precisely. Observation of particle decay. Time dilation also affects the observed decay rates of unstable particles in experiments. In high-energy physics experiments, certain particles are observed to decay much more slowly than would be expected if they were at rest with respect to the observer. This allows detailed study of their properties and the interactions that lead to their decay, which would be far more challenging if their decay rates were not extended by their high speeds. Neutrino beams. Experiments involving neutrinos often utilize beams of these incredibly light and weakly interacting particles sent over long distances. Neutrinos produced in particle accelerators can travel hundreds of kilometers to be detected in distant underground laboratories. Time dilation ensures that a significant number of these high-speed neutrinos survive long enough to be detected after their arduous journey, despite their tendency to interact only very weakly with matter. Testing fundamental symmetries and theories. Time dilation is integral to tests of fundamental symmetries in physics, such as Lorentz invariance, a cornerstone of special relativity, which states that the laws of physics are the same for all non-accelerating observers. Experiments that measure how different particles experience time under extreme conditions can provide evidence that either supports or challenges the standard model of particle physics and theories of relativity. These practical applications show that time dilation is not merely a theoretical abstraction, but a real effect that has measurable consequences in the realm of high-energy physics, impacting how experiments are designed, conducted, and interpreted. Are there any other fundamental symmetries in physics that are tested using time dilation? Yes, in addition to testing Lorentz invariance, time dilation is involved in probing other fundamental symmetries and principles in physics. These include CPT symmetry. CPT symmetry is a fundamental principle of physics, stating that the laws of nature should remain unchanged if three basic transformations are applied simultaneously. Charge conjugation C, which switches particles with their antiparticles. Parity transformation P, which inverts the spatial coordinates as in a mirror image. And time reversal T, which reverses the direction of time. Experiments involving particles and antiparticles moving at high velocities, where time dilation occurs, can test whether both behave identically under the same conditions, as predicted by CPT symmetry. Any deviation could suggest new physics beyond the current understanding provided by the Standard Model. Time translation. Symmetry and energy conservation. The principle of time translation symmetry, which implies that the laws of physics are the same at any time, is closely related to the conservation of energy through Noether's theorem. In experiments where particles travel at relativistic speeds, time dilation can affect the measurement of energy changes over time. High-energy physics experiments, such as those conducted in particle accelerators, must account for time dilation to ensure that energy is properly conserved in particle collisions and decays, thus testing the symmetry. Tests of general relativity and equivalence principle. While not a symmetry in the conventional sense used in particle physics, tests of the equivalence principle, a cornerstone of general relativity, are related to time dilation. The equivalence principle states that gravitational mass and inertial mass are equivalent, and thus the motion in a gravitational field should be indistinguishable from that in an accelerating frame. Time dilation due to gravity can be measured and compared with predictions from general relativity. Experiments such as those involving clocks on airplanes, satellites, or in high-altitude locations test this principle by observing how time dilates in different gravitational potentials. Lorentz symmetry. While Lorentz invariance was mentioned earlier, it's worth noting that Lorentz symmetry itself encompasses more than just transformations concerning relative motion. It includes transformations related to rotation in space and time. Experiments that measure how physical phenomena like the decay rates of moving particles or the behavior of fundamental forces under high-speed conditions behave can test whether Lorentz symmetry holds under extreme conditions. Deviations might indicate phenomena like quantum gravity effects or extra dimensions. These symmetries are fundamental to our understanding of the universe, and their violation could indicate new physics. High-precision experiments that utilize the effects of time dilation are essential for pushing the boundaries of these symmetrical principles, providing deeper insights into the fabric of reality. Length contraction, shrinking spaces, visualizing real-world examples, and thought experiments. In the realm of special relativity, length contraction stands as a fascinating and counterintuitive consequence of the theory. As objects approach the speed of light, their length appears to contract along the direction of motion to an observer at rest. This phenomenon, known as length contraction, challenges our intuitive understanding of space and offers a glimpse into the strange and wondrous world of relativistic physics. Visualizing length contraction. To better understand length contraction, it is helpful to visualize the scenario from both the moving object's perspective and that of a stationary observer. Imagine a spaceship traveling at nearly the speed of light, carrying a long measuring rod. To an observer on Earth, the rod appears to be shorter than its proper length due to length contraction. However, to the astronauts on the spaceship, the rod remains at its proper length, and it is the surrounding space that appears stretched. This apparent discrepancy highlights the fact that length contraction is not an absolute property, but rather a relative effect that depends on the observer's reference frame. As the spaceship approaches the speed of light, the length of the spaceship itself contracts from the perspective of an Earth-based observer, but to the astronauts on board, the spaceship remains its original length. Real-world examples and thought experiments. While length contraction may seem like an abstract concept, it has been experimentally verified and plays a crucial role in modern physics. One notable example is the behavior of muons, subatomic particles that are produced in the upper atmosphere and decay rapidly. Due to length contraction, the muon's lifetime appears longer to an observer on Earth than it does to the muons themselves, allowing them to travel further than would be expected based on their intrinsic decay rate. Thought experiments can also help us explore the implications of length contraction. Consider the classic twin paradox scenario, where one twin travels near the speed of light on a spaceship, while the other remains on Earth. When the traveling twin returns, they will have aged less than their Earth-bound sibling due to the effects of time dilation and length contraction. This thought experiment highlights the profound differences between the experiences of moving and stationary observers in the relativistic world. In the realm of special relativity, length contraction challenges our intuitive understanding of space and offers a glimpse into the strange and wondrous world of relativistic physics. By visualizing the phenomenon, exploring real-world examples, and engaging in thought experiments, we can deepen our appreciation for the fundamental principles that govern the universe and the fascinating consequences they yield. Time travel, the concept of moving backward or forward through time, has fascinated humanity for centuries. Although it remains a staple of science fiction, the scientific community continues to explore the possibility of time travel and its implications for causality and the nature of the universe. Causality is the principle that events in the universe have causes and effects, with the cause always preceding the effect. Time travel, particularly to the past, raises questions about causality and the potential for paradoxes that could arise from altering past events. The grandfather paradox is one of the most famous time travel paradoxes. It suggests that if a person were to travel back in time and kill their own grandfather before their parent was conceived, the time traveler would never have been born. This creates a logical inconsistency, as the time traveler could not have existed to go back in time and carry out the action in the first place. Another well-known paradox is the bootstrap paradox, also called the ontological paradox. In this scenario, an object or piece of information is sent back in time, becoming trapped in a causal loop where it has no discernible origin. An example would be a time traveler who receives a book from their future self, then later sends the same book back in time to their younger self, creating a closed loop without a clear starting point for the book's existence. The Novikov self-consistency principle, proposed by Russian physicist Igor Novikov, offers a potential resolution to these paradoxes. According to this principle, any action taken by a time traveler in the past must be consistent with the history that already exists. In other words, time travelers cannot change the past in a way that creates paradoxes or inconsistencies. The principle suggests that the universe has a way of self-correcting to maintain consistency, although the exact mechanism for this remains unclear. General relativity, Einstein's theory of gravitation, offers theoretical support for time travel through the concept of closed time-like curves, CTCs. CTCs are paths in space-time that loop back on themselves, allowing objects to travel back in time if they follow these curves. Some solutions to Einstein's field equations, such as those describing rotating black holes or wormholes, contain CTCs, raising the possibility that time travel could be achievable under certain conditions. However, the feasibility of time travel is still uncertain, and many challenges remain. Quantum mechanics, the theory governing the behavior of particles at the subatomic scale, does not appear to allow for time travel. The uncertainty principle, a fundamental aspect of quantum mechanics, suggests that particles do not have definite positions or velocities until they are measured, making it difficult to reconcile with the deterministic nature of time travel. Additionally, some physicists have proposed the chronology protection conjecture, which suggests that the laws of physics actively prevent the formation of CTCs and, consequently, time travel. According to this conjecture, any attempt to create a CTC would result in the destruction of the CTC or the prevention of its formation through some unknown mechanism. The debate surrounding time travel and its implications for causality continues to engage scientists and philosophers alike. While the possibility of time travel remains uncertain, Exploring the theoretical and philosophical implications of this concept can provide valuable insights into the nature of time, causality, and the fundamental structure of the universe. Delving deeper into time travel theories and paradoxes. One of the most intriguing time travel theories is the multiverse theory, also known as the many worlds interpretation. This theory suggests that there are an infinite number of parallel universes, each representing a different outcome of every possible event. In the context of time travel, the multiverse theory proposes that when a time traveler goes back in time and alters an event, they create a new, alternate timeline rather than changing the original one. This approach could potentially resolve paradoxes like the grandfather paradox, as the time traveler would not be altering their own past, but rather creating a new, separate reality. Another time travel concept is the idea of time dilation, a consequence of Einstein's theory of special relativity. Time dilation occurs when an object is moving at a significant fraction of the speed of light or is subjected to strong gravitational fields. In these situations, time passes more slowly for the object in motion or under the influence of gravity compared to an object that is stationary or in a weaker gravitational field. While time dilation is not time travel in the traditional sense, it does suggest that time can be manipulated and experienced differently under certain conditions. The twin paradox is a thought experiment that illustrates the concept of time dilation. In this scenario, one twin embarks on a journey through space at near light speed, while the other twin remains on Earth. When the traveling twin returns, they will have aged less than their Earth-bound counterpart, due to the effects of time dilation. This age difference is a consequence of the different experiences of time between the two twins, and it has been experimentally verified using precise clocks on board high-speed aircraft and satellites. Wormholes, theoretical tunnels connecting 2 points in space-time, are another concept often associated with time travel. Wormholes could potentially allow for rapid travel between distant regions of space, or even different points in time. However, the existence of wormholes remains purely speculative, and it is unclear whether they could be stable enough for practical use, or even created artificially. The concept of time travel also raises philosophical questions about free will and determinism. If time travel were possible, it could imply that the future is already set in stone, and every event, including human actions, is predetermined. This perspective seems to contradict the notion of free will, which asserts that individuals have the power to make choices and shape their own lives. The debate between free will and determinism is an ongoing one, and the potential for time travel adds another layer of complexity to this discussion. In conclusion, time travel remains a captivating and enigmatic concept that has yet to be proven feasible. The various theories, paradoxes, and philosophical implications associated with time travel continue to challenge our understanding of the universe and inspire fascinating debates among scientists, philosophers, and the general public alike. While the possibility of time travel remains uncertain, exploring these ideas can provide valuable insights into the nature of time, causality, and the fundamental structure of reality. The quest to unravel the fundamental constituents of the universe has been an enduring pursuit of humanity, one that has challenged our perceptions of reality and pushed the boundaries of our understanding. From the earliest contemplations of the ancient philosophers to the cutting-edge theories of modern physics, the exploration of the building blocks of matter has taken us on a journey that spans the realms of the infinitesimally small and the infinitely vast. At the heart of this cosmic tapestry lies the atom, the fundamental unit of matter that serves as the foundation for all the elements that make up the universe we inhabit. These microscopic structures, once thought to be the indivisible and immutable components of existence, have revealed themselves to be intricate worlds unto themselves, comprised of even smaller subatomic particles. Within the confines of the atom, a delicate dance unfolds, governed by the laws of quantum mechanics. At its core resides the nucleus, a dense concentration of protons and neutrons held together by the strong nuclear force, while the surrounding cloud of electrons, bound by the electromagnetic force, orbit in a probabilistic haze determined by the principles of wave-particle duality. The interplay between these subatomic constituents gives rise to the rich tapestry of elements that populate the periodic table, each with its unique set of properties and behaviors. From the lightest element, hydrogen, to the heaviest known elements forged in the hearts of cosmic furnaces, this diversity of elemental building blocks serves as the foundation for the vast array of chemical compounds and molecular structures that underpin the complexity of our universe. Yet, as our understanding of the cosmos has deepened, we have been confronted with a profound realization. The visible matter we can perceive and interact with is but a mere fraction of the universe's true composition. The enigmatic presence of dark matter and dark energy, two elusive and perplexing components that dominate the mass-energy budget of the cosmos, has challenged our conventional understanding and forced us to confront the vast realms of the unknown that permeate the fabric of existence. Dark matter, an unseen and enigmatic substance that exerts a gravitational pull on the visible matter in the universe, has long been a source of fascination and bewilderment for cosmologists and astrophysicists. Its presence was first inferred from the observed motion of galaxies within galactic clusters, which revealed a discrepancy between the gravitational forces at play and the visible matter present, suggesting the existence of an invisible, yet gravitationally potent, form of matter. Despite its elusiveness, dark matter plays a crucial role in shaping the cosmic tapestry, acting as a cosmic scaffolding that guides the formation and evolution of galaxies and large-scale structures throughout the universe. Its gravitational influence is the unseen hand that sculpts the intricate filaments and voids that permeate the cosmic web, leaving an indelible imprint on the distribution of matter and energy across the cosmos. Equally enigmatic is the presence of dark energy, a mysterious force that permeates the entire fabric of space-time itself, driving the accelerated expansion of the universe. First inferred from observations of distant supernovae, which revealed an unexpected dimming that could only be explained by an accelerating rate of cosmic expansion, dark energy has challenged our fundamental understanding of gravity and the expected deceleration of cosmic expansion due to the attractive force of matter. The nature of this enigmatic force remains one of the greatest mysteries in modern cosmology, forcing us to confront the limitations of our current scientific paradigms and prompting us to explore new frontiers of theoretical and observational research. Is dark energy a manifestation of Einstein's cosmological constant, a repulsive force intrinsic to the fabric of space-time itself? Or is it a dynamic, time-varying field known as quintessence, evolving over time and shaping the destiny of the cosmos in ways we have yet to comprehend? In our quest to unravel the mysteries of dark matter and dark energy, we have embarked on a multifaceted approach that combines cutting-edge observational campaigns, sophisticated computer simulations, and audacious theoretical models. Ground-based telescopes and space-based observatories, such as the James Webb Space Telescope, are probing the cosmic microwave background radiation and mapping the large-scale structure of the universe, seeking imprints and clues that could shed light on the nature of these elusive components. Particle accelerators like the Large Hadron Collider at CERN are pushing the boundaries of our understanding, searching for elusive dark matter candidates and probing the realms of particle physics that could hold the answers to these cosmic puzzles. Meanwhile, theoretical physicists and cosmologists are developing innovative models and simulations, exploring the parameter space of dark matter and dark energy, testing hypotheses, and refining our understanding of the processes that shape the cosmic landscape. As we delve deeper into the realms of the unseen, we are confronted with a profound realization. The visible matter we perceive and interact with is but a fleeting glimpse into the vastness of existence itself. The true tapestry of the universe is woven from threads of known and unknown, the seen and the unseen, the familiar and the unfathomable. It is within this cosmic interplay that we find ourselves, explorers of the infinite, seekers of truth, and stewards of knowledge. The journey to unravel the building blocks of matter and the unseen components that dominate the cosmos is not merely a scientific endeavor, but a profound expression of the human spirit, a relentless quest to push the boundaries of understanding, to transcend the limitations of our terrestrial existence, and to embrace the infinite wonders that the universe has to offer. The concept of counting atoms may seem trivial, but in the realm of astrophysics, it holds paramount importance. Accurate quantification of atomic content is crucial in understanding the composition and evolution of celestial objects. Modern astrophysics employs an array of innovative methods to count atoms, leveraging cutting-edge tools and techniques. One of the most widely used methods is spectroscopy, which involves analyzing the light emitted or absorbed by atoms and molecules. By examining the distinct spectral lines, researchers can identify the presence of specific elements and quantify their abundance. Spectroscopy can be applied to various astrophysical contexts, including the study of stellar atmospheres, interstellar gas, and planetary nebulae. Another powerful tool is the technique of atomic absorption spectroscopy, AAS. This method measures the absorption of light by atoms in a sample, allowing researchers to determine the concentration of specific elements. AAS has been instrumental in analyzing the chemical composition of stars, galaxies, and nebulae. The development of advanced telescopes and detectors has enabled the application of spectroastrometry, which combines spectroscopy with high-resolution imaging. This technique allows researchers to map the distribution of elements within celestial objects, providing valuable insights into their internal dynamics and chemical evolution. In addition to spectroscopic methods, researchers employ indirect techniques to count atoms. One such approach is the use of X-ray fluorescence, which involves exciting atoms with high-energy X-rays, causing them to emit characteristic X-rays that can be detected and analyzed. This method has been successfully applied to the study of highly ionized plasmas in black hole environments and neutron star atmospheres. The analysis of cosmic microwave background radiation (CMB) has also proven valuable in quantifying the cosmic abundance of elements. The CMB's blackbody spectrum contains subtle signatures of atomic interactions, allowing researchers to infer the abundance of light elements such as hydrogen, helium, and lithium. However, despite these advanced methods, challenges persist in accurately counting atoms. One of the primary hurdles is the complexity of astrophysical environments, which often involve intense radiation fields, strong magnetic fields, and high-energy particles. These conditions can alter the atomic energy levels, making it difficult to accurately model and interpret spectral signatures. Another challenge lies in the limitations of current detector technology. Many spectroscopic instruments are limited by their spectral resolution, signal-to-noise ratio, and detector efficiency, which can result in incomplete or inaccurate data. Furthermore, the interpretation of spectroscopic data often relies on complex models and simulations, which can introduce additional uncertainties. For instance, the treatment of atomic processes, such as ionization and recombination, can significantly affect the derived abundance values. To overcome these challenges, researchers are developing novel instrumental techniques, such as the use of advanced spectrographs and spectrometers. These instruments will provide higher spectral resolution, increased sensitivity, and improved detector efficiency, enabling more accurate and precise measurements. The development of sophisticated computational models and simulations is also crucial in addressing the challenges in counting atoms. Researchers are working to improve the accuracy and complexity of atomic models, incorporating advanced treatments of atomic processes and radiation transport. Ultimately, the quest to count atoms in the cosmos is an ongoing endeavor, driven by the need to better understand the composition and evolution of celestial objects. As new tools and techniques emerge, researchers will continue to refine their methods, pushing the boundaries of our knowledge and understanding of the universe. In the realm of modern astrophysics, the development of novel methods for counting atoms has opened up new avenues for research. One such area is the study of cosmic dust, which plays a crucial role in the formation of stars and planets. By analyzing the atomic composition of dust grains, researchers can gain insights into the chemical evolution of galaxies and the formation of planetary systems. The study of atomic abundances in white dwarfs has also garnered significant attention, as these objects provide a unique probe of the galactic chemical evolution. By analyzing the atomic composition of white dwarf atmospheres, researchers can reconstruct the history of star formation and chemical enrichment in the galaxy. Furthermore, the development of advanced computational models has enabled the simulation of complex astrophysical processes, such as supernova explosions and black hole accretion. These simulations allow researchers to investigate the role of atomic processes in shaping the cosmic environment and the formation of celestial objects. In conclusion, the methods of counting atoms in modern astrophysics are diverse and multifaceted, leveraging cutting-edge tools and techniques to quantify the cosmic abundance of elements. As researchers continue to push the boundaries of our understanding, new challenges and opportunities will emerge, driving the advancement of our knowledge and understanding of the universe. The significance of knowing the number of atoms in the universe cannot be overstated, as it has far-reaching implications for our understanding of the cosmos and the laws of physics that govern it. At its core, the number of atoms is a fundamental parameter that underlies the fabric of the universe, influencing the behavior of matter and energy at all scales. One of the most striking consequences of knowing the number of atoms is the insight it provides into the scale of the universe. The sheer number of atoms in the observable universe, estimated to be around 1080, is a staggering figure that defies human comprehension. To put this number into perspective, consider that the number of stars in the observable universe is estimated to be around 10 circumflex 24, a tiny fraction of the total number of atoms. This disparity highlights the immense scale of the universe, with atoms being the building blocks of matter that make up the vast majority of its content. Furthermore, the number of atoms has a profound impact on our understanding of the universe's evolution. The abundance of light elements such as hydrogen, helium, and lithium is a direct consequence of the number of atoms in the universe. These elements were formed during the Big Bang, when the universe was still in its infancy, and their abundance is a reflection of the universe's primordial composition. The precise measurement of these elemental abundances has led to a deeper understanding of the universe's early stages, including the formation of the first stars and galaxies. The number of atoms also has significant implications for our understanding of the fundamental laws of physics. The Standard Model of Particle Physics, which describes the behavior of fundamental particles like quarks and electrons, relies heavily on the number of atoms to constrain its parameters. For example, the precise measurement of the proton's mass, which is a function of the number of atoms, has led to a deeper understanding of the strong nuclear force and the structure of atomic nuclei. Moreover, the number of atoms has far-reaching implications for cosmology, the study of the universe on its largest scales. The distribution of matter and energy in the universe, which is directly influenced by the number of atoms, has a profound impact on the universe's large-scale structure. The formation of galaxy clusters, superclusters, and even the cosmic web itself is a direct consequence of the number of atoms in the universe. The precise measurement of these structures has led to a deeper understanding of the universe's evolution, including the role of dark matter and dark energy. In addition, the number of atoms has significant implications for our understanding of the universe's fate. The ultimate fate of the universe, whether it will continue to expand indefinitely or eventually collapse in a big crunch, is directly influenced by the number of atoms. The precise measurement of the universe's density, which is a function of the number of atoms, has led to a deeper understanding of the universe's long-term evolution. The significance of knowing the number of atoms is further underscored by its connection to the concept of entropy, a measure of the universe's disorder or randomness. The number of atoms in the universe is directly related to the universe's entropy, which has far-reaching implications for our understanding of the universe's evolution. The second law of thermodynamics, which states that entropy always increases over time, is a direct consequence of the number of atoms in the universe. Furthermore, the number of atoms has significant implications for our understanding of the universe's quantum nature. The precise measurement of the number of atoms has led to a deeper understanding of the quantum behavior of particles, including the phenomenon of quantum entanglement. The connection between the number of atoms and the quantum nature of the universe is a testament to the profound interconnectedness of the universe's fundamental laws. In conclusion, the significance of knowing the number of atoms in the universe cannot be overstated. It has far-reaching implications for our understanding of the universe's scale, evolution, and fundamental laws. The precise measurement of the number of atoms has led to a deeper understanding of the universe's composition, structure, and fate, and has underscored the profound interconnectedness of the universe's fundamental laws. Integrating light, time, and atoms, unveiling the intricate relationships in modern science. In the realm of modern science, three fundamental concepts reign supreme: light, time, and atoms. These concepts have been studied extensively in isolation, but their interplay has revealed fascinating phenomena that have revolutionized our understanding of the universe. In this text, we embark on a journey to explore the intricate relationships between light, time, and atoms, and how they have shaped the face of contemporary science. Light, the electromagnetic radiation that traverses the cosmos, has been a subject of interest since ancient times. From the study of optics to the discovery of lasers, light has been a vital tool in understanding various phenomena. However, the integration of light with time and atoms has led to groundbreaking discoveries. The concept of time dilation, for instance, illustrates how time and light are intertwined. According to Albert Einstein's theory of relativity, the passage of time is relative and can be affected by factors such as speed and gravity. This idea has been proven through experiments such as the Pound-Rebka experiment, where the gravitational redshift of light was observed. The interaction between light and atoms has also led to significant breakthroughs. The concept of quantum mechanics, which describes the behavior of matter and energy at the atomic and subatomic level, has been instrumental in understanding the nature of light. The discovery of photons, the particles that make up light, has revealed the dual nature of light, exhibiting both wave-like and particle-like properties. This property has led to the development of technologies such as lasers, solar cells, and LEDs. Furthermore, the integration of light, time, and atoms has led to the discovery of exotic phenomena such as quantum entanglement and the photoelectric effect. Quantum entanglement, a phenomenon where particles become connected and can affect each other instantaneously, has been demonstrated through experiments involving entangled photons. The photoelectric effect, where light hitting a metal surface can eject electrons, has led to the development of technologies such as solar cells and computer chips. In addition, the interplay between light, time, and atoms has led to the exploration of new frontiers such as quantum computing and cryptography. Quantum computing, which utilizes the principles of quantum mechanics to perform calculations, has the potential to solve problems that are currently unsolvable with classical computers. Quantum cryptography, which uses entangled photons to secure communication, has been used to create ultra-secure communication channels. In conclusion, the integration of light, time, and atoms has led to a plethora of groundbreaking discoveries and technologies in modern science. The interplay between these concepts has not only deepened our understanding of the universe, but has also opened up new avenues for research and development. As scientists continue to explore the intricate relationships between light, time, and atoms, we can expect even more exciting breakthroughs that will shape the future of humanity. The relationship between light, time, and atoms is a fascinating area of study that has led to many groundbreaking discoveries in modern science. Here are some additional examples of how these concepts are interconnected. Quantum entanglement. As mentioned earlier, quantum entanglement is a phenomenon where two or more particles become connected in such a way that their properties are correlated, regardless of the distance between them. This phenomenon is a result of the interplay between light, time, and atoms. Entangled particles can be created by manipulating the quantum state of atoms using light, and the entanglement can be measured using various techniques, including the detection of photons. Quantum teleportation. Quantum teleportation is a process that allows information to be transmitted from one particle to another, without physical transport of the particles themselves. This is achieved by using quantum entanglement and the principles of quantum mechanics to transfer information from one particle to another. Quantum teleportation has the potential to revolutionize communication and data transfer, and it relies on the interplay between light, time, and atoms. Quantum computing. Quantum computing is a field of study that aims to develop computers that can solve problems that are currently unsolvable or require an unfeasible amount of time to solve using classical computers. Quantum computers rely on the principles of quantum mechanics to perform calculations, and they use quantum bits qubits instead of classical bits. Qubits can be manipulated using light, and the quantum state of atoms can be used to store and process information. Quantum cryptography. Quantum cryptography is a method of secure communication that uses quantum mechanics to encode and decode messages. This method relies on the principles of quantum entanglement and the no-cloning theorem, which states that it is impossible to create a perfect copy of an unknown quantum state. Quantum cryptography is theoretically unbreakable, and it has the potential to revolutionize secure communication. Time dilation. Time dilation is a phenomenon predicted by Einstein's theory of relativity, which states that the passage of time can be affected by factors such as gravity and motion. This phenomenon has been observed and studied extensively, and it has important implications for our understanding of the universe. For example, time dilation can be used to explain the behavior of clocks on board GPS satellites, which are essential for navigation and positioning. Gravitational redshift. Gravitational redshift is a phenomenon predicted by Einstein's theory of general relativity, which states that the gravitational field of a massive object can affect the frequency of light emitted by the object. This phenomenon has been observed in various astrophysical contexts, such as the redshift of light emitted by white dwarfs and neutron stars. These are just a few examples of the many ways in which light, time, and atoms are interconnected in modern science. The study of these concepts continues to be an active area of research, with new discoveries and breakthroughs being made regularly. As we peer into the horizon of physics, the exploration of dark matter and dark energy remains one of the most tantalizing frontiers. These mysterious components constitute about 95% of the universe, yet their true nature remains largely elusive. Theoretical physicists and cosmologists are pushing the boundaries with new models and experiments, such as the use of direct detection experiments that seek to capture dark matter particles as they pass through detectors, and the mapping of cosmic microwave background radiation to understand the influence of dark energy on the universe's expansion. Another significant direction involves the unification of gravity with quantum mechanics. General relativity and quantum mechanics, pillars of modern physics, work well in their respective realms, but famously clash when combined. String theory and loop quantum gravity are leading candidates in this quest, proposing that at a fundamental level, everything in the universe is composed of vibrating strings or loops of spacetime, respectively. New experimental approaches, potentially involving observations of black holes and the behavior of spacetime at the Planck scale, are critical to testing these theories' predictions. The realm of neutrino physics also offers a fertile ground for discovery. Neutrinos are among the most abundant particles in the universe, yet they interact very weakly with matter, making them incredibly difficult to study. Recent advancements in neutrino detection technology could help answer fundamental questions about their masses, the possibility of right-handed neutrinos, and their role in the asymmetry between matter and antimatter in the universe. Quantum computing and information science not only represent a technological revolution, but also provide a new toolkit for testing the foundations of quantum mechanics itself. Questions about the nature of quantum entanglement, superposition, and decoherence might be explored through the lens of quantum computational processes, which require maintaining coherent quantum states over timescales and complexities previously unattainable in experimental physics. On the more applied side of physics, the development of ultra-precise timekeeping and measurement devices using quantum phenomena could revolutionize how we measure everything from gravitational waves to the fine structure constant. Such precision measurement could lead to new standards in technology and industry, influencing everything from navigation systems to secure communications networks. Philosophically, these advances challenge our understanding of reality. The potential discovery of other dimensions, or the realization that space-time might be quantized, can alter our metaphysical view of the universe, blurring the lines between the known and the unknown, the tangible and the abstract. The philosophical implications extend into the realm of determinism, causality, and the nature of information and reality itself. Personal reflections on these topics often lead to awe and a deeper appreciation for both the complexity of the cosmos and the ingenuity of human inquiry. The pursuit of knowledge in physics embodies a profound narrative of exploration and discovery, reflecting our intrinsic desire to understand the universe and our place within it. These explorations not only satiate our curiosity, but also hold practical implications that could transform society through new technologies and a deeper understanding of the forces that govern our existence. As we continue to push the boundaries of what is known, the integration of technology, experimental innovation, and theoretical breakthroughs in physics will likely unravel more of the universe's mysteries. This journey, inherently interdisciplinary and global, not only reshapes our scientific landscape but also profoundly impacts our philosophical and cultural frameworks, inviting us to rethink what it means to know and understand. Advancing into new territories of physics also involves the exploration of quantum gravity. This field seeks to describe the gravitational force according to the principles of quantum mechanics, and a successful theory could provide insights into the early moments of the Big Bang where current theories break down. Experiments such as the detection of gravity waves from the merging of black holes and neutron stars are offering new data points, potentially providing clues to a quantum theory of gravity. Moreover, hypothetical particles like gravitons, predicted as quantum carriers of gravity, remain a significant area of interest. Detecting such particles would be a monumental step in physics, though no current technology can achieve this directly. Additionally, the physics community is increasingly turning its attention to the information paradox in black holes. This paradox, which highlights a conflict between quantum mechanics and general relativity, questions what happens to information when matter falls into a black hole. The recent theoretical advancements suggest that information may not be lost, but could be scrambled and emitted back out via Hawking radiation, a concept that has profound implications for understanding the fundamental nature of information in the universe. Another promising area is the study of complex systems and chaos theory in quantum systems. While traditionally associated with classical physics, recent developments have explored how quantum properties influence chaotic systems. This research could vastly improve our understanding of everything from weather patterns to economic systems, and even brain function, by applying quantum computational models to these traditionally intractable problems. In terms of practical applications, the ongoing advancements in materials science, particularly through the use of physics-based insights, are leading to the development of metamaterials with properties not found in nature. These materials can manipulate electromagnetic waves in unconventional ways, leading to potential new technologies in optics, telecommunications, and cloaking devices. Philosophically, the potential discoveries in quantum mechanics and cosmology could lead to a new understanding of causality, locality, and the concept of time. These fundamental aspects of reality, when viewed through the potentially counterintuitive findings in modern physics, invite a reconsideration of how we conceptualize the universe and our interactions with it. The philosophical ramifications could extend into existential realms, influencing everything from the free will debate to our understanding of consciousness. Reflecting personally on these developments, there is a profound sense of entering uncharted waters where each discovery not only answers old questions, but also unveils a myriad of new mysteries. It's a reminder of the perpetual frontier of human knowledge and a call to future generations to continue the quest for understanding. The journey of physics is far from linear. It is a vibrant testament to human creativity and resilience, showing that our capacity for wonder and inquiry can lead to practical solutions and deeper philosophical insights. Detecting gravitons, the hypothetical quantum particles of the gravitational field, remains one of the most challenging and speculative endeavors in physics due to the extraordinary weakness of the gravitational force compared to other fundamental forces. Because gravitons are expected to interact very weakly with matter and have extremely low energy, direct detection is beyond the reach of current technology. However, there are some theoretical approaches and indirect methods that researchers consider when exploring the quantum aspects of gravity, including the potential detection of gravitons. Gravitational wave observatories. While not directly designed to detect gravitons, observatories like LIGO Laser Interferometer Gravitational Wave Observatory and Virgo are crucial in studying the properties of gravitational waves, which in quantum theory could be mediated by gravitons. By analyzing the quantum noise and detailed characteristics of these waves, physicists hope to gather data that might hint at the quantum nature of gravity, and thus the presence of gravitons. Any anomalies in the expected classical wave patterns could provide clues about their quantum origins. Cosmic Microwave Background (CMB) experiments. Experiments that study the polarization of the cosmic microwave background, such as the BICEP and Planck missions, also contribute indirectly to our understanding of the quantum aspects of gravity. These studies focus on detecting patterns of B-mode polarization, which are believed to be caused by primordial gravitational waves from the early universe. These primordial waves could theoretically involve gravitons if gravity is quantized. High-energy particle colliders. While currently no particle collider is capable of directly detecting gravitons due to their expected low interaction with matter and high energy requirements, theoretical models often suggest that certain types of particle collisions could emit gravitons. If these gravitons escape into extra dimensions, as predicted by some theories like string theory, they could potentially be inferred by missing energy and momentum in collider experiments. Projects like the Large Hadron Collider LHC look for such anomalies, which could suggest the existence of gravitons. Theoretical proposals involving quantum optics. Some theoretical proposals suggest using quantum optics techniques to detect gravitons. For example, setups using highly sensitive light interferometers, beyond even the capabilities of LIGO, might one day be capable of detecting the quantized nature of the gravitational field. These remain speculative, but are part of ongoing theoretical research. Space-based experiments. Future space-based experiments and observatories might provide the necessary sensitivity and environmental conditions, such as ultra-low noise levels, not achievable on Earth, to explore the quantum properties of gravity further. Proposals for such missions are in the conceptual stage and would aim to test various aspects of gravitational physics with unprecedented precision. In summary, while direct detection of gravitons remains a formidable challenge, ongoing advances in gravitational wave astronomy, particle physics, and theoretical research continue to improve our understanding of quantum gravity, potentially paving the way for indirect evidence or new theories that could explain how gravitons might be detected or inferred. Gravitational wave astronomy has rapidly developed since the first detection of gravitational waves in 2015 by the Laser Interferometer Gravitational Wave Observatory LIGO. This groundbreaking discovery opened a new window onto the cosmos, providing insights into phenomena that are invisible in traditional electromagnetic observations. Here are some recent advancements in this exciting field. Increased detection sensitivity. The The sensitivity of LIGO and its counterparts like Virgo and Kagra has continuously improved through hardware upgrades and better data analysis techniques. Enhanced sensitivity allows these detectors to observe gravitational waves from a broader range of sources and at greater distances, increasing the volume of the universe we can study. These improvements have led to a higher frequency of detected events, including binary neutron star mergers, binary black hole mergers, and possibly black hole neutron star mergers. Discovery of diverse and complex sources. The range of phenomena detectable through gravitational waves has expanded. For instance, the detection of binary neutron star merger GW170817 was a milestone, providing not only gravitational wave signals, but also electromagnetic counterparts across the spectrum. This event confirmed that such mergers are a source of short gamma-ray bursts and heavy elements like gold and platinum. More recently, detectors have observed events that suggest the existence of intermediate mass black holes, potentially filling in a long missing piece of the cosmic puzzle regarding black hole demographics. Multi-messenger astronomy. The field of multi-messenger astronomy, which combines gravitational wave detections with observations across the electromagnetic spectrum and other cosmic messengers like neutrinos, has blossomed. This approach was spectacularly validated with GW170817 and continues to be a powerful method for understanding the physics of cataclysmic events. Multi-messenger observations allow scientists to correlate the timing and location of gravitational wave events with other cosmic phenomena, enhancing our understanding of the life cycle of stars, the behavior of matter under extreme conditions, and the expansion rate of the universe. Tests of general relativity. Gravitational waves provide an unprecedented testing ground for Einstein's theory of general relativity. Observations to date have supported the theory's predictions, including the propagation speed of gravitational waves and the nature of black hole horizons. Advanced detectors are now testing other aspects, such as the polarization of gravitational waves and potential deviations from predictions in the strong gravitational fields of merging black holes. Global network of detectors. The global network of gravitational wave observatories has expanded. Japan's Kagra joined LIGO and Virgo, enhancing the ability to triangulate the source locations of gravitational waves more precisely. Plans for future detectors like LIGO India and the proposed Einstein telescope in Europe aim to further increase the global network's sensitivity and sky coverage. Cosmological insights. Gravitational waves are becoming a tool for cosmology, offering new methods to measure the expansion rate of the universe, the Hubble constant independent of traditional ladders used in electromagnetic observations. This could help resolve current discrepancies in measurements of the universe's expansion rate, which is a significant debate in modern cosmology. These advancements highlight the dynamic and rapidly evolving nature of gravitational wave astronomy, which continues to transform our understanding of the universe's most extreme and enigmatic phenomena. The field of gravitational wave astronomy is poised for significant advancements over the coming years and decades. These advancements will not only enhance our understanding of the universe, but also open up new realms of astrophysical research. Here are some of the key potential future developments. Next-generation detectors. Future detectors, such as the Einstein Telescope ET in Europe and the Cosmic Explorer CE in the US, are planned to be much larger and more sensitive than current facilities. These detectors will be able to probe a greater volume of the universe, detecting events that are further away and fainter, thus increasing the event detection rate significantly. They will provide better insights into the population statistics of black holes and neutron stars, and possibly uncover new types of astrophysical objects, space-based observatories. The planned Laser Interferometer Space Antenna LISA, a European Space Agency mission expected to launch in the early 2030s, will consist of 3 spacecraft arranged in a triangular formation millions of kilometers apart. LISA will be sensitive to lower frequency gravitational waves than those detected by ground-based observatories, potentially observing supermassive black hole mergers, extreme mass ratio in spirals, and even the background hum of gravitational waves from the early universe. Improved sensitivity and resolution. Advances in technology and data analysis will improve the sensitivity and spatial resolution of gravitational wave detectors. Enhanced sensitivity will allow for the detection of signals from the earlier phases of binary and spirals, providing more detailed information about the orbits and properties of the objects involved. Higher resolution will improve the localization of gravitational wave sources, facilitating better multi-messenger observations. Quantum technology. Incorporation of quantum technologies, such as squeezed light, which is already being implemented in some detectors, could further enhance the sensitivity of gravitational wave observatories. Future developments in quantum computing and quantum sensors might also provide new tools for data processing and noise reduction. Multi-messenger astronomy and collaboration. As gravitational wave detectors improve and more observatories come online, multi-messenger astronomy will become even more robust. The collaboration between facilities detecting electromagnetic signals, neutrinos, and gravitational waves will lead to a more comprehensive understanding of cosmic events. This synergy will be crucial in studying phenomena such as neutron star mergers, supernovae, and gamma-ray bursts. Probing fundamental physics. Gravitational waves offer a unique avenue for testing the fundamentals of physics, including general relativity, the properties of black holes, and potentially even the nature of dark matter and dark energy. As detections become more common and detailed, gravitational wave astronomy will contribute significantly to high-energy physics, cosmology, and the understanding of gravity at both the quantum and macroscopic levels. New phenomena and sources. As the observational reach expands and sensitivity improves, it's likely that gravitational wave observatories will discover previously unknown sources of gravitational waves. These could include cores of exploding stars, phase transitions in the early universe, or even hypothetical objects like boson stars. These potential advancements promise not only to deepen our understanding of known astrophysical phenomena, but also to possibly uncover new physics or cosmological principles, thus continuing to revolutionize our view of the universe. Let's delve deeper into some of the specific areas where gravitational wave astronomy could lead to groundbreaking advancements and discoveries. Exploration of early universe phenomena. Gravitational waves provide a unique window into the very early universe, a time that is not accessible by traditional electromagnetic observations due to the opacity of the universe before recombination, approximately 380,000 years after the Big Bang. Gravitational wave observatories like LISA might detect backgrounds of gravitational waves produced by a variety of high-energy processes in the early universe, such as phase transitions, cosmic strings, or inflation. These observations could offer unprecedented insights into the physics governing the universe at these extreme energy scales and very early times, potentially unlocking mysteries about the universe's initial conditions and evolution. Tests of general relativity in the strong field regime. Gravitational waves allow for precision testing of general relativity in ways that were not possible before. Observations from black hole mergers, in particular, provide a direct probe of the strong field regime of gravity. Future observations will help to test predictions such as the no-hair theorem, which posits that black holes can be completely described by just three external observables: mass, charge, and angular momentum, and the area increase theorem. Any deviations from the predictions of general relativity could indicate new physics, potentially pointing towards a theory of quantum gravity or other modifications to our understanding of space-time and gravity. Advanced multi-messenger astronomy. As gravitational wave detectors become more sensitive and are joined by new facilities around the globe, the ability to quickly and accurately locate the sources of gravitational waves improves. This enhanced localization is critical for follow-up observations with telescopes that observe in the electromagnetic spectrum, neutrinos, or cosmic rays. For instance, after detecting a neutron star merger through gravitational waves, astronomers could aim other telescopes to the event's location to observe gamma-ray bursts, X-rays, or visible light emissions. This comprehensive approach not only helps in understanding the physics of these cataclysmic events, but also contributes to our knowledge of the chemical enrichment of the universe through processes like our process nucleosynthesis, which occurs during such mergers. Insights into black hole and neutron star populations. Continued observations of gravitational waves from black hole and neutron star mergers are expanding our understanding of these objects' mass and spin distributions, their rates of formation, and their evolutionary histories. This information provides crucial input for stellar evolution theories and the life cycles of galaxies. As more detections are amassed, statistical analyses will refine our models of how binary systems form and evolve, including the influence of environmental factors like metallicity and dynamical interactions in dense stellar environments. Gravitational wave cosmology. Gravitational waves also offer a new method to measure the expansion rate of the universe. By using the standard siren method, where the gravitational wave signal provides a direct measure of the distance to the source, while electromagnetic observations identify the host galaxy, astronomers can calculate the Hubble constant independently of the traditional distance ladder approach. This could help resolve the current tension between different measurements of the universe's expansion rate, which is one of the major unresolved issues in cosmology today. Discoveries yet imagined. The history of astronomy teaches us that each new observational medium eventually leads to discoveries that were entirely unforeseen. Similarly, as gravitational wave astronomy matures, it is likely to reveal phenomena and objects that we have not yet imagined, continuing to enrich our understanding of the cosmos. These potential breakthroughs and advancements in gravitational wave astronomy not only promise to deepen our understanding of the universe, but also challenge and possibly extend the current frameworks of physics and cosmology. The concept of quantum physics is delightfully peculiar, isn't it? It's so interesting how the rules of the quantum world are different from what we're used to. The rules that govern how this world operates at the level of atoms and elementary particles are truly extraordinary, and it's so fascinating to learn about them. They even regulate the behavior of light and matter in ways that we are only just beginning to understand. The wonderful Richard Feynman described it as governing the behavior of light and matter. It is truly amazing to think that there are principles at work in the quantum world that are so different from the principles we are familiar with, which we call common sense. It's so interesting to see how quantum laws challenge our usual ideas about reality. They even tell us that a cat can be both alive and dead at the same time, and that a particle can exist in 2 different locations at once. And there's more. Guess what? Any particle can also be considered a wave, and there more. Isn't it amazing? Everything that exists in the quantum universe can be defined exclusively in terms of waves, or entirely in terms of particles. It's totally up to you which you prefer. The equations that describe the fascinating world of quantum waves were discovered by the brilliant Erwin Schrödinger. He was quite the genius. Guess who came up with the equations that describe the quantum world of particles? The brilliant Werner Heisenberg. And there's more. Paul Dirac made an incredible discovery. These 2 interpretations of reality are actually comparable and depict the same quantum universe. By the time the 1920s came to a close, it was clear that something truly amazing was happening in the world of physics. But even though it was all so exciting, lots of physicists and ordinary folks alike were left wondering, what was really going on? It seemed like no one could give a simple, everyday explanation. You might choose to put this issue to the back of your mind, hoping it will go away on its own at some point in the future. The wonderful thing about equations is that they can be used in so many different ways. These amazing equations can be used to create a laser, describe the structure of DNA, or even construct a quantum computer. And so it came to pass that an entire generation of students was given the exciting challenge of shut up and do the math. This meant they could focus on the numbers without worrying about the meaning of the equations, which was great. This is a bit like telling someone to plug your fingers into your ears while typing la la la. I can't hear you. Luckily, there are still some physicists out there looking for a bit of solace and tranquility during this time. In their quest to explain the wonders of the quantum realm, these brilliant minds have already come up with lots of clever ways of doing so, some more daring than others. The term interpretations refers to these means, which encompass quanta of consolation, and they are a wonderful thing. Each of these interpretations is special and fascinating in its own way. While interpreters and their followers may have their own favorites, it's clear that each interpretation has its own light of genuine faith. On the other hand, heretics are folks who embrace different beliefs. But when we look at it from a mathematical point of view, they're all equally valid. There's a good chance we're missing something big here. Who knows? Someday, we might even discover an amazing new description of the world. This new description will be able to make all of the same predictions as contemporary quantum theory, and it will also make sense. At the very least, there's still hope. In the meantime, I'm really excited to share an in-depth look at the core interpretations of quantum physics with you. They all seem pretty out there when you think about them logically, but that's what makes them so intriguing. And some are even more out there than others. In the quantum world, being a little bit crazy doesn't necessarily mean you're unfaithful. And you know what? Being a little bit crazy doesn't necessarily mean being unfaithful. I've picked 6 examples, which is my usual half dozen, mostly to justify including a passage from Through the Looking Glass as an epigraph. I'd love to hear your thoughts on the relative qualities of both of them. And if you want to, you can just cover your ears and sing la la la, I can hear you. No pressure though. But before I jump in and start sharing my thoughts, I'd love to take a moment to explain what we're trying to understand together. It's so interesting how scientific research often advances in spurts. It's like they say, 1 step forward, 2 steps in place. It would be absolutely wonderful to start off with 2 big leaps forward, which would be another way of saying thank you to Charles Ludwig Dodgson, who is more commonly known as Lewis Carroll. The double-slit experiment is an absolutely fascinating phenomenon that has shed light on the intriguing nuances of the quantum world. The wonderful Richard Feynman, who was awarded the Nobel Prize for his contributions to quantum physics, had a different name for it: the 2-hole experiment. He made a bold and brilliant claim that this phenomenon cannot be explained in a classical manner in any way, shape, or form. This amazing phenomenon contains a fundamental component of quantum physics. It's actually hiding one pretty amazing secret and includes all the building blocks of quantum physics. This experiment has shown us something truly amazing: that light is a specific type of wave. It might be a bit of a surprise to those of you who remember learning about it in your high school physics class. In the classic school experiment, we start by filling a dark room with light, which then flows onto a simple screen made of paper or cardboard. It has 2 tiny holes, or, in other forms, 2 narrow slits that are really quite small. On the other side of this screen is another screen that is completely free of any holes. After traveling through 2 little holes in the first screen, light makes its way into the second screen, where it creates an amazing pattern of light and shadow. The incredible process of diffraction is the term used to describe how light is deflected from the holes. And the pattern that results is truly a remarkable interference pattern. This amazing thing happens because 2 beams of light from 2 holes interact with each other. And there's more. This pattern is just like the pattern that would be produced if light were to move in the form of a wave through space. Sometimes the waves come together in a truly spectacular fashion, forming a bright and beautiful spot on the second screen that's absolutely breathtaking. And the best part is, this amazing phenomenon occurs in certain locations. In some cases, something truly amazing happens. The peak of one wave meets the bottom of another, creating a truly spectacular display of light and shadow. In an amazing display of mutual compensation, a dark stain is left behind. Isn't that something? It's truly amazing that you can even see this same kind of interference pattern in the waves that break apart on the calm surface of a pond when 2 pebbles are thrown in at the same time. Guess what? the brightest spot of light on the second screen is not just behind one of the holes, it's exactly halfway between both. This is one of the coolest things about this kind of interference. It's totally unique. It's truly amazing. There will be light in a stream of particles where you would expect to see complete darkness on the second screen. Absolutely. If light were a stream of particles, you would definitely see something really cool. You would see a brilliant spot formed behind each hole and darkness between them. Everything is going really well so far. In the early 19th century, Thomas Young came up with an amazing idea. That light moves like a wave. I'm so happy to say that this experiment proves that this hypothesis is correct. In an unfortunate turn of events, another experiment in the early 20th century proved that light behaves similarly to a stream of particles. In a truly brilliant experiment, a beam of light was used to remove electrons from a metal surface. This truly amazing phenomenon is called the photoelectric effect. In an absolutely amazing discovery, it was found that the energy of the electrons ejected was the same for light of any color. Isn't it amazing that bright light causes a greater number of electrons to be removed from the surface? But here's the really cool part. The energy of these electrons remains the same. It's the same energy as the energy of a smaller number of electrons removed by dim light. Isn't that fascinating? Guess who explained this amazing phenomenon? None other than Albert Einstein himself. Einstein made a truly brilliant move. He used light particles, which we now refer to as photons, and which he himself referred to as light quanta. Isn't it amazing that the color of a photon and the amount of energy it contains are directly correlated? Isn't it amazing that for any given color, all photons carry the same amount of energy? I just love Einstein's theory. It's pretty mind-blowing to think that a single quantum of light has this incredible ability to transfer its entire energy to a single electron. Isn't it amazing how light amplification is simply a matter of increasing the number of photons? You might be surprised to learn that photons are quanta of light. Isn't it amazing that each photon can give an electron the same amount of energy? Oh, Einstein didn't actually win the Nobel Prize for the theory of relativity. He won the Nobel Prize for his incredible work in physics. For 100 years, light was thought of as a wave. But then something truly amazing happened. It was researchers in the field of physics who had the brilliant idea of thinking of light as a particle. And if that is the case, it would be absolutely amazing if we could explain the experiment that involved two holes. Oh my, things are really starting to get interesting. When physicists saw that experiments with the photoelectric effect made them think that light might not be a wave after all, they were absolutely thrilled in 1920. In a truly amazing discovery, scientists found that the tiniest particle in the universe, the electron, can actually behave like a wave. In a truly fascinating experiment, electron beams were directed onto a series of leaves made from gold foil. Isn't that amazing? The leaves were of varying thicknesses, from 0.001 to 0.001 millimeters, to leaves of gold foil that were between 1,000th and 100,000th of a millimeter in thickness. Isn't that fascinating? The researchers were absolutely delighted to see what came out of the metallic foil on the other side of the leaves. Exciting new research has shown something really amazing. When beams of electrons pass through gaps between atoms in a metal's atomic lattice, they behave in a strikingly similar way to light being scattered in an experiment with two holes. George Thomson was awarded the Nobel Prize for his amazing work showing that electrons are waves. He was lucky enough to see his dad, Joseph John Thomson, win the Nobel Prize for proving that the electron is a particle. Both awards were so well-deserved. It's the perfect time to celebrate these amazing achievements that show just how special and unique the quantum universe is. And there's more. The riddle of wave-particle duality, or the wave-particle duality as it came to be known beginning in the 1920s, was at the core of theoretical discussion about the meaning of quantum mechanics. And what an exciting topic it was. The great news is that physicists were able to find some peace of mind by thinking about the basics of quantum mechanics. I'll explain more about this in a later section. But the best is yet to come. In the 1970s, a series of incredible experiments brought the riddle back into the spotlight. It was a truly magnificent sight to behold. So, I'm going to skip over half a century of searching for solace and instead present you with the contemporary facts concerning this key mystery. And don't forget what Mark Twain said: truth is often stranger than fiction. Fiction has to stay within the bounds of plausibility, but the truth is so much more exciting. If you're having trouble believing what's about to happen, don't worry, just remember this. In 1974, 3 Italian physicists named Pier Giorgio Merli, Gianfranco Messiroli, and Giulio Pozzi made an incredible discovery. They developed a method that allowed them to see a process that was comparable to the electron two-hole experiment. In a clever move, they used a beam of electrons emitted from a filament rather than a beam of light from the filament. The amazing apparatus, an electron biprism, was used to pass the beam through. And now, something truly amazing is about to happen. The electrons enter the biprism through one little entrance and come into contact with an electric field. This is really cool because it causes the beam to be divided in half. In a truly remarkable feat of engineering, one outlet is used to release half of the electrons, while the other exit is used to release the other half. Isn't that amazing? The best part is that only one exit is needed, while the other half leaves through the other, creating a seamless and elegant solution. And then, something really cool happens. Each electron hits a detection screen that's like a computer screen. It's so amazing to see the impact of each electron leave a white dot on the screen. The best part is that these dots stay on the screen for a long time, creating an amazing pattern as more and more electrons move through the setup. It's so cool to watch. As the installation continues to expand, a picture that is well organized appears on the screen, and it's absolutely amazing. And now for the really cool part. When a beam of electrons passes through the device, they leave a number of overlapping dots on the screen that form a pattern. It's really quite fascinating to see. This pattern is something really cool. It's an interference pattern, which is a characteristic of waves. When one electron is sent into a biprism, it flies out of one or another output with a 50% probability of either outcome. And guess what? It leaves a dot on the screen. This was an amazing discovery in itself. This is so fascinating. It's totally possible that even though electrons are particles, they could interact with each other and create an interference pattern. There are so many electrons in the beam. They're all traveling through the installation together. It's truly amazing that waves on the surface of water can also produce interference patterns. And water is made up of tiny molecules, which we can think of as particles. And there's more. Guess what? Waves also form interference patterns. But there was still more to come. The Italian experiment was so precise that it allowed electrons to be discharged one after the other, just like airplanes taking off from a crowded airport. It was truly a remarkable feat of precision. In an amazing turn of events, the electrons flew one after the other with a large delay between each one, just like airplanes taking off. The detector screen was located 10 meters away from the source of electrons, which was created in a truly ingenious manner. It was a little more inventive than a plain filament, and it was a real feat of engineering. And the truly incredible thing is that the next electron didn't leave the source until after the one before it had arrived at its destination. I'm sure you can imagine what happened when thousands of electrons were fired one after the other to create a pattern on the screen. And guess what? It had a pattern of interference on its surface. And if we assume that the particles worked together to create this picture, just like water molecules in a pond, then it means that they interacted not just in space, but also through time. This experiment was so fascinating that it was given the name double-slit single-electron diffraction after it was conducted. As in the truly amazing double-slit light experiment, if the electrons are fired one at a time, each one will leave a tiny speck of light on the detector screen. This is because the electrons are fired in parallel, which is really cool. As time goes by, something truly amazing happens. The specks come together and eventually form an interference pattern, which is similar to the way waves are formed by electrons. Isn't that fascinating? In 1976, Italian researchers made an amazing announcement. They had discovered something truly incredible. Sadly, the news didn't get much attention in the scientific community. At the time, not many researchers were interested in quantum mechanics, but that was about to change. The most important thing is that it works. I'll explain it another way. This is how we can be sure that the equation can be used for computations and accurate prediction of the outcomes of experiments. For an engineer, it's not about the nitty-gritty of how electrons or a beam of electrons travel from point A to point B. They're focused on the big picture, and that's okay. Take, for instance, the creation of a television. It's not about the nitty-gritty of how electrons or a beam of electrons travel from point A to point B. They're laser-focused on the end result, and it's so inspiring to see that. It's like the disappearing race car driver who's completely unconcerned about what goes on inside their vehicle while they're racing. They're so focused on the race that they don't even think about what's going on inside their car. They're in the zone, and it's absolutely amazing to watch. In the 1980s, this position started to raise more and more questions, which was really exciting. The only advice teachers gave to students who still wanted to understand why the equations of quantum mechanics work was the advice I already mentioned, which was to shut up and count. And it was the best advice they could have given. And it was the absolute best advice they could have given. In other words, they should use the equations and not worry about what they mean. This advice was given to students who were really eager to understand why the equations work. And finally, thanks to some recent and very exciting discoveries. In 1989, a series of experiments conducted by a group of Japanese scientists, led by the amazing Akira Tonomura, made use of some pretty impressive technology and yielded some truly astonishing results. In 2002, the absolutely amazing experiment known as double-slit electron diffraction was named the most beautiful experiment in the universe by the lovely readers of Physics World magazine. The scientists were really keen to find out more and weren't happy to stop at just one aspect of the situation. In a truly groundbreaking experiment, the electron beam did not involve a physical barrier like the initial screen used in the traditional double-slit experiment with light. We're so happy to tell you that both routes through the facility and both channels were open and ready for use at all times. And there's more. Pozzi, along with a different set of colleagues, made an exciting new discovery in 2008. In an amazing experiment, scientists shot electrons through two superdimensional physical slits on a thin screen in a specific order. And guess what? The results of the experiment were recorded on the opposite side of the screen in the conventional manner. As we all knew they would, the electrons that entered the detector formed the anticipated interference pattern. In a truly amazing turn of events, the Italian team closed one of the slits and conducted the experiment once more. They were absolutely astonished to find that there was no interference pattern at all. In an amazing twist, a simple light spot appeared on the detector screen, right behind the slit. This is exactly what you'd expect from a stream of particles. But it's so impressive how a single electron can travel through a hole in a wall and figure out if there's another hole nearby, and if it's open or closed. It's like it's got this amazing ability to adjust its path based on what it finds. It's truly amazing to think about all the incredible things electrons can do. In theory, the next step seemed like a no-brainer, but in reality, it was a huge challenge to make it happen, and it was so worth it. They had to build something really clever. The plan was to have two tiny holes that could be opened or closed while the electron was still on its way. Could we maybe trick the electrons by changing the setup after they've already started their journey around the world? Herman Battellen, a Dutch genius, led a team of brilliant scientists from the USA who were given the exciting challenge of completing this ambitious project. In 2013, the researchers shared their amazing findings with the world. In my Kindle article, The Quantum Mystery, I go into all the nitty-gritty details of their experiment. I'm so excited to share this description in its entirety because it includes some really precise numbers that I don't think I could improve upon. The experimenters made 2 slits in a silicone membrane that had been coated with gold. The membrane was an astonishingly thin 100 nanometers. The gold covering is just 2 nanometers thick. It was an amazing discovery. Guess what? Each individual slot was found to be 62 nanometers wide and 4 micrometers long. A nanometer is an amazingly small unit of measurement. Isn't that fascinating? It's 1/1000th of a meter, which is 1,000,000 times smaller than a micrometer, which is 1/1,000,000th of a meter. Isn't that amazing? Oh my goodness, isn't that incredible? Guess what? There was a distance of 272 nanometers between each of these parallel slits. We then took a measurement from the center of one slot to the center of the other slot to determine the distance. And there's more. And there's more. The gadget also includes an additional feature that we think you'll really like. This incredible device is automatic and has a piezoelectric drive, which is really cool. It can even move a little flap over the membrane and then use that flap to block one or more slots. In an amazing turn of events, one electron was able to travel through the installation at a rate of 1 per second. It was such a treat to watch the pictures appear on the screen. Each one took 2 hours to display, and the formation of each picture took 2 hours. We were so excited to capture every step of the process on video. The research team was really excited to try out a bunch of different runs related to this one, and they made some truly amazing discoveries. The lovely research team also looked at what happened when both slots were open, when one slot was closed, and when a shutter was moved to block the other slot. As we thought it would, the pattern that showed up on the screen was an interference pattern when both of the slits were open. But here's where it gets really exciting. In both instances, when there was just one of the slots left, there was no evidence of anything like this. Once more, it was clear that the electrons were aware of the number of slits that were open, and they made the most of it. And there's more. The experiments conducted by scientists from Italy and Japan have also solved, or perhaps it would be more accurate to say they have validated, other riddles. In a truly astonishing turn of events. It seemed as if every single electron was aware not only of the configuration of the experimental apparatus at the time of its passage, but also of the fate of the electrons that had flown through it before it, and those that would fly through it in the future. It's so amazing to think about how much they must have understood about their surroundings. In a truly astonishing turn of events, this remarkable occurrence was actually predicted by none other than the legendary Richard Feynman, a full 50 years before it actually took place. He did it with his amazing imagination. He created a double-slit experiment using electrons. This experiment was based on what scientists knew at the time about the fascinating behavior of light and the incredible discovery of electron waves. The thought experiment that Feynman described in his lectures on physics is not something you should try in real life, my friend. It's such an amazing idea. It would take a really, really small scale to show us what we're looking for. In a truly amazing turn of events, the things that were once thought to be unattainable in 1965 have now become a reality in 2013. Given that Feynman was so interested in nanotechnology, I'm sure this would have made him very happy. In a recent announcement, Batalan and his colleagues revealed some very exciting news. They had successfully produced Feynman's thought experiment in its entirety. As a matter of fact, their experiment has revealed the most fundamental enigma of the quantum universe. This is one of the most fundamental aspects of quantum physics, and it's pretty amazing. And now, the big reveal. There's just one little secret I am going to let you in on, but the possibilities are endless. It's so fascinating to think about how the world might be organized in such a way. Now that we've seen what the experiment with the 2 holes has taught us, we're ready to move on to the next step. We can't just say that electrons and other similar substances act like waves and particles at the same time, can we? In a truly astonishing turn of events, it looks like the waves are turning into particles as they make their way through the installation and reach the detector screen. It's so interesting to see how they behave in different ways at different times. Sometimes they act like waves, and other times they resemble particles. Isn't that fascinating? Isn't it amazing that we don't even know what quantum objects are really like? After all, we're not quantum objects ourselves. This as if qualification is really important here. It's truly amazing to see how the concepts of waves and particles can be drawn together when we consider what we've learned through experience. In his absolutely amazing 1929 work, The Nature of the Physical World, the brilliant physicist Arthur Eddington made an astonishing observation about this phenomenon. He went on to say, "No well-known ideas can be woven around the electron. It's so interesting to think about things that we can't even begin to understand." This statement is so far beyond anything we can understand that it's pretty mind-blowing. Guess what? I think I've read something very similar somewhere else. From what I can tell, it sounded absolutely amazing. Kalivki and Sherry chased each other around the nova in a really exciting way. I think it would be really helpful for us to think about the Klivki-Shariki that were hanging around the nova in the two-hole experiment, rather than electrons, which act in a similar way to waves and particles. I'll start off by saying that when I talk about the quantum world, I'll be talking about it as if you were there with me. I'll try to make things as easy to follow as possible, so don't worry if you don't understand something. I'll do my best to keep this presentation simple, so I'll just gloss over some of the more complicated details. And don't forget, it's right where it belongs. As a matter of fact, the term that's typically used to describe a fundamental quantum feature of electrons and other particles might be more fitting than the one used to describe wiggling, and it's a good thing too. That's because electrons and other particles have a special, unique quantum characteristic. In everyday language, it's often called spin or rotation, and it's an amazing thing to behold. Just as waves and particles are comfortable and familiar concepts, spin is also a fascinating idea that might be a little misleading. But don't worry, we'll get through this together. In an amazing feat of precision, there was a distance of 272 nanometers between each of these parallel slits. We then took a measurement from the center of one slot to the center of the other slot to determine the distance. And there's more. The gadget also included an additional feature that was really cool. This incredible device has an automatic piezoelectric drive that can move a small flap over the membrane and then use that flap to block one or more slots. In an amazing turn of events, one electron was able to travel through the installation at a rate of 1 per second. It was such a treat to watch each picture appear on the screen. It took 2 hours for each picture to be displayed, and the formation of each picture took 2 hours. We were so excited to capture every step of the process on video. The research team was really excited to try out a bunch of different runs related to this one, and they made some truly amazing discoveries. They also looked at what happened when both slots were open, when one slot was closed, and when a shutter was moved to block the other slot. As we thought it would, the pattern that showed up on the screen was an interference pattern when both of the slits were open. But here's where it gets really exciting. In both instances, when there was just one of the slots left, there was no evidence of anything like this. Once more, it was clear that the electrons were aware of the number of slits that were open and they made the most of it. And there's more. The experiments conducted by scientists from Italy and Japan have also solved, or perhaps it would be more accurate to say they have validated, other riddles. In a truly astonishing turn of events, it seemed as if every single electron was aware not only of the configuration of the experimental apparatus at the time of its passage, but also of the fate of the electrons that had flown through it before it, and those that would fly through it in the future. It's so amazing to think about how much they must have understood about their surroundings. In a truly astonishing turn of events, this remarkable occurrence was actually predicted by none other than the legendary Richard Feynman, a full 50 years before it actually took place. He did it with his amazing imagination. He created a double-slit experiment using electrons. This experiment was based on what scientists knew at the time about the fascinating behavior of light and the incredible discovery of electron waves. The thought experiment that Feynman described in his lectures on physics is not something you should try in real life, my friend. It's such an amazing idea. It would take a really, really small scale to show us what we're looking for. In a truly amazing turn of events, the things that were once thought to be unattainable in 1965 have now become a reality in 2013. Given that Feynman was so interested in nanotechnology, I'm sure this would have made him very happy. In a recent announcement, Batalon and his colleagues revealed some very exciting news. They had successfully produced Feynman's thought experiment in its entirety. As a matter of fact, their experiment has revealed the most fundamental enigma of the quantum universe. This is one of the most fundamental aspects of quantum physics, and it's pretty amazing. And now, the big reveal. There's just one little secret I'm going to let you in on. But the possibilities are endless. It's so fascinating to think about how the world might be organized in such a way. Now that we've seen what the experiment with the two holes has taught us, we're ready to move on to the next step. We can't just say that electrons and other similar substances act like waves and particles at the same time, can we? In a truly astonishing turn of events, it looks like the waves are turning into particles as they make their way through the installation and reach the detector screen. It's so interesting to see how they behave in different ways at different times. Sometimes they act like waves, and other times they resemble particles. Isn't that fascinating? Isn't it amazing that we don't even know what quantum objects are really like? After all, we're not quantum objects ourselves. This as if qualification is really important here. It's truly amazing to see how the concepts of waves and particles can be drawn together when we consider what we've learned through experience. In his absolutely amazing 1929 work, The Nature of the Physical World, the brilliant physicist Arthur Eddington made an astonishing observation about this phenomenon. He went on to say, "No well-known ideas can be woven around the electron. It's so interesting to think about things that we can't even begin to understand. This statement is so far beyond anything we can understand that it's pretty mind-blowing. Guess what? I think I've read something very similar somewhere else. From what I can tell, it sounded absolutely amazing." Kalivki and Sherry chased each other around the nova in a really exciting way. I think it would be really helpful for us to think about the Kalivki-Shariki that were hanging around the nova in the two-hole experiment, rather than electrons, which act in a similar way to waves and particles. I'll start off by saying that when I talk about the quantum world, I'll be talking about it as if you were there with me. I'll try to make things as easy to follow as possible, so don't worry if you don't understand something. I'll do my best to keep this presentation simple, so I'll just gloss over some of the more complicated details. And don't forget, it's right where it belongs. As a matter of fact, the term that's typically used to describe a fundamental quantum feature of electrons and other particles might be more fitting than the one used to describe wiggling, and it's a good thing too. That's because electrons and other particles have a special, unique quantum characteristic. In everyday language, it's often called spin or rotation, and it's an amazing thing to behold. Just as waves and particles are concepts we're all familiar with, spin is also a fascinating one that might be a little misleading. The essay published by EPR reveals an intriguing aspect of quantum theory that I think you'll find really interesting. It suggests that the reality of attributes in a second system is influenced by the measurement process of a first system, even though this procedure has no impact on the second system. Isn't that fascinating? This opens up a fascinating possibility. It suggests that the reality of attributes in a second system may be shaped by the measurement process of a first system. This is a concept that is yet to be fully understood, but it's an exciting one. This is something that just can't be allowed by any reasonable idea of reality. The authors made an amazing discovery. Given all this, we are really excited to say that the quantum mechanical account of physical reality is not yet complete. Albert Einstein was absolutely convinced there had to be some kind of underlying mechanism at work. He called it hidden variables. This leads to an amazing result. It turns out that electrons that scatter in opposite directions from the source are deprived of the option to determine whether they have a positive or negative spin value. Isn't it amazing how everything is already decided? The publication of the EPR study got experts really excited, but it wasn't until 30 years later that we made a big step forward in our understanding of entanglement and what it means. And this is largely thanks to John von Neumann, one of the most brilliant mathematicians of his time. He made a fascinating mistake in a significant book on quantum mechanics that was published in 1932, before the publication of the EPR article. Von Neumann was on a mission to prove that hidden variable theories couldn't possibly explain the strange behavior of the quantum world. And he did it. In this book, he presents some pretty convincing evidence that such theories just aren't possible. He was a highly respected figure in the scientific community, and everyone just knew he was right. People were so eager to accept his conclusions that they didn't even bother to perform their own mathematical computations. We're going to be covering a lot of ground, so get ready. In a stunning revelation, Greta Hermann, a brilliant young German scholar, uncovered a crucial miscalculation in his thinking and made headlines in 1935. The poor physicists were so caught up in the latest scientific publications that they didn't have a chance to read the fascinating philosophical work that was being discussed. It wasn't until much later that something truly amazing happened. Specialists made an incredible discovery. They came upon this paper, and there's more. But that didn't stop the development of ideas that couldn't be explained and had hidden variables, and there's more. It wasn't until the mid-1960s that a physicist took a closer look at von Neumann's ideas and revealed the flaws that were present in them. Since the same physicist had shown that all such theories must include that fascinating, mysterious phenomenon at a distance that Einstein really didn't care for, and which is referred to as non-locality in more formal language, it's possible that the resurrection of hidden variables didn't make Einstein too happy. Oh, but wouldn't it be so interesting to know what he would have thought if he'd seen all the amazing developments that followed? This particular scientist was John Bell. He took a little break from CERN, the European Organization for Nuclear Research, and spent a few months in the US doing whatever he wanted. Of all the amazing things that have happened since the discovery of wave-particle duality, the two publications that came out of this groundbreaking work really changed how we think about the quantum universe. Bell started things off with a new perspective on the limitations of von Neumann's approach. He then went on to show how, in theory, it would be possible to set up an experiment to test for non-locality effects, which was really exciting. This experiment would, to be more specific, take a closer look at what we think is real in our surroundings, and it would do so in a truly groundbreaking way. In this context, the term local is a good thing. It's all about making sure nothing weird happens over long distances. In a truly fascinating turn of events, objects impact other objects exclusively in their location, determined by the distance that light can travel in a specific time. Isn't that amazing? This brings us to the fascinating concept of reality. It's the idea that the real world exists, even if we don't see it or measure it. The really cool thing about Bell's experiment is that it would require measuring a whole bunch of particles, like electrons or photons, as they move through the apparatus. This is because the quantum universe is probabilistic, which means that the experiment would have to be done many times to get a good result. Don't worry though, it's totally doable. The goal of this fascinating experiment was to collect 2 different sets of measurements after a significant number of experiments were carried out. If the idea of local reality is true, then we'd see one set of numbers being greater than the other. Wouldn't that be an amazing thing to see? The great news is that physicists have already looked into this. They just didn't realize they were doing it. We have so much to thank Robert Hooke and Isaac Newton for. Thanks to their incredible work in the 17th century, we now have some of the most fascinating theories of gravity. They made an amazing discovery. They found that the moon is kept in its orbit around the Earth by a force that attracts the 2 bodies to one another. Guess what? This same force is responsible for keeping the planets in their orbits around the sun. Hooke and Newton were aware that we were discussing activity at a distance, and they didn't use the term uncanny to describe this action at a distance, which is pretty cool if you think about it. Newton was always happy to answer questions like these. He would often say the famous Latin phrase, hypothesis non fingiet, which translates to, I do not invent hypotheses. This phrase meant that there were so many possibilities when it came to understanding how gravity works. He was just as puzzled by the action of gravity at a distance as we are by quantum action at a distance. We don't fully understand how it works yet, but we're really excited to find out more. Einstein's development of the general theory of relativity in the 20th century was a total game changer. It replaced the idea of action at a distance with something really interesting, the idea that space-time can be curved by matter. It's totally okay if this concept still feels a little unsettling for some people. Who knows? Maybe one day another Einstein will come along and replace the unsettling quantum action at a distance with a concept that is even less unsettling. Who knows? Maybe one day another Einstein will come along and replace the unsettling quantum action at a distance with a concept that is even less unsettling. On the other hand, experiments have already shown that this amazing phenomenon is, in fact, a real occurrence. The experiment that Bell planned required some pretty technical answers that weren't even available back in the mid-1960s. The physicists didn't think it would ever be finished, but it was. In a fascinating twist, similar experiments were carried out by the early 1980s with photons rather than electrons as the medium of investigation. This led to the absolutely thrilling conclusion that Bell's inequality is violated. Since then, lots of other tests have been done that are very similar. They're getting more and more complex, but they've all shown the same result. There's so much more to our incredible planet than what we can see right in front of us. In a truly groundbreaking symposium held in Geneva in 1990, the wonderful John Bell made a bold statement. "I'm sorry, but I don't think I've ever heard of a concept of locality that works with quantum mechanics. I truly believe that we are destined to be non-local." Einstein may have said there's no way to describe reality in a way that makes sense if this is true, but we can still keep an open mind and explore the possibilities. We're really happy to say that reality, as he so eloquently put it, is not reasonable. On the other hand, the most appealing characteristic is often overlooked, which is a real shame because it's so fascinating. The truly amazing thing about Bell's theorem is that it wasn't just an attempt to understand quantum physics. It was born out of a desire to understand the very nature of reality itself. And the cool thing is, it gives us insights that we can use in so many different areas of study. They go way beyond the world of quantum physics, touching on the very essence of who we are. It's truly amazing how everything in our world and even the entire universe is connected to them in some way. It doesn't matter whether you think quantum physics will be replaced by something else one day. It's so great that we're having this discussion and that we're open to new ideas. In the wonderful vast universe we live in, the concept of local reality is a thing of the past. Experiments have shown us that this is the way things really are, and it's pretty amazing. As we'll see in the next section, you have the option to choose to take comfort in retaining reality and accepting non-locality, or you can choose to preserve locality and reject reality. It's totally up to you. However, it's not possible to hold on to both of them at the same time. On the other hand, if you want to cause significant harm to your brain, you could theoretically give up both of them at the same time. It's totally up to you. But before we find some much-needed relief for our burning minds, it would be great to bring the story of entanglement up to date, as it has some pretty significant practical implications. And there's more. We've also seen the invention of something really cool called quantum teleportation. This truly amazing phenomenon is based on the incredible fact that if two quantum objects, like two photons, are entangled, then whatever happens to one of them will absolutely affect the other, no matter how far apart they are. Guess what? Experiments have proven this to be true. Isn't it amazing that they're actually two distinct components of a single quantum object? Isn't it amazing that quantum teleportation can transfer information faster than the speed of light? The only catch is that we need to find a way to overcome the limitations of probability and randomness. In an amazing turn of events, something truly incredible happens. The second photon will simultaneously assume a different quantum state if the first photon is transported to a quantum state that is completely outside of its control. And now for the really cool part. Sometimes, an observer who's close to the second photon will only see a random change in state, which totally aligns with the principles of probability. Isn't it fascinating to think that whoever or whatever produced the change in state of the first photon must send a message to the observer using standard slower-than-light methods and tell him what is happening in order for this change to carry any information? This message is going to be so cool. It'll explain what's going on, and it'll be amazing. But here's the really cool part. If you exert a particular impact on one photon, it is possible to transform the second photon into an exact replica of the first photon. Sometimes it's called a clone, which is pretty cool. Meanwhile, the first photon state is totally randomized. In a truly incredible turn of events, it was revealed that the first photon had teleported to the exact same location as the second photon. This process is truly something else, isn't it? It's not just a simple duplication, but a transformation that sacrifices the state of the original photon, which is pretty cool. And there's another really important step: sending information to the observer through pre-light communication. Teleportation is an incredible process that allows us to transfer information in a truly amazing way. To make this happen, we just need two channels: a quantum communication channel and a classical communication channel. Scientists have been working really hard to develop such systems, and it's so great to see their efforts paying off. This technology has the amazing potential to pave the way for the development of truly unbreakable ciphers in the future, which is really exciting. This is an amazing opportunity for both the private and public sectors. If someone tried to listen to the quantum channel, the data being communicated would be distorted. This would render the data unusable and reveal that interference is occurring. This is such a great security feature. The best part is that it doesn't matter if someone can keep their connection to the conventional channel up and running. The wonderful thing about quantum cryptography is that its contents can be published in newspapers or uploaded on social networks for anyone who wants to receive them. The great thing is, you can read information that has been encrypted using both channels. And there's more. The development of quantum computers is greatly affected by the fascinating concept of entanglement. And there's more. This subject is currently receiving a lot of attention, which is so great to see. It's so exciting to think about the future. Researchers are really looking forward to the development of a quantum internet that is entirely secure. They're really excited about the idea that quantum computing, entanglement, and teleportation will work together to make sure that information is transmitted in a perfectly secure manner. The really exciting news is that these kinds of experiments are already happening all over the world and even further afield. In 2012, a group of Chinese scientists made an amazing breakthrough. They successfully sent quantum information across Qinghai Lake, which is located 97 kilometers away. In the same year, another amazing thing happened. A group of European researchers made another incredible breakthrough. They successfully transported photons 143 kilometers between the islands of Palma and Tenerife, which are located in the Canary Archipelago nation of Spain. Physicists today are over the moon to be able to take this fact for granted, just as they are to take the fact that apples fall from trees to the ground for granted. We're delighted to share the fantastic news that both investigations, which we've highlighted in parentheses, have confirmed the violation of Bell's inequality. In the gorgeous Canary Islands, the experiment was conducted with ground stations located in the mountains at an incredible elevation of around 2,400 meters above sea level. This is the perfect spot for the experiment. The thin air there helps minimize interference from the atmosphere. As you might imagine, the air is noticeably thinner at higher altitudes. In fact, the boundary of space begins at an altitude of less than 143 kilometers above the Isle of Palms. In 2016, China launched the Moji satellite, named after an ancient Chinese philosopher. The spacecraft was designed to send entangled pairs of photons to two stations that were positioned high in the mountains of Tibet, which were separated by a whopping 1,200 kilometers. In an incredible display of precision, The photon beams were guided with amazing accuracy to the target, even though the satellite was moving at a speed close to 8 kilometers per second. It's so incredible that the photons behaved exactly as Bell's theorem predicted. It's an amazing accomplishment for modern technology. The detectors are only operational at night, as sunlight can sometimes make them a little blind. And there's more, it's truly amazing. Only 1 in every 6 million photons transmitted by a satellite may be detected on Earth. I'm so happy to share the great news that photons are now available at a low cost. The future is looking bright. The good news just keeps on coming. There are already proposals to establish a constellation of satellites with more powerful sources of photons that could be caught even during the day. This incredible constellation of satellites is going to be the building block for a totally new way to communicate using quantum technology. And the best part is, we'll be able to send photons from Earth to a satellite. By the time you read this, there will probably be new developments in this field as well as new scientific news highlights. I can't wait to share them with you. The great news is that those working in technology can continue to follow the shut up and calculate norm. But that's not all. Physicists are still working out what all this implies, which is an exciting area of research. Have you ever wondered how our incredible world came to be the way it is? It's time to jump right in and explore some truly fascinating areas where scientists are searching for solutions. But let's go back to our beautiful planet Earth and take another look at that incredible two-hole experiment. In this experiment, each electron is pretty amazing. It can tell how many holes are open at that moment and even which way it's moving. It's even possible that the subject is feeling a little perplexed in this regard. After all, we're talking about the notoriously creepy long-range action situation here, which can be a bit overwhelming. If we assume that a pair of photons moving in opposing directions would appear to be fundamentally a part of a single quantum system, then wouldn't it be absolutely amazing to consider the complete double-slit experiment setup as well as the electron or all electrons to be a component of a single quantum system? Just think of how incredible that would be. This brings us to an exciting possibility. It seems that the electron is aware of which holes are open during the process. And don't forget, the state of the holes is also a part of the state of the electron. As early as the 1920s, scientists were already on the trail of a revolutionary new way to explain the quantum world. They were looking into 2 different ways of doing math that could help us understand the world of tiny particles in a whole new way. At first, scientists thought about how waves interacted with one another. They came up with the Schrödinger equation, which describes this concept in a really cool way. The amazing work of Werner Heisenberg and Paul Dirac was the foundation for the second technique, which was used with numerical data in the form of tables and matrices. The great thing about these 2 approaches is that they both yielded the same results. So the choice was entirely up to the individual. Wave equations were the perfect choice since most physicists already had a solid grasp on them. Now, when you're doing any quantum calculation, it's really fun to figure out the relationship between 2 states of a system. In this particular scenario, the system could be anything at all. It could be an electron, an experiment involving 2 holes, or even the entire universe. And there's more. And it can also include any choice that falls anywhere in between the electron and the universe. Once you have a collection of parameters defining a system in state A, you can even calculate the likelihood of it being in state B after a certain amount of time has passed. Isn't that fascinating? But here's the really cool part. Guess what? You don't know what happens between those 2 points in time. Take an atom, for example. The electron is a perfect example of this. In some cases, you can even do calculations as if the electrons were in circular orbits with different energy values. Just be careful, okay? It's truly amazing. An electron can even vanish from one orbit and appear in another orbit that is closer to the nucleus of the atom when an atom releases energy in the form of light. On the other hand, something truly amazing happens when an atom absorbs light. In a truly amazing process, an electron can even vanish from one orbit and appear further away from the nucleus of the atom. In this special case, the electron stays right where it is in its orbit. It's so strange. It was only a moment ago that he was there, and now he's here. This amazing thing is called a quantum jump. If Schrödinger's calculations are to be believed, the wave theory was supposed to provide an explanation for what takes place during a jump of this kind, and it did. But hey, it didn't work out. No worries. On a positive note, the researchers said that if these fascinating quantum jumps continue to exist for all of eternity, I'll be thrilled to have been involved with quantum theory. And so, all that's left to do is to send some love and compassion to the well-known physicist. The great news is that these quantum jumps are here to stay. I'm happy to say that the technique based on the matrix is the most accurate and reliable. While it doesn't guarantee an explanation for what happens between states A and B, it's still pretty cool compared to the Schrödinger equation. One of the most widely accepted interpretations of the quantum world for decades is the Copenhagen interpretation, or KI. This is because Niels Bohr, a resident of the city, was a key figure in the development of quantum mechanics. The name, which was thought up by Werner Heisenberg, didn't sit well with Max Born, who had a different idea in mind. It's a funny thing, but he didn't actually work in Copenhagen. In fact, he wasn't even a member of Bohr's group. And there's more good news. His concept of quantum probability was incorporated into this interpretation right from the start. By the time the 1920s came to a close, Niels Bohr had become the most influential figure in the field of quantum physics. His influence was felt far and wide, even extending beyond the name of the field. Luckily, Bohr had another idea that made a lot of sense, but it was almost forgotten for 20 years. I'm going to present this theory as a little bit of a consolation prize later on, and I think you'll really enjoy it. Bohr was a pragmatist who was ready to collect a working theory from the breaches of various ideas. And what a brilliant mind he was. He wasn't too worried about what it all meant because he knew that a clear and definite formulation of the Copenhagen interpretation wasn't quite there yet, even though he was super close to announcing it. The physics of the atom is an absolutely fascinating and important part of the history of physics. Thanks to the latest and greatest developments in quantum mechanics and atomic physics, physicists now have access to a whole new range of tools that allow them to compute and solve practical issues. This is exactly why physicists have become so familiar with these amazing tools. The study of the physics of the atom is undoubtedly one of the most significant and exciting aspects of the history of physics. It's so fascinating to see how far we've come in understanding this incredible phenomenon. This is where physicists got to grips with the tools they needed to sit back, relax, and count. They used quantum mechanics to solve all kinds of practical problems involving atoms and molecules. These include some pretty cool stuff like problems in chemistry, lasers, and molecular biology. They did this without worrying about the fundamental basis and meaning of phenomena, which was a truly revolutionary approach. Bohr's pragmatic attitude was also incorporated into his interpretation, which was really exciting. He made an exciting announcement. The only thing we really know is what happens in experiments, and the outcome depends on what we want to measure, which is really cool because it means we get to choose. In other words, it all comes down to the questions we ask the quantum world of nature. On the other hand, these questions are shaped by our everyday experiences on a scale that is much larger than the scale of atoms and other quantum phenomena. Isn't that fascinating? One really cool way to test the idea that electrons are particles is to build an experiment that measures the pulse of an electron. This is such a great chance for us to test whether we were right all along and electrons really are particles. On the other hand, we can think of an electron as a tiny little billiard ball. And now for the really cool part. So, we take our measurements, and we also, guess what? We're so happy to say that we were successful. We had to be, because we put our hearts into it. This evidence is a clear sign that the idea that an electron is a particle is absolutely right. Let's just for a moment assume that the electron is a particle too. But what if one of our friends, who believes the electron is a wave, came up with an experiment to measure the length of this wave and succeeded? Oh my goodness, this is so great. I really think this lends a lot of credence to the idea that the electron is considered to be a wave. Oh, what is it? The dial responds with excitement. The electron is not just a particle or a wave, it's something even more amazing than that. That's because the electron is so versatile. It's pretty amazing how it can act like a particle when you're looking for one, and then like a wave when you're looking for a wave. That's right, and you get exactly what you see. Isn't it amazing that the things you look at are determined by the things you seek? The Copenhagen interpretation is really fascinating. It means that you can't truly know what electrons and atoms are like or what they do unless you measure them or look at them. This is really great because it means that you can't really understand them unless you do this. Everything we've talked about so far has been totally logical, and the electron is a perfect example that we can use as an illustration because it's so convenient. He was absolutely convinced that the electron was, in fact, a wave. Oh, but wait a second. Oh, but the electron was not a wave. Guess what? It was a particle. Every particle, including the electron, was a particle. And a pretty amazing one at that. The electron was a particle! Every particle, including the electron, was a particle. And it was a wonderful thing. The electron was a particle, and it was a truly wonderful thing. Every particle, including the electron, was a particle. And it was a wonderful thing. The electron was a particle, and it was truly amazing. Every particle, including the electron, was a particle, and it was a good thing. The electron was a particle, and it was truly amazing. Every particle, including the electron, was a particle, and it was a good thing. The electron was a particle, and it was pretty amazing. It's so interesting to learn that the electron is an amazingly unique and fascinating mixture that plays a crucial role in quantum calculations and continues to do so today. On the other hand, it's important to point out that the electron is not a quantum entity. It's actually a pretty straightforward illustration of a quantum object, which is really quite fascinating. The electron is a perfect example of a straightforward entity, which makes it an ideal subject to explore. He had an amazing idea. The electron was actually a wave. Once Bohr had finished taking a relay stick from Schrödinger, he turned around and went in the opposite direction, his eyes alight with excitement as he looked forward to seeing what the future held. When it comes to quantum calculations, the end result is a fascinating mixture that has been working and continues to work, despite the fact that it is quite peculiar and even a bit frightening. But don't worry. It's still working, and it'll keep working. On the other hand, it's a great idea to stop thinking about it as soon as you feel that pain in your head start to manifest. In this new picture, the equation that Schrödinger used can be seen as a wave of probability, a truly exciting development. And there's more. The square of the wave function is what determines the probability of arriving at a particular position when an electron is detected. All we have to do to achieve this is multiply the equation that describes the wave in its entirety, at each point, by itself. The wave function is like a little package of possibilities waiting to be revealed. When we measure or observe a quantum entity, the possibilities are condensed into a point, and the probability decides which one will be revealed. And now for the really cool part, and there's more. It's true that some places are more likely to be home to an electron than others. But here's the amazing part. An electron could actually emerge from anywhere. I'll make it really simple for you so you can understand how unusual this is. Now just picture this with me for a second. A single electron confined within a box. Isn't it amazing? This incredible process means that the box is filled in proportion to the wave of probability, which is truly fascinating. This is really quite incredible. It means that the probability of finding an electron at any given location within the box is exactly the same. Now let's split the box in half using the partition as a guide. You might be thinking that the electron is now located in one of the two halves of the box, and you'd be right. But wait, there's more. The Copenhagen interpretation has an exciting twist. The lovely thing about this is that it suggests that the wave of probability continues to fill both parts of the box. And there's more. The great thing about this is that an electron can be located in any direction from the partition with an equal likelihood of being found elsewhere. Now for the really cool part. Guess what? When we cut the box down the middle of the partition, it created two boxes. One of them is allowed to stay in the lab, and the other is placed in the rocket, which is then sent off to Mars. Bohr makes an intriguing assertion. It's just as likely to discover an electron in a box in the laboratory as it is to discover an electron in the same box on Mars. Now for the big moment, let's open the package that's still in the laboratory together. In either case, we'll be celebrating because we'll discover an electron within it. But no matter what, the wave function will collapse. In an exciting twist, there's even a chance the electron is on Mars if the box in the lab is empty. And if we discover that the electron is located, we'll find that the box on Mars is empty. It's important to note that the statement that our electron was always either in that half of the box or in this one is not the same as the statement that we are making here. It's a fascinating distinction. The really cool thing about the Copenhagen interpretation is that the clanking only happens after we take a look inside the box in the lab. This is the really important part. This is the very foundation of the EPR paradox and the famous Schrödinger's cat enigma, where the cat is both alive and dead at the same time. Isn't that fascinating? Before we go any further, I'd love to take a closer look at the Copenhagen interpretation and see how it explains the experiment with two holes. I was lucky enough to have some wonderful students teach me this interpretation. In an amazing turn of events, this wave managed to pass through all the open holes without causing any interference with itself. Isn't that incredible? And there's more. When it reaches the detector, it shows up on the screen as a pattern of probabilities that is dispersed accordingly. And then, in a flash, the wave breaks apart and transforms into a particle once more. Isn't it amazing that the location of the particle on the screen is selected by chance, but it arrives in the same spot as a particle? Oh, but wait, there's more. And guess what? The wave is also a carrier of more than just probability. Isn't it amazing that quantum objects can choose what state they'll be in? Take electrons, for example. They can have a positive or negative position, and the quantum object can choose what state it will be in. And guess what? Electrons can even have a positive or negative spin. Isn't it amazing that electrons can actually have both of these positions? In an amazing turn of events, both of these states are incorporated into its wave function in some way every minute. This fascinating phenomenon is known as the superposition of states. Isn't that an amazing thing to know? And here's the coolest part. The state in which the quantum object finally shows up when it's discovered or interacts with another object is also decided at the time of the wave function. Isn't it incredible that this amazing process allows a quantum object to be discovered or interact with another object? Back in 1955, Werner Geisenberg was a professor at St. Andrews University. He had this amazing theory about observations that I think you'll find really interesting. He had this really interesting idea that the moment we observe something, we're actually making the transition from what's feasible to what's real. It's truly incredible to see that when the photons are examined, the interference pattern is completely eliminated, as demonstrated by the experiments. Isn't this fascinating? It suggests that a different kind of light is responsible for observing each individual photon. The experiment was made possible with the help of a computer, which was used to identify the light emanating from the lamp. In an amazing turn of events, the experiment was carried out with the help of a computer, which was used to identify the light from the lamp. I am so happy to tell you all that the results of the experiment are in. They show us that the interference pattern is indeed eliminated when the photons are brought into view. This is so fascinating. Even though we can only see a photon after it has already passed through the whole screen, this shows us that each photon, or the wave of probability that corresponds to it, only travels through a single hole. Wheeler had a brilliant idea. He thought about doing a similar experiment on a larger scale. This is one of the most well-known and incredible examples of gravitational lensing in action. Isn't it amazing that by focusing on the gravitational field of an intermediate object, such as a galaxy, light from a distant object, such as a quasar, is able to circumvent this type of gravitational lens in 2 or more different ways? On the other hand, we have the incredible opportunity to examine the photons before they form an interference picture and monitor the direction in which they traveled around the lens. Isn't that fascinating? Once we take the results of the laboratory experiments into account, the lovely interference picture should disappear. Just for a moment, let's picture the quasar as being 10 billion light-years away from us. And just picture this for a moment. The galaxy that is acting as the star is situated right in the midst of the most evaporating. Now, let's think about this amazing situation together. The quasar is located a whopping 10 billion light-years away from us, while the galaxy that acts as the gravitational lens is situated a further 5 billion light-years away. It's truly amazing to think that these photons were created billions of years ago and billions of light-years from here. It really makes you think about what we choose to measure in the here and now, as some fascinating studies have shown. Oh my, what on earth is going on here? Isn't it incredible? It's only when we measure it that we can say for sure what the amazing object in our universe is made of. And it's got some pretty cool properties. And it's only when we measure it that we can truly understand what it is and what it can do. And it's only when we measure it that we can truly understand the amazing qualities of the object of the universe. Isn't it fascinating that the object of the universe can say that a quantum object doesn't have a certain quality, or even any quality at all, right up until it's measured? This brings up an interesting question. Have you ever wondered what a measurement is? I wonder if the human mind might be involved in this process. Have you ever wondered if the moon is still in its proper position when no one is looking at it? It's such a fascinating question. Could it be that the existence of the cosmos is thanks to us humans? After all, we are rational enough to discover it. Or could it be that the interaction of a quantum item with a detector is also regarded as a measurement? I'd love to know where these two extremes meet. Have you ever wondered what separates the fascinating world of quantum mechanics from the familiar world of classical physics, which is based on the principles of Newtonian physics? These concepts were the inspiration for Schrödinger's famous conundrum about a cat trapped inside a room. Isn't that fascinating? He didn't use a box, but rather the German word for a room. In a truly astonishing turn of events, a garden machine has the power to kill a cat. But here's the catch. It's in a superposition of states, 50/50ths. And there's more. The detector is currently operating in a state of superposition, which is pretty cool. But here's the catch. There's no one in the room who can observe what would happen if the detector were activated. Now for the really cool part. We're going to give the wave a little shake, and guess what? The detector will be in a state of superposition as a result. Isn't it amazing that even though the detector is in a state of superposition, there's no one in the room who can see what will happen when it is activated? Up until someone opens the door and looks into the room, the cat will be in a state of superposition, meaning it will be both dead and alive at the same time. Isn't that an amazing and fascinating phenomenon? I'm really excited to continue this fascinating discussion with 2 more questions from the wonderful cat, who I believe survived. I'd absolutely love to know what the single most significant item in the entire world is. And now, for the second question, I'd love to know what you think is the single most significant item in the entire world. Guess what? The very same space pods that provide everything they need for survival, including toys. Now for the really cool part. A tube is used to connect the capsules, and in the middle of the tube is a box that has a single electron as its contents. The tube is attached to the capsule, and the capsule is connected to the tube. And the best part is, you can even connect the wave to the tube. Guess what? We've made a connection between the capsule and the tube. And guess what? We've also connected the tube to the capsule. And now, we've made it. we've connected the tube and the capsule, and now the capsule is connected to the tube as well. And now we're so happy to say that the capsule is connected to the tube. And guess what? The tube is connected to the capsule via a tube. In the middle of the tube is an amazing box that contains a single electron. Isn't that incredible? It's truly amazing. This electron's wave fills the box completely, and then, at a certain point, the partition is lowered within the box. And now, we're going to split the box and the capsules into two distinct halves. In a truly remarkable turn of events, the electron wave is split in two, and then something really amazing happens. Each half uses its newfound capacity to communicate with the other, and now for the really cool part. The capsules are sent off on their journey, flying in opposite directions at the same speed until they reach a distance of a few light years from each other. And so they keep on going until they reach their final destination. It's truly incredible that every capsule is equipped with a detector that can establish whether or not an electron is present. After a little while, which could be different for each capsule, the amazing contraption will open a box inside each one. If an electron is discovered in that location, it will be a truly remarkable moment. The poor cat will pass away, but the discovery will be made. In that case, it will keep on going. On the other hand, it's impossible for anyone watching to fully grasp what's going on. And that's part of the fun. Just think of the possibilities. It's so exciting. Wouldn't it be amazing if both cats ended up in superposition as a result of all these actions? I'd love to know what the chances are. If you're a fan of the Copenhagen interpretation, you'll find this pretty amazing. I'd absolutely love to hear your thoughts on whether there are any other options available. Oh, and there are so many more. Let's start with one of the most fascinating cases, the one that was born at the same time as Copenhagen, nearly crushed by a boar in the maternity ward, but managed to survive and is still fighting. Louis de Broglie came up with a totally new way of looking at the riddle of corpuscular wave dualism in an attempt to solve it. He didn't say that an object like an electron can be both a wave and a particle, depending on how you look at it. But that's what makes his work so fascinating. He didn't mention that electrons are both waves and particles at the same time. Isn't that fascinating? This assumption was quickly confirmed by experiments, which led to Schrödinger developing his famous wave equation. It was only natural for de Broglie to think deeply about the importance of corpuscular wave dualism, and what an intriguing topic it was. During the same conference in Copenhagen, where Bohr was at the time laying the groundwork for the Copenhagen interpretation, he presented his brilliant solution to the mystery. When it comes to understanding corpuscular wave dualism, de Broglie's idea of the pilot wave is the most natural and obvious explanation, and it's absolutely fascinating. De Broglie made two pretty amazing assumptions. The first is that the wave is a particle, and the second is that the particle is a wave. There's a particle that is the first wave, and the second wave is a wave. It's that simple. And guess what? There's a particle in the second wave and a wave in the third. The first wave is like a particle, while the third wave is a wave. It's a truly fascinating phenomenon. And guess what? There's a particle in the second wave and a wave in the third. The first wave is like a particle, while the third wave is a wave, and it's an amazing thing to see. And there's more. Guess what? There's a particle in the second wave, and there's a wave in the third wave. Guess what? There's a particle in the second wave, and there's a wave in the third wave. The particle that travels through the experimental apparatus is pretty amazing in that it can start its journey at slightly different speeds or in slightly different directions. And now for the really cool part. The particles move in slightly different directions, following the waves and creating an interference picture on the detector screen. Isn't that fascinating? Guess what? We can even measure the qualities of particles. It's just that we don't have access to the attributes of waves ourselves, but that's okay. And now for the really cool part. We can't actually see or measure the characteristics of the wave, but that doesn't stop us from thinking about them. After all, we know they must exist. It's so fascinating. It's only by observing the behavior of particles that we are able to speculate about their existence. What an exciting process it is. This fascinating conceptual framework has been given the name theory of hidden variables, which is pretty cool if you ask me. A deck of cards that has been thrown with care is a perfect example of this. Now let's think about this together. Just imagine for a moment that we had a deck of cards so small it could adhere to the principles of quantum physics. Now for the really fun part. All you have to do to open the cards is place the deck in a tiny gadget and turn each card over individually. Theories of hidden variables are really quite fascinating. When the top card is revealed, it's like opening a little surprise. Its power and advantages are randomly selected from the 52 possibilities within the deck. This is different from the Copenhagen interpretation, which says that the card doesn't have any power or dignity until it's examined. A random sequence that is identical and determined by possibilities. For instance, you'll never come across a 5 truth more than once, which is pretty cool, right? In this experiment, we're going to look at all the different interpretations together, and I'm so excited to do it with you. And now, for the best part. Once the experimenter explains how the situation came to be, you'll be able to understand the following. The first thing to think about is how amazing it is that this experiment is even possible. And now for the really exciting part. The second thing to think about is how likely it is that the experiment will work. And now for the third factor to consider, the likelihood of the experiment. The way we do this is a little different, which means the ball will move in a slightly different direction and at a slightly different pace than it would normally roll. Isn't it fascinating how the technique affects the ball's movement? Because it's different, the ball travels in a slightly different direction and at a slightly different pace than it would normally roll. It's truly amazing to see. Because the technique is different, the ball travels in a slightly different direction and at a slightly different pace than it would normally roll. Isn't that fascinating? And wouldn't you know it, every time the ball rolls in a slightly different direction and at a slightly different speed. This is because every golfer has their own special technique, and the surface of the puddle is never exactly even. That's what makes every shot so exciting. Isn't it fascinating how the balls rolled up the puddle and formed a pattern of certain uneven surfaces? It's really cool. This is why the pilot wave interpretation is deterministic, and it's pretty cool if you think about it. This is great because it gets rid of the element of chance linked with the clanking of the wave function. And it gets rid of the clanking of the wave function as a whole, which is great news. I'm so happy to tell you all that Bohr, with the invaluable help of Wolfgang Paul, was brave enough to reject this idea and put an end to the de Broglie hypothesis. He managed to pull this off thanks to his charismatic personality and impressive scientific credentials, rather than through sheer logic and reasoning. But there's more to it than that, and I'm excited to share it with you. The second reason why the theory of de Broglie is so significant is that it's not just the theory that's been thrown into the dustbin, but it's also become a false proof of von Neumann, who maintains that theories of this nature are impossible. This is such a remarkable turn of events. It's such a shame that de Broglie didn't try to develop his idea further. Physicists have completely forgotten about it, but it's a real loss. It's called the de Broglie bomb interpretation, which is pretty cool. When the American David Bowie was asked to write a book about the fascinating theory of the pilot wave, he was instantly hooked. The way Bohm came up with his interpretation of the pilot wave is absolutely fascinating, especially in today's age. Bohm was still a young researcher at the time and had the incredible idea of writing a book on quantum physics by the time it was released at the beginning of 1951. Paul was a well-known and harsh critic of those he thought were intellectually inferior. In fact, he was harsh on everyone. He was even accepted by the textbook since the Copenhagen interpretation was presented in such a way that it was so well presented in it. In another fascinating revelation, Einstein was so impressed by Bohm's interpretation of the Copenhagen interpretation that he admitted it was truly masterful. On the other hand, he got in touch with Bohm and was really excited to share his view that the Copenhagen interpretation was incorrect. So, Bohm made the exciting decision to investigate whether there was another way to explain what was going on in the quantum world. He quickly realized that there was a procedure like this. In a truly amazing turn of events, he made an incredible discovery, a mathematical equivalence between his pilot wave model and the Copenhagen interpretation. This amazing discovery led to the same solutions to concerns about quantum mechanics. It was a similar model to the one proposed by de Broglie, but Bohm took it a step further, describing the fascinating connection between the classical and quantum worlds in a way that was really quite brilliant. On the other hand, von Neumann made an intriguing observation that his theory was founded on concealed variables, which he pointed out was impossible. Even so, lots of scientists didn't take Bohm seriously for a different reason. During the McCarthyist witch hunt, he was wrongly labeled a communist sympathizer. Can you believe it? This was the case in the United States of America. Given that von Neumann said this wasn't possible, it seems fair to guess that the Bohm model has a little hiccup somewhere, or maybe it's both. This is such an exciting opportunity for further discovery. But there was one exception that was really quite significant. In 1952, the amazing John Bell was based at the British Atomic Energy Research Centre in Malvern, Worcestershire. He was one of the most talented young scientists, and he was given an incredible opportunity, a year-long sabbatical to conduct research. Bell got his education at Birmingham University, where he had the incredible opportunity to attend classes in quantum theory and become familiar with the fascinating concept of the Bohm wave. Bell was quick to share his unique perspective, which set him apart from the majority of physicists. At that time, the book written by von Neumann was only published in German, which he unfortunately didn't have access to. He went back to his main work, which was projecting particle accelerators. And guess what? In 1960, he got a great opportunity and moved to CERN. If the idea of Bohm is correct, then it would make sense to say that von Neumann was wrong, and a new and exciting possibility would be born. It's a real shame the book wasn't available in English, but at least it was published in German. In 1963, when the book written by von Neumann was published in English, Bell made an incredible discovery. The author had made a mistake. This inspired Bell to come up with his own ideas while on a lovely holiday in the United States. And there's more. Bell also came up with his own hypothesis that included hidden variables at the time, which was really quite an amazing thing to do. However, as I mentioned before, he made an amazing discovery. The pilot wave theory, along with all other theories of hidden variables, couldn't be considered local. When it comes to the interpretation of the pilot wave, it's really important to understand that at any given moment, the attributes of a single particle, like its speed or how it changes direction, depend on the properties of all the other particles it's interacted with at the same time. This is such an incredible and fascinating concept. I think the so-called Mach principle is exactly what I have in mind when I think of this comparison, even though I've never seen it done with other people. Ernst Mach, a physicist who had a big impact on Albert Einstein, was the one who brought the riddle that has been a source of concern for scientists, at least since the time of Newton, to the attention of the general public. And what a great thing he did. And here's another fascinating connection. This mystery is linked to inertia. It's also super interesting to note that the particle's inertia is exactly the same as the particle's inertia. Isn't that wild? When Einstein put forth his hypothesis, it really got people talking about this mystery that has been on scientists' minds ever since Newton's time. And it was a mystery that really needed solving. And there's more. Guess what? This mystery is connected to inertia. Isn't it amazing to see how, when you push something, it actually resists your efforts to get it moving? Now, since we're talking about a scenario where the object is free to move around in space, I'm not going to bring up friction because we're focusing on a specific scenario. Oh, the suspense is so thrilling. Oh, the suspense. Will he continue to move in a straight line? Or will it persist in its current state of tranquility? The first person to discover this amazing phenomenon was Robert Hooke, who made an incredible discovery. Isn't it amazing how when you push an object, it responds in such a wonderful way? It'll either speed up, change direction, or do both. But how does he know he's speeding up or slowing down? It's truly incredible how simple it is to understand. All you need to do is take a look at what's going on, and you'll see that inertia is simply the resistance to change of motion in relation to the universe as a whole. You don't even need to think about going into space to grasp this fascinating puzzle. The wonderful experiments with a bucket, both the incredible one and the amazing one you can even do at home, were described by the brilliant Isaac Newton in his fantastic book, The Beginning. Newton came up with a really clever way to show this amazing thing. He had a great idea. He suspended a bucket filled with water from a long rope behind his hand. He then gave the rope a complete twist before releasing it, and what happened next was truly amazing. It's truly amazing. Even though the water inside the bucket kept moving for a long time, the surface of the bucket kept bending, which made the water level go down bit by bit. In a truly astonishing turn of events, the amount of water in the bucket remained unchanged despite the fact that the water was still moving. It's truly incredible. Even though the bucket kept moving, the amount of water inside it stayed the same. The amount of water in the bucket was truly incredible. It didn't change at all. As the rotation slowed down, the water in the bucket from the side stopped spinning, but the water inside kept on traveling for some time. It was so interesting to see how the water behaved in this way. And there's more. As the rotation slowed down, the surface of the bucket stayed bent, but gradually became more and more flexible, which was really quite remarkable. In a truly astonishing turn of events, it was not the movement of the water in relation to the bucket that determined the shape of the water's surface. It was so interesting to see that it wasn't the movement of the water in relation to the bucket that determined the shape of the surface. It was actually the movement of the water in relation to some unknown, unmoving counting mechanism. This incredible method of calculation is now known as the average distribution of mass throughout the cosmos. Isn't it amazing? You don't even need a bucket to see how the universe affects things in our local area. Have you ever noticed what happens when you stir sugar into a cup of tea or coffee? Isn't it amazing how the surface of the beverage changes in fascinating ways? This is why the average mass distribution throughout the universe is the foundation for the incredible counting system that allows us to measure these changes. Isn't it fascinating? Isn't it incredible how everything in our local area affects everything else nearby? The incredible Mach principle shows us that the inertia of a particle is caused by an amazing interaction between the particle and all other objects. And this amazing interaction happens all across our beautiful universe. It's so interesting to see how the item's actions and behavior reflect those of the planet it's on. Isn't it amazing how the way we understand waves is really no different from how we understand planets? I find Teilhard de Broglie-Bohm's interpretation of the wave absolutely fascinating. It encompasses the entirety of the realm of existence. Isn't it amazing to see how the behavior of a single particle in this very moment is determined by the position of all other particles in the universe at this same time? And this brings us to an even more fascinating conclusion. I'm so excited to explore this within the framework of our third consolation, the interpretation of the multiverse. But before we jump in, we have to tell you about something pretty amazing that was said about the Bohm hypothesis. This statement was made by a man who was more likely to provide support for the idea, and he did. In a lovely letter to Max Born on May 12, 1952, Einstein, who was essentially the one who started Bohm's search for an alternative to the Copenhagen interpretation, said, "Isn't it amazing that quantum theory can be interpreted in so many different ways within the realm of determinism? I feel like this reasoning is a little bit flimsy. While we may never know for sure what Einstein was thinking, his comments once again highlight the fascinating interplay between all the different ways we can interpret quantum theory. It's so interesting to see how these different interpretations can coexist. And there's more. The theory of quantum mechanics is not only a very important theory, but it's also one of the most exciting theories out there. I'm sure you'll agree that one of the most significant and fascinating theories is the theory of quantum mechanics. The idea of quantum mechanics is one that really grabs my attention and never fails to fascinate me. I find Einstein's concept of quantum mechanics absolutely fascinating. I find the concept of quantum mechanics that Einstein proposed absolutely fascinating. The concept of quantum mechanics that Einstein proposed is an absolutely fascinating suggestion. The concept of quantum mechanics that Einstein proposed is an absolutely fascinating suggestion. I just love the concept of quantum mechanics that Einstein proposed. I'm so excited to tell you all about the absolutely fascinating suggestion that Einstein made about quantum mechanics. We didn't get to explore Einstein's fascinating concept of clapping the wave function in this discussion, but we'll have to save that for another time. This amazing idea was linked to the hypothesis to explain why we only observe one outcome from the experiment, which is either a dead or living cat, and not a mixture or a supershape. Isn't that fascinating? The theory suggests something really interesting, that the wave function is not just one thing, but a supershape in itself. The theory puts forth the fascinating idea that the wave function is a supershape, and that the wave function itself is a supershape. Isn't that an amazing thought? The theory puts forth something truly amazing, that the wave function is a supershape, and that the wave function itself is a supershape. This theory is really fascinating because it suggests that the wave function is not just a combination or superposition of various states. Isn't that interesting? It's actually a supershape in itself. But here's the really cool part. Even though we only record one outcome or solution of the wave function, it doesn't mean there aren't other solutions out there. It was thought that when we look at something, it would collapse into a different state. Schrödinger was ahead of the curve. He wrote an article in 1952 that showed this expectation was ridiculous. He made a bold statement in his writing. It's not possible to control the wave function using two completely different methods, but that's okay. It's really interesting to see how wave alignment can play a part in some situations. But there are also other instances where it's the direct interference from the observer that's the driving force, regardless of the wave alignment. Isn't it fascinating how often we see the concept of a cat being a component of a universe being used in so many different ways? Sometimes this is done by aligning the waves, and other times it is done by the observer directly intervening, regardless of the waves. The great news is that Schrödinger didn't actually apply this concept to his famous cat, but it's still a perfect solution to this mystery. Given that Schrödinger's terminology has been expanded upon, it's now possible to suggest that there are two parallel universes, or two worlds. Isn't that fascinating? This means that our dear cat lives on in one of these two wonderful worlds, while it passes away in the other. In one universe, a sad discovery is made. A dead cat has been found inside a box that has been opened. In a truly surprising turn of events, the cat that was found inside the box is revealed to be alive and well in a different universe. Since the beginning of time, there have always been two worlds, and they were exactly the same at the very instant when the dreadful machine decided the fate of cats. Isn't that amazing? Isn't that just the most incredible thing you've ever heard? Guess what? The collapse of the wave function isn't happening. Isn't it amazing that quantum theory is built on the idea that anything could happen? Isn't it amazing that quantum theory is based on the idea that anything is possible? The right answer is that quantum theory is built on the thrilling possibility that this or that could be true. If we were to take this perspective for just a quarter of an hour, for example, we would have a fantastic outcome. I think we can all agree that would be great. The answer is that the quantum theory is founded on the probability of nature, which is really exciting. But here's the really fascinating thing about this theory. The outcomes it predicts aren't always the same. Isn't it amazing that the outcomes of this theory can vary depending on how it is used? Just for a moment, let's imagine that the rules of nature could look like this. For instance, if we just spent a quarter of an hour looking, we'd be able to see how the universe around us is changing really quickly. It'd go from being a solid, structured thing to a crack, to a formless jelly or plasma. It's truly an amazing thought. The theory makes the bold assertion that the results of the theory are not what you might expect. Isn't it amazing? It's so interesting. It looks like none of the lines are floating, and it's as if we're starting to resemble jellyfish ourselves. I find it so interesting that he has such a strong belief. He's absolutely certain that the nature that hasn't been observed works precisely this way in accordance with the wave equation. The options we talked about earlier are only useful when we make observations. And it's important to remember that these observations don't have to be scientific. That opens up a whole new world of possibilities. In its early stages, he made an interesting comparison with the dividing amoeba. This was used to show how different the two are from one another. The amoeba is an amazingly complex and fascinating material. It's truly incredible. It can be tricky to understand the difference between it and the other material, but it's a fun challenge. Back in 1955, when he was working on a dissertation at Princeton, he found it really interesting to try to understand the difference between the amoeba and other materials, especially as the amoeba is so complicated. In the first draft of the document, he made an amazing connection to a dividing amoeba, which is further divided into two smaller cells. Isn't it amazing to think that each of these little amoeba would have remembered the same story until the moment of separation? And then, just like us, a new story would begin to accumulate. If the simplest thing in the world had a mind, this would undoubtedly be the case. He was absolutely thrilled to receive a recommendation from John Wheeler, the scientific director of Everett, to devise a mathematical description of the concept for the purpose of writing a dissertation and an essay that was published in Reviews of Modern Physics in 1957. But then, something truly amazing happened. The lovely amoeba analogy vanished, and it didn't reappear in print for a long time. Everett made an intriguing observation. Even if no observer has ever had the sensation of other worlds, the assertion that there cannot be any other worlds because we do not perceive them is not any more convincing than the assertion that the Earth cannot spin around the sun because we do not feel its movement. Everett never tried to further the concept of multi-world interpretation throughout his life, but he certainly left us with a fascinating idea. In an unexpected but thrilling turn of events, he began working at the Pentagon in the Waffen System Evaluation Group, even though he hadn't yet finished defending his dissertation. To help tackle the challenges of the Cold War, he was given the exciting task of applying mathematical principles to documents that were playfully dubbed game theory. Luckily, some of his work is still out there for us to discover. Sadly, he disappeared from the academic community, and it was as if he had never been there at all. It wasn't until the latter half of the 1960s that Everett's concept really started to gain attention. When Bryce DeWitt, a professor at the University of North Carolina, accepted it and began to promote it with excitement, he said something really interesting. He said that every quantum transition taking place in every star of every galaxy, in every distant corner of the universe, splits our local world on Earth into myriads of copies of itself. And the best part is that each and every one of these quantum transitions occurs in every single star in every single galaxy. Isn't that amazing? With Wheeler, it was a truly excessive amount. In the 1970s, he made a bold statement. In the end, I had to give up on supporting this hypothesis because I'm afraid it will carry too much metaphysical load. He was initially drawn to the multi-world interpretation, but he changed his mind and decided not to endorse it. In a truly amazing turn of events, this was precisely when the concept was reborn and evolved in the realms of quantum computing and cosmology. Even though he wasn't quite ready to back this interpretation, those who knew about it were really excited about its potential. John Bell made an intriguing observation. Humans multiply with the world, and people living in a specific region only perceive what's happening in that area. He was also really happy to say that there might be a way this idea could be useful. The multi-world interpretation is an ambitious and fascinating theory, It's also, at its core, an extremely open-ended one, which makes it really exciting. I'm almost ready to say goodbye, but I'm also really excited to see what else it can do. But don't lose hope. It's entirely possible she has something to say about the conundrum that Einstein, Podolsky, and Rosen have created. I'd love to see what she has to say. It would be so amazing if we could come up with a really solid version of it and figure out if it's actually true. And there's another great thing about the existence of plausible worlds. It allows us to relax a bit more about our own world, which is actually less likely than other worlds in certain ways. David Deutsch, who is affiliated with Oxford, is the brilliant mind behind the development of a rigorous form of the multi-world interpretation. As a matter of fact, it was the foundation upon which the Schrödinger version was built. Even though Deutsch wasn't aware of it at the time, it ended up being the foundation for his work. David and Deutsch worked together throughout the 1970s, and in 1977, during the final conference that was scheduled, Deutsch had a meeting with Everett. This was a truly special moment, the one and only time Everett ever got to present his thoughts to a wide audience. By becoming a pioneer in the realm of quantum computing, Deutsch was able to demonstrate his conviction that the multiverse interpretation is the most effective method for understanding the quantum world, and it was a resounding success. He wasn't interested in computers, but he thought that if someone made a quantum computer, it would show that the multiverse interpretation was true. He was absolutely convinced that this would be the case. And now, we're back to the fascinating topic of quantum computing. Isn't it amazing? You can make a quantum machine that isn't a quantum machine, and you can also make one that does everything a quantum machine does. This is the truly amazing concept behind a quantum machine. Have you ever thought about what it would be like to make a quantum machine that is a quantum machine? Well, that's exactly what this concept is based on. It's a pretty mind-blowing idea that you can make a quantum machine that is a quantum machine, but a quantum machine itself is not a quantum machine. The idea of a quantum machine is based on the exciting idea that it might be possible to build a quantum machine where the whole universe is split in two. In a similar way, David shared something truly fascinating. It's about something really cool, a free electron in a faraway galaxy. When faced with a choice between two or more quantum paths, it actually splits the entire universe, and that includes both of us. Isn't that incredible? There are so many worlds out there, each with its own special reality, and they all come from the infinite possibilities of the quantum wave function. This is what scientists call the multiverse. Isn't that fascinating? This is such an intriguing idea. It's called the Deutsche-Schrödinger variation, and it's fascinating to see how it works. Isn't it incredible? This machine can create a whole bunch of worlds that correspond to all of the possible solutions to the quantum wave function. This is the incredible multiverse. In the experiment with the cat, there are so many universes that are just like our own. And in each of these universes, kind experimenters build machines that are just as awful as the last. And the best part is, all of these worlds will continue to be precisely the same until the moment the machine actually starts working. In some realities, the poor cat passes away, while in others it continues to live. And this amazing thing happens in future stories throughout the universe. It's just so amazing. It's so interesting how parallel worlds can't communicate with each other no matter what, or they might be able to. You never know. The wonderful Dr. Schumann, a German scientist, has been working on something truly amazing, a quantum computer that can track quantum phenomena in the brain. The amazing Deutsch makes the fascinating claim that when two or more identical pre-universes that are subject to the impact of quantum processes are forced together, two or more identical pre-universes are created. He has this really cool idea that a quantum computer will be able to remember the experience of time, even when it's in parallel realms. Even though this research is still in progress, Deutsch has already found evidence of the multiverse that is much more straightforward, which is really exciting. Isn't it amazing that a quantum computer's keys are in a superposition of states? This is a really different kind of computer. A regular computer is made up of a bunch of keys, which are parts of electrical circuits. These keys are truly amazing. These keys are pretty amazing. They can be activated or deactivated, which corresponds to the digits 1 and 0. This allows you to perform calculations by manipulating lines of numbers written in binary code. The term bit simply refers to each individual key. The more bits we have available to us, the more powerful the computer is. It's that simple. A byte is equivalent to 8 bits, and the amount of memory that a computer can store nowadays is absolutely incredible, measured in billions of bytes. It's mind-boggling to think about. Can you believe it? 1 gigabyte. In the wonderful world of binary code, a gigabyte is equivalent to 2 to the 31st degree bytes. Isn't that fascinating? This is the most accurate and precise definition of the term you'll find. The good news is that this is usually not detected. On the other hand, each key in a quantum computer is something pretty amazing. It can exist in a superposition of states at the same time. Isn't that cool? In general, it is an atom, but in principle, it can be thought of as an electron, and the spin of an electron can be either positive or negative. How cool is that? Isn't it amazing that superposition is so different from other states? It's because the electron has both a positive and a negative spin. Isn't this just the coolest thing ever? It's a 0 and a 3. Each of these keys is called a qubit. This special property of quantum mechanics is what makes each qubit equivalent to 2 bits. It's truly a remarkable phenomenon. It might not seem like a big deal at first, but it's actually pretty amazing. And now, for the really fun part. Guess what? If you have 3 qubits, you now have 8 different ways to assemble them. Now for the really cool part. I'm sure you'll be as amazed as I was to discover that when we compare the total number of qubits to the equivalent number of bits, we find that they are always equal to 2 times the degree of the qubits. This quantity is typically referred to as a kilobit, which is a truly impressive number. Strictly speaking, it's comparable to 2 to the 10th power of a bit, which is 1024. And there's more. Guess what? Only 10 qubits would be equivalent to this. It's truly amazing to see how these geometric progressions keep growing, and it just keeps on going faster and faster. Just picture a computer with 300 qubits. It would be like a regular computer with a bit number that's greater than the total number of atoms in the entire universe. But how on earth could a computer like this possibly perform all those calculations? The great news is that the first quantum computers, which consist of multiple qubits, have already been built and shown that they work just as we hoped they would. This is great news. It means we can now start using them in ways that will make a real difference in the world. I'm so excited to tell you all about this. The answer is truly fascinating. According to Deutsche, the calculations are performed all at once on machines that are exactly the same in each of the parallel universes that correspond to our superpositions. In the context of a computer with 3 qubits, this is truly amazing. It means that 8 superpositions are utilized simultaneously, which is incredible. I'm so excited to tell you all about this fascinating answer. The calculations are done at the same time on the same computers in each of the parallel universes that match up with our superpositions for a 3-qubit computer. This is just so incredible. It's pretty amazing to think that there are 8 superpositions of computer engineers working on the same task using identical computers to get the answer. It's no surprise that they're all working together. They're all part of the same team, with the same goals and reasons for being there, which is great because they can support each other. It's actually pretty simple. Just picture this for a second. What if we built a machine with a volume of 300 cubic centimeters? I'm sure this will happen at some point in the future. If Deutsch is right, it would mean that lots and lots of universes would be working together, which is pretty mind-blowing. In fact, it would be more than the maximum number of atoms that we can see in our cosmos. This brings us to an interesting question. Could the metaphysical load already be too heavy? The great news is that you get to decide for yourself, but if you think it's excessive, you get to explain how quantum computers work. Luckily, there's a growing trend among quantum computer experts to sidestep these concerns. Fortunately, there is a group of researchers who are unafraid to face these concerns head on. On the other hand, there is a group of scientists who are used to thinking about so much more than just 6 impossible things each and every morning before breakfast. Guess who the members of this group are? They're none other than the brilliant cosmologists. Some of them have even come to the conclusion that the best way to explain the very existence of the cosmos is to adopt a multi-world explanation. They start with the really exciting fact that the equations don't mention anything about the collapse of the wave function. And that's where it all begins. At the same time, they're talking about a single wave function, which is the same wave function that shows the whole world as a mix of states, a multiverse that represents a mix of universes. The theory of the universal wave function is the name of the initial version of Everett's dissertation. It was subsequently revised and condensed with the assistance of Wheeler before being submitted. In the context of the universal, the author was trying to make a very literal reference. The universe, and entity are all such exciting words. They're full of possibilities. This is such an amazing discovery. This is great news. It means that we can now regard the functions of the state as fundamental objects, and it even lets us think about the role of the state of the entire universe. I'm so excited to introduce this theory as the theory of the universal wave function. This is because it is thought that all of physics comes from this one function, which is an absolutely fascinating idea. Given what we're trying to achieve, it's obvious that the state function is another way of saying the wave function. All of physics is connected to everything, including us, the observers, in the language of the physical sciences. Isn't that just the most amazing thing? This isn't because they were also included in the wave function, but rather because this idea of a single non-clashing wave function is the only way to understand quantum mechanics. This is fantastic news. It means there's a chance that quantizing the general theory of relativity could be a fruitful basis. This is why cosmologists are absolutely thrilled about this theory. In the mid-1980s, he inspired a new wave of optimism among cosmologists who began actively working on the theory, even though his wish has not yet come true. But don't worry, there's still plenty of evidence to support this theory. The universal wave function is an incredible mathematical expression that explains the position of every particle in the universe at a specific moment in time. But wait, there's more. It even defines every potential position that these particles could be in at that exact moment. And there's more. Even though there are limits to what can happen in space and time, there are still so many possibilities for each particle to be in at any other point in time. From this truly mind-boggling number of potential universes, many of the possibilities will be so outlandish that it's impossible to imagine stable stars, planets, and people living on them. But that just adds to the fun. As we see in science fiction and art literature, there will be at least some universes that are similar to ours in many ways, and they're out there waiting for us to explore. In his statement, Deutsch made an intriguing claim. He said that according to the multi-world interpretation, any world portrayed in a literary work genuinely exists somewhere in the universe, provided that it abides by the laws of physics. Somewhere, for instance, there is the absolutely fantastic world of Thunder Mountain. The cosmos is a truly fascinating and intricate universe. It's not easy to capture its essence in a single word. Just think of how many different worlds there are in the universe. The cosmos is so intricate and fascinating that it's impossible to describe the universe with just one word. The universe is an amazingly complex and intricate place, isn't it? The cosmos is an amazingly complicated and intricate universe. It's just not possible to describe it in terms of time, like 1 second, 1 hour, or 1 year. And that's why the universe is so wonderfully complex and intricate. The cosmos is so much more than just a singular entity. It is a complete whole. The cosmos is a whole, and it's so exciting to understand it as such. The universe is an amazing, complete entity that exists in a similar way to ours, but it is displaced in time by a certain amount of time, such as 1 second, 1 hour, or 1 year. On the other hand, there's no evidence that any universe is moving from one instant in time to the next. I am so lucky to be the subject of the second universe, which is characterized by the universal wave function. I'm so lucky. I have all of my memories from the very first moment of time, as well as the memories that go along with the second moment, the third, the hour, the year, and so on. On the other hand, it's not like all of these possibilities represent the same individual, which is pretty cool, right? Isn't it amazing that we can group different time states together based on the events that happen in them? This is great because it means we can tell the difference between the past and the future. But, my friends, it's time for us to make a change. It's time to find a new form of comfort, my friend. And now we're going to search for it in the direction of the cosmos together. The cosmos is an amazing, intricate universe. It's truly something to behold. It is a cosmos that is extremely, extremely complicated, and it's absolutely amazing. The universe is an amazingly complex and fascinating place, isn't it? The universe is an amazingly complex and fascinating place. The universe is an amazingly complex and fascinating place. The universe is an amazingly complex and fascinating place. The universe is an amazingly complex and fascinating place. It's time to set off on a new adventure to find a different kind of solace. And this time, we're going to search for it in a totally new way. And the best part is, to be coherent is really all you need. Physicists are really excited about the concept of coherence, and it's easy to see why. And those who advocate for interpretations based on decoherence make an exciting claim. They say that it is the presence of issurance that causes the quantum world to function in the manner that it does. To gain a deeper understanding, we'll conduct an experiment with two holes, as we often do, and we'll walk you through it step by step. Color waves, along with any other waves that diverge in different directions from two holes, have this amazing ability to originate from a single source and, as a result, synchronize with each other. Isn't that incredible? The holes are simply directed along distinct trajectories by these coherent waves, and it's really cool to see how the difference in the length of these trajectories affects the way in which two sets of waves interact with each other. In this area, they come together in a unified phase, while in that region, they diverge. Waves are just the coolest, aren't they? They can interact with each other in so many different ways. They can be in the same phase, or they can be incoherent. It's really quite fascinating. Have you ever thought about how light from two torches illuminating a wall is an example of incoherent waves? There's no interference picture there, but that's okay. But there are also different grooves and falls of the waves that always fall into place in a regular pattern, following clear rules. Isn't it fascinating how the waves interact with each other? It's truly amazing how they create the same regular pattern of light and shadow. In most cases, there's something really cool called interference between them. Even though it can seem like everything is a bit chaotic, there's still a pattern that emerges. It's really quite amazing to see how quantum particles seem to disappear when nothing is separated from everything else, according to the interpretation that incorporates decoherence. On the other hand, the light that came from the two torches was never quite together, and that's what made it so fascinating. They were both so intriguing, weren't they? I'm so excited to share another analogy that I think you'll find really helpful. Have you ever seen the amazing Mexican wave at a stadium? It's so much fun. Just picture this for a second. All the spectators in the stands start rising and lowering their hands at random intervals. You'll see the most spectacular display of people waving their hands in unison. But here's the amazing thing. Isn't it amazing what can happen when everyone in the stadium raises and lowers their hands at the right time, following their neighbors? It's like a wave that carries over the stadium stands. Isn't it amazing how a coherent wave can be created? But here's another cool thing. Random waving hands aren't coherent, which is pretty neat too. This is why the term decoherence doesn't quite fit in the context of quantum mechanics. On the other hand, some folks who love this idea might feel like the name gives people who aren't familiar with it a wrong impression about what they're talking about. If those who support this concept are right, it would mean that the boundary between the quantum world and the conventional world isn't defined by size, but by coherence. This is something that Bohr and his colleagues have hinted at in a rather intriguing way, and there's a good reason for it. I'm really interested to know more about this. I find the idea of a quantum machine absolutely fascinating. It's not about size, but coherence. This is something that Bohr and his colleagues have explained in a somewhat hazy manner, and there is a reason for this, and it's an intriguing one. Isn't it amazing that single atoms can exist in a quantum superposition? I can see where you're coming from. You might think that a cat, which is a big and complex animal, is too big to be in a quantum superposition. This is such a great argument. Just think of the possibilities. So let's play a little thought experiment together. Imagine a cat in a box. Where do you think we'll need to draw the line to differentiate between the two? I wonder if we could ever know whether it is alive, dead, or in a state of superposition. Would that be enough information? And what about a tiny little microbe? Nobody had any idea about that. It was just so amazing that you could even take it in your hand and hold it. The only hiccup was that the device needed to be cooled to extremely low temperatures to work properly, so it was tricky to hold it in your hand while it was in use. Once the electric current in the superconductor has been initiated, it will continue to flow indefinitely. It's truly amazing. Isn't it amazing that you can actually monitor the behavior of the current as it flows through the ring squid? And you can even adjust it by using electrical and magnetic fields. In some amazing experiments, we've seen that the electrical wave around the ring behaves just like a single quantum entity. This amazing quantum object is about 100 million times larger than an atom. I bet it's even bigger than bacteria or fleas. The Leggett was a huge success in achieving its initial goal, and it didn't stop there. I bet you're wondering how a wave can move in a circle in both directions at once. Well, it can't, but that's what makes it so special. Oh, you've made a little mistake there. Since then, there's been so much progress in this field. It's led to some truly amazing achievements. In fact, it's resulted in something really special, the Leggett Nobel Prize as well as a knighthood. I'm so excited to tell you all about the amazing squid device. It's getting bigger and better all the time. I'm happy to say that it's already making a difference in the field of medicine. It's being used as a highly sensitive magnetic field detector generated by the human body, which is pretty amazing. And there's more. It's also being considered for use as potential components of magnetic fields formed by the human body. And there's more. It's also being considered for use in quantum computing, which is really exciting. It's so important for us to remember that even though waves are coherent, they behave like macroscopic examples of quantum states that are clearly articulated. It's a truly fascinating phenomenon. But as the temperature rises and the waves decacoage, we get to explore the fascinating phenomenon of quantumity in action. In Bohr's terminology, we can say that decaduration is the factor that results in the collapse of the wave function, which is really exciting. This has led some physicists to believe that the Copenhagen interpretation is similar to the interpretation with decoherence, but that it is referred to by a different term. On the other hand, at the same time, we can see how superposition and confusion play a fundamental role in the strict formulation of the interpretation with decoherence. The concepts of superposition and confusion are two peas in a pod. Isn't it amazing what happens when two particles come into contact? They go through a process of confusion. From that point on, anything that happens to one particle affects the other. It's truly fascinating. In fact, they blend together to become one entity, and it's truly incredible to witness. And so, from this point forward, anything that happens to one of them will affect the other. It's truly amazing. They actually merge into a single entity. Similarly, the wave that's moving around the squid ring in both directions at once can be seen as two waves happening at the same time and connected to each other. It's a really cool thing to think about. This is where it really gets interesting. And then something really cool happens. A single quantum object is produced, which is a wave that travels around the ring in not just one direction, but in two directions at the same time. The world is so much more than we ever could have imagined. It's not just one thing, but a whole quantum object. It's a wave that moves in a circle, not just one direction, but two at the same time. This is the only thing that leaves room for doubt, which makes it all the more fascinating. Isn't it fascinating to see how the concept of disagreement didn't exist until the 1980s? Isn't it amazing how things work out sometimes? This was a truly remarkable coincidence because it coincided with the tests that showed that confusion is an accurate representation of the way our world operates. Take a moment to think about this with me. What happens when a pure quantum item decays because it interacts with the outside world? I know it's not getting any easier to understand, but I promise it'll all make sense soon. Just picture it for a moment. Imagine a single particle in a completely unadulterated quantum state. Just stop for a moment and think about how fascinating it would be if it were to disperse to another particle or even interact with a photon of light. How could it possibly be confused from that point on? In an amazing turn of events, when one of the three entangled items interacts with the third, all three of them become entangled, and their quantum states are in a state of superposition. Isn't that incredible? It's truly fascinating. It's this amazing phenomenon that's responsible for spreading confusion. It might be hard to believe, but there's no such thing as a completely isolated quantum system. In the absence of extremely exceptional circumstances, such as the existence of a quantum system that is completely isolated from the rest of the world, this is what we can expect to happen. Don't worry, this is pretty normal and nothing to be concerned about. However, there are some special cases like when we study squids, and there are even some systems that are confused with both. And now for something really interesting. The superposition is a really interesting concept. It basically means that the combination of everything that has ever interacted with the initial particle and everything else that it has ever interacted with is referred to as the superposition, and there's more. It also includes everything that it has ever interacted with, as well as everything that it has ever contacted or communicated with in the past. Have you ever heard of the term decogreyance? It's an amazing concept that refers to the incredible process of integrating all of the elements of the world and the universe into a single quantum system. This is why it's so fascinating, and I'm so happy to share it with you. It's so interesting. The quantum of a particle that was once isolated is no longer something we can observe because it has become mingled with everything else. This presents an exciting challenge for us to understand the underlying quantum components of everything, with the exception of the most basic systems. The great news is that since the equations that describe the quantum world are time trivial, mathematics will tell you that this is possible in principle. This is why the quantum world is so interesting and complex. But don't get your hopes up. It's unlikely that someone will try to do this anytime soon. As the wonderful Philip Ball so perceptively noted, decoherence swiftly leads to an incoherent state. On top of that, the lovely Philip Ball has also shared some fascinating insights that aren't directly related to the task at hand. The good news is that it's still up for grabs. There's still a little bit of a mystery left to solve, but that just means there's plenty of room for discovery. On top of all that, the Ball also shared some fascinating insights into how long it takes for decoherence to happen in large objects. Guess what? This even applies to the famous Schrödinger's cat. Isn't it amazing that Schrödinger's cat can be both dead and alive at the same time? It's because it's prepared in a state of pure quantum that's almost incredible and coherent. And the best part is, you can even do it with a cat. All you have to do is be in a pure quantum state, and you're all set. And there's more. And the best part is, if you succeed, the quantum cat will decohere in either a living or dead cat at a rate that is faster than pollen floating in the air disintegrates. This also opens up a fascinating possibility, exploring some of the intriguing philosophical objections that can be raised against the Prague interpretation. The Copenhagen interpretation is a really interesting one that says that nothing is real unless you see it or measure it. If we go by this interpretation, we are taking it literally, which is really fascinating. Just for a moment, picture this. The code in the box is capable of being in a superposition of states. Isn't that fascinating? Oh, but wait a second. The opponents have another question, which I'm happy to answer. Do you think the moon is still there while no one is looking at it? On the other hand, after all this time, we know for sure that the moon is real. It's not something we can just brush off as not being real, you know? This brings up a really interesting question. How can we be sure that the moon is real? The great news is that it's totally possible to say that the moon doesn't exist. People made a really smart move by applying this way of thinking to all of history or to all of the stories that have been told about the cosmos. Rather than using the concept of decoherence only in the situation that's happening right now, they decided to broaden its scope so that it doesn't just apply to the current state of confusion in the universe, and that's where our story begins. The story of the universe is just beginning, and it's going to be a wild ride. And now, the story is just getting started. This is so exciting. It's so interesting to see how ideas evolve. What was once an autonomous interpretation, meaning an interpretation of stories that didn't contradict each other, has now evolved into an interpretation of stories that contradict each other. On the other hand, let's start with the point where we're discussing non-contradictory. This is where things really start to get interesting. We can say with certainty that the pattern on the screen matches what we see in the interference picture from the experiment with 2 holes. This shows us that the waves flowed through the holes and interfered with each other. This is the one thing we can say for sure, and it's pretty amazing, isn't it? We can be really proud that this is consistent with the fact that light started out as a photon when we see that light beats electrons that are embedded on the surface of the metal. Another method, known as the top-to-bottom strategy, was the one that Stephen Hawking himself favored. This method is truly fascinating, isn't it? It all starts with what the universe is like right now, and then it goes back in time, one step at a time. So, the big question is, what wave functions led to the birth of the cosmos? And in addition to that, what other possibilities might there be? Isn't it amazing that there are so many different ways this result could have been reached? And guess what? In most cases, there are more than one such path. There's no story that contradicts itself, and there's no one story that could be the only story in the world that could be restored in this manner. In the electronic version of the experiment with 2 holes, the electron reaches a particular position on the screen. Isn't it a total mystery which hole it traveled through? This is because there's no way to figure out which hole it went through. It's a mystery. I'm happy to say that both of these potential narratives fit perfectly with what we're seeing to be the case. And there's more. The world is often a lot more intricate than just an experiment with 2 holes. This is great news because it means there's a much wider range of stories that don't contradict those of the experiment. I'll circle back to this, but first, let's answer a quick question. Where exactly does the lack of coherence within this plot show up? And now for the really interesting part. If each measurement and each quantum interaction chooses 1, it means that the diversity of the multiple universes is diminished, which is a bit of a shame. This also reduces the number of possible universes, which is pretty cool, don't you think? The second most common type of quantum interaction is the one we call the second quantum interaction. It's really exciting because it's so important in this field of study. The first quantum interactions are the most common type of interaction, and they're pretty amazing. Isn't it amazing that quantum interactions are the very first of their kind in the history of numerous worlds? The second quantum interaction is the first quantum interaction, which is the first quantum interaction possible, and it's a truly remarkable phenomenon. This means that the amazing variety of universes that we could never have imagined is slowly becoming less and less, and this amazing process continues all the way up to the present day, helping us to understand the history of our universe. It's not just our own little corner of the universe, but also the incredible number of different worlds that could ever be. Isn't it amazing that decoherent storytelling lets us explore the full spectrum of possibilities rather than focusing on just one universe? Absolutely. We're going to jump back into the super fascinating topic of multiple universes, but this time we'll approach it from a fresh perspective. Some physicists were absolutely thrilled by the idea of using decoherence to transform the concept of many worlds into the concept of many stories. This was an amazingly revolutionary idea. This was a truly revolutionary idea. It allowed them to get rid of all that unnecessary baggage in the form of parallel worlds and replace them with a whole new concept. A variety of stories that existed only in the form of ghostly states among probabilities. But by the middle of the 1990s, things were about to get a whole lot more interesting than anyone had ever imagined. At a conference, Lee Smolin, affiliated with the Canadian Institute of Theoretical Physics Perimeter, had the incredible opportunity to hear Faye Doker's presentation on the fascinating topic of potential outcomes, and the concept, which he would later describe in his book titled 3 Roads to Quantum Gravity, was something that absolutely captivated his attention. Guess what? There are 3 amazing paths that lead to quantum gravity. This is the path to quantum gravity. I find the conclusions of Doker and Adrian Kent absolutely fascinating. They also suggest that there must be an endless number of paths, which is pretty mind-blowing, especially since the classical world we're experiencing, where particles have certain coordinates, is one of the worlds that doesn't contradict itself. It's described as some kind of theoretical solution, which is really exciting. Wouldn't it be amazing if we discovered that the interpretations of the infinite worlds of the past are different? It would be a truly incredible breakthrough in our understanding of the universe. Oh my, how things have changed since the past. Oh my, the world has changed so much since the past. Oh my, the world was so different in the past. Oh my, the world was so different in the past. Oh my, the world was so different back then. Isn't it amazing? If we can interpret stories that don't contradict each other accurately, then we have an incredible opportunity to explore the possibility that dinosaurs walked the earth 100 million years ago based on the existence of the fossil. Every story is like a window into reality. The questions we ask help us piece together the incredible true history of our wonderful world. The idea is that our world is not just a place that existed in the past. It is a part of the cosmos, which is the same as reality. And there's more. It's so interesting how the questions we ask shape our understanding of the history of our world. And it's just like that experiment with electrons. If you look for waves, you'll find them. And guess what? If we look for particles, we'll find them too. Isn't it amazing? We find a history that corresponds perfectly with the existence of dinosaurs in the past. And not only that, but we also find a story that fits perfectly with the existence of dinosaurs in the past. Guess what? If we look for evidence of the existence of dinosaurs in the past, we find a history. Isn't that fascinating? This is true, but it doesn't necessarily mean that dinosaurs existed in historical times. I'm so happy to tell you all the great news. This is great news. It means that what we see around us today doesn't rule out the possibility that dinosaurs lived on our planet in the past. I'm so excited to tell you all about this amazing discovery that Smolin has made. He's come up with a theory that helps us understand some things, but also leaves room for more. In the interpretation with decoherenza, you have the fantastic option of viewing either the Copenhagen version or the multiverse interpretation, depending on what you prefer. I'm not saying it's perfect for both of us and yours, but it could be. And that's totally okay. Don't worry if none of them align with your preferences. I'm sure the ensemble interpretation will bring you some comfort. The ensemble interpretation was the first to emerge, and it was also the simplest. Albert Einstein was a huge fan of this approach, by the way. As we work to embrace the quantum theoretical description as a comprehensive account of distinct systems, we may find ourselves at a crossroads. This is fantastic news. It means we no longer need to resort to such unnatural interpretations. Leslie Ballantyne, a professor at Simon Fraser University in Canada, and the most prominent current proponent of this concept, makes a great point. Einstein had other criticisms of how the theory of the universe is interpreted too. Leslie Ballantyne, a professor at Simon Fraser University in Canada and the most prominent contemporary proponent of this concept, explains that Einstein's criticism of the interpretation, which a large number of physicists accept by default, was connected to the fascinating fact that the wave function, which is the function of the quantum state, provides a description of not a distinct system, but rather an ensemble of systems that are similar to one another. The reality is that this interpretation doesn't really interpret anything at all, which is pretty amazing if you think about it. The argument makes a really great point. It shows that anything that seems unusual in the quantum world can be explained by looking at it from a statistical perspective. Sometimes the term statistical interpretation is used to describe this, and it's a great way of looking at things. Instead, it's a nice little reminder for the law enforcement officer who's at the scene of the crime that everything's under control and they should feel confident about moving forward. It's all about statistics and specific groups of data. But there's so much more to the phrase ensemble than meets the eye. In everyday language, an ensemble is a group of things that have something in common or work together. I'd like to give you a fantastic example of an ensemble, a musical string ensemble. For those who love statistics, an ensemble can be something truly special. Imagine a collection of 600 playing cubes, all crafted with the same design. It's a sight to behold. According to the rule of probability, we can look forward to some pretty amazing things. So, we're looking at about 106, 105, and the same number of 4s, 3s, 2s, and 1s. And here's the best part. You can achieve the same statistical result by using a different method. All you have to do is start with a single bone that is absolutely perfect for playing and then throw it 600 times. It's totally reasonable to anticipate that the 6 will fall approximately 100 times. The 5 will also fall approximately 100 times, and so on and so forth. This is the very essence of quantum physics. Isn't it fascinating? I'm sure you'll agree that it's not quite right to call a container full of gas molecules an ensemble. Guess what? Guess what? You can do the same experiment with lots of similar containers that contain gas. But don't worry, there are exceptions to this rule. This is the ensemble, and the results will follow the distribution of probabilities in accordance with the rules developed by Max Born to carry out such an experiment in practice. Don't worry. It's all pretty straightforward. But that's not what this experiment is about, my friend. In an ideal scenario, you would get to carry out the exact same experiment over the exact same particle a number of times. And the best part is, you get to track the result of each of these attempts. Now, just picture this for a second. Instead of 1,000,000 electrons zipping through the setup of a two-way experiment and being logged on the other side, it's just one electron at a time going through the setup 1,000,000 times. And here's the really cool part. Each time the electron passes through, we mark the position it's in on the other side. And the best part is that all of this is happening at the same time. In this context, particles are always real particles in the sense that you and I would use the word in our everyday lives. This is the part that really gets them going. This is where it gets really interesting. The wave function doesn't apply to individual particles, so every single electron has either a positive or a negative spin. But here's the really cool part. When there are lots of particles, there's a 50% chance of discovering each variant when inspecting a single electron, as long as all other variables remain the same. The idea of corpuscular wave dualism, superposition, and the existence of both dead and living cats are all incorrect, and that's a good thing. Wouldn't it be amazing if we could do an experiment with the same cat over and over again, 100 times or more? The ensemble interpretation makes an exciting prediction. If we were to do this with hundreds of cats in turn, half of them would survive and half of them would die. But here's the really fascinating part. Not a single cat will be in a superposition. This is why the ensemble interpretation is so powerful. It includes all of the cats. Does it sound appealing to you? I'm sure it will. It's really quite simple and it all makes perfect sense. However, as you and Squires helpfully pointed out, we haven't quite solved the interpretation problem yet. We'll just put that on the back burner for now. Oh my, there are so many possibilities. But how can we make it work in the real world? It's so tricky to explain what happens when the system, in this case the ensemble, is examined or interacts with the outside world in some other way. But that just means there's so much room for discovery and innovation. This is something that often happens in quantum theory, and it's so interesting. It's so interesting how the preparation of the system and the observation of it adds another fascinating layer of coincidences. This is made possible by a certain amount of participation in accidents. Once more, we have the thrilling opportunity to identify the boundary between the system and the outside world. Take, for example, the fascinating situation of confusion that permeates the entirety of the cosmos for the purpose of interpretation with decadence. It's a pretty mind-boggling concept, isn't it? One really cool example of this is quantum physics. It offers a super interesting way to understand how the system interacts with the outside world. But there's still so much to learn about how systems change from one state to another. The collapse of a wave function can't be described using the equations, but that doesn't mean it can't be described using something else. Every single experiment that has ever been conducted has failed to record any wave function that is in the process of collapsing. Isn't that fascinating? It means there's still so much to discover. In 1954, Alan Turing made an amazing prediction. He said that if you monitor a quantum system constantly, it will never change. This is why it's so important to keep an eye on things. They keep everything nice and still. This is something that medical professionals are working hard to explain in a variety of different ways, and they are doing a great job. Isn't it fascinating to see the difference in the physics of the system? It's a totally different physics, my friend. There's a fascinating difference in the physics of the system. Isn't it amazing that there's a difference in the physics of the system? And it's not just a little difference, it's a big one. There's a fascinating difference in the physics of the system. There's something really fascinating about the physics of the system. I've got some great news for you. I think there's a good chance you'll be able to view it in another state if you wait a little bit longer and take a look at it. But if you take a quick peek, you'll see that there's no time for modifications. Don't you worry, the system will continue to exist in the same state. This is why it's impossible for it to be in an intermediate state, because there are no intermediate states. And so, the wave will begin to spread once more from the same point. If you keep an eye on the system, you'll never see it change. Guess what? If you keep an eye on the quantum kettle, it'll never come to a boil. Turing made this incredible forecast, and his prediction has already been put to the test through many fascinating experiments. It's so exciting to see his ideas being tested in real life. Every single one of these tests is an exciting new twist on the same old subject. In normal circumstances, a kettle is made up of thousands of ions of a specific element, like beryllium, which have been captured by electric and magnetic fields. Isn't that fascinating? Ion is a really fascinating word. It's used to describe an atom that has one or more electrons removed from it. This is why the atom is given a positive charge, which makes it super easy for the ion to be manipulated by means of fields of this kind. And it just keeps getting better and better. It's truly amazing how much energy the system can carry. The really cool thing is that we can actually see what's going on inside the system using some pretty sophisticated technology that makes use of lasers. This incredible method lets us see how many ions have made it to the main state during a specific time frame. In a typical experiment, something pretty amazing happened. A single ion was produced in just 128 milliseconds. This experiment is pretty straightforward and the results are pretty amazing. The ion is a fascinatingly simple process that's also easy to understand, which I think you'll find really interesting. This amazing method lets us see how many ions have made the transition to the primary state over a specific time frame. In a typical experiment, we made an amazing discovery. In just 128 milliseconds, half of the ions had successfully made it through the primary state. In an exciting twist, we discovered that if the laser arrived at the system 64 milliseconds after the beginning of the process, then just 1/4 of the ions would have made it through the primary state. Guess what? It's the same story for each interval of 4 milliseconds. The great news is that when we make observations more frequently, we can see the effect more clearly. If you see wave functions, don't worry. They'll never collapse. So let's jump right in and think about the possibility that they might collapse. In his argument, Ballantyne makes a really good case that they don't do that. He also presents the fascinating phenomenon we mentioned earlier as an example of experimental evidence that supports the ensemble interpretation. It's pretty amazing that today's experimenters can handle individual quantum objects with such care and precision, even though they're not considered examples of quantum objects. It's a funny thing, but a quantum object isn't the experimenter. It's the experimenter who is the quantum object. Guess what? The experimenter is a quantum object too. The experimenter is a quantum object, and here's the really cool part. The quantum object itself is also not a quantum object. Isn't that fascinating? It's pretty amazing to see how experimenters can calmly manage independent quantum objects, such as electrons, in scenarios like quantum computing. After all, the experimenter is a quantum object too. It's like they're conducting a symphony of quantum particles where they seem to follow the rules of the wave function. But here's the really cool part. The experimenter itself is not a quantum entity. And there's more. The squid ring can even demonstrate a single macroscopic quantum entity using light. Isn't it incredible? In this amazing superposition, the electron wave travels along it simultaneously in both directions. Isn't it amazing? It's traveling in both directions. The latest and greatest form of ensemble interpretation incorporates the most important characteristic of the cosmos, non-locality. If Einstein hadn't been open to the idea of non-locality, we might never have seen the amazing transformations he proposed. One of the most fascinating concepts that has emerged in the ongoing evolution of our beautiful cosmos is the idea of non-locality. I think it's very likely that Einstein would have been absolutely thrilled with the revolutionary new interpretations he embraced throughout his life. However, Smolin is so taken with them that he undoubtedly enhances his interpretation of the true ensemble interpretation. The most important and exciting distinction is that, in the Smolin version, the members of the ensemble are concurrently actual. This is a really important and exciting distinction. In the traditional understanding of the ensemble, it is impossible for all of the members of the ensemble to exist at the same time. Let's throw in one more physicist-specific jargon word to make it shorter and more reflective of the real world. A group of possible quantum components, such as hydrogen atoms, are referred to as beebles, which is a really fascinating concept. The word beeble comes from the word be able, which means power to have an opportunity. Isn't that a lovely idea? That's why we call them potentialities. They have the amazing potential to occur. But here's the really cool part. Guess what? When you throw one playing bone 600 times, instead of throwing 600 bones all at once, it's totally fine if they're not all present at the same time or in the same order. I'm really excited to introduce the real ensemble interpretation, which says that all of the beebles that make up the ensemble truly exist in nature at the same time. I'm so excited to tell you that the ensemble is made up of 600 playing bones that are thrown together, rather than one bone that is thrown 600 times in a row. Isn't that amazing? Isn't that great? By determining the values of the variables, you can analyze any quantum system in any other system. I am so excited to tell you all about Smolin's reasonable principle. It's a pretty amazing idea. It basically says that anything that affects how the real system in the universe behaves should also be part of the real system in the universe itself. I'm so happy to tell you all the great news. This is great news. It means that everything that affects the behavior of the real system in the universe should also be a genuine system in the universe. He's really passionate about this idea that it's not okay to think there's some kind of spooky mechanism where potentialities affect the world around them. Take the pilot wave interpretation, for example. The idea is that the wave is a real property of the universe, a form of capability, not some scary wave of probability. This is such an amazing idea. This is because the wave is a result of the universe, and it's a pretty amazing result. This interpretation, though, presents an intriguing challenge to another hypothesis that Smolin proposed. In the wonderful world of nature, nothing is ever truly lost. Guess what? Every action can be undone. This is an amazing new way of thinking about Newton's third rule, which says that in classical systems, action and counteraction are equal in size and opposite in direction. In other words, this is an extreme and fascinating example of the law. Smolin has created a truly amazing picture of how all the different parts of the ensemble influence each other. It's so inspiring to see how this explains the incredible behavior we see in tests like the experiment with 2 holes. It's so interesting to see how the wave affects the particle and how the particle affects the wave in the interpretation with the wave pilot. And if all of the elements that make up the ensemble are genuine, then there's absolutely no reason why there can't be some exciting new interactions between them. In fact, there's every reason to believe there will be. Smolin provides an excellent illustration using hydrogen atoms in their primary state, which is the state in which they have the least amount of energy. In the vastness of the cosmos, there is a collection of all these hydrogen atoms, which can be thought of as a real collection of real beables. It's so interesting to see how all the different parts work together. Isn't it amazing how this interaction allows beables to copy each other's states exactly, according to the rules of copying? It's truly a remarkable phenomenon. Isn't it great that the rules of copying don't depend on where the components are in space? Isn't it fascinating how they depend on how the variables are distributed throughout the ensemble? The great news is that we can create a list of all the places in the primary state where hydrogen atoms can be found using quantum statistics. But here's even better news. This method doesn't let us figure out which hydrogen atom is in which spot. From this perspective, they simply don't have anything to interact with yet. This leads to some really fascinating conclusions. The first thing we know for sure is that our beautiful universe must have a finite size. In a truly fascinating twist, the law of Newton and other similar laws are considered perfectly appropriate as an approximation of quantum mechanics. It's so great that the law of Newton and other similar laws are absolutely appropriate as an approximation of quantum mechanics. As an approximation of quantum mechanics, the law of Newton and other similar laws are considered absolutely appropriate. As an approximation of quantum mechanics, the law of Newton and other similar laws are considered absolutely appropriate. As an approximation of quantum mechanics, the law of Newton and other similar laws are considered absolutely appropriate. As an approximation of quantum mechanics, the law of Newton and other similar laws are absolutely spot on. As an approximation of quantum mechanics, the law of Newton and other similar laws are absolutely spot on. As an approximation of quantum mechanics, the law of Newton and other similar laws are absolutely spot on. As an approximation of quantum mechanics, the law of Newton and other similar laws are considered absolutely appropriate. On the other hand, Smolin has this feeling that quantum mechanics itself is just an approximation to a more profound explanation of the universe, and he's absolutely convinced it's the right one. This is what inspired him to courageously venture into these mysterious depths, going to incredible lengths to prove his point. He says that if this is true, then we can forget about the problem of messages being sent at the speed of light. But it's not just us. It's the whole cosmos that's up against this challenge. And so it has been inspired to jump right in and explore these mysterious depths. And there's more. If this is true, then sending signals at speeds comparable to the speed of light would be a breeze. There's one thing that shows we're not quite there yet with the definitive version of the theory, but we're getting there. I'm sure you've already picked up on the fascinating fact that the interplay of the Beebles suggests the presence of a distinct cosmic time. It's time to expand the scope of the theory of relativity. This is the only way we can make it possible for these interactions to take place at the same time. Smolin makes an intriguing suggestion that quantum physics is actually an approximation of some as yet unknown cosmological theory presented in a different language. It looks like we might be on the cusp of a breakthrough in our quest for these fundamental rules. Experiments involving systems that exist in the universe in a tiny number of copies are helping us to understand more. These are the special systems that exist right at the boundary between the microscopic and macroscopic worlds. Just for a moment, let's imagine we were to do tests using quantum computers. Wouldn't it be amazing if we could find out if there are copies of themselves somewhere in the universe? There's a real possibility of detecting some pretty amazing effects produced by quantum physics corrections that depend on the size of the ensemble. This might sound a bit out there, but Smolin really has a way of making things stand out. It's so interesting how people used to be amazed that the sun could affect the planets from such a distance. Newton's famous response, hypothesis non fingo, or I do not fabricate a hypothesis, was his brilliant way of explaining how it all works. As I've already mentioned, even Newton didn't try to explain how it all works. This ensemble interpretation is really exciting because it suggests a new kind of non-local interaction between the balls. It's totally understandable to feel a bit uneasy about this. But it's important to remember that just 100 years ago, the interaction between the sun and the earth was described by a different kind of interaction. Now, it's described by general relativity, which is a pretty amazing development. I'm happy to share some great news. It's not widely known, but physics and locality aren't as scary as they seem. It's so great to see that more and more physicists are embracing this idea as a standard part of their reality, just like gravity. Once you get your head around it, you'll see it's actually pretty simple. Isn't it amazing that it's the interaction itself that is the established property of the world around us? Now let's talk about these interactions. What can we say about them, given that this is not the appropriate time? Could this be the answer we've been looking for? I really hope so. Have you ever wondered about the nature of light? It's a fascinating topic that fascinated Albert Einstein. It turns out that the transactional interpretation of quantum mechanics may have its roots in this very question. This fascinating study of light inspired Einstein to develop the revolutionary theory of special relativity, which was a truly amazing achievement. This amazing discovery was what made him see just how much potential there was in this field of study. It's truly amazing to think that the equations which describe the behavior of light and all other electromagnetic radiation actually follow from those very same equations. This incredible revelation led to the development of the special theory of great physics. In an amazing turn of events, we discovered that everything and everyone is moving at the same incredible pace, which is the speed of light. And now we have something to count on. It's written down as a C, so if you shine a flashlight in my direction and I simply stand next to you, I'll get a grade of C when I measure the speed of light coming from a flashlight. But here's the really cool part. I'll still get a C no matter how fast I approach or leave you, my friend. This simple fact inspired the great Albert Einstein to develop the theory of relativity. The truly amazing Maxwell equations tell us that the speed of light is the same for everyone, no matter who they are or where they are. These amazing equations are named after the brilliant physicist who discovered them in the 19th century, who was named Maxwell. But wait, there's more. The equations of James Clerk Maxwell have another fascinating quality that I'm excited to share with you. And the best part is, they're totally symmetrical in terms of time. Isn't it amazing that these equations always have two solutions, no matter if they're about electromagnetic radiation or not? Guess what? This even applies to radiation linked with a moving electron. Have you ever heard of a delayed wave? Isn't it incredible how a wave starts from the source and then travels forward in time, eventually being absorbed in the distant future? The other one shows us the advance wave that starts from the absorbers in the outside environment and comes towards us from the future, as if it's coming from a source of radiation. In this case, the source of radiation is an electron that is moving, which is really fascinating. It's a real shame that most physicists don't pay attention to this innovative idea. But guess what? Einstein did it in the year 1909. In the first scenario, the electric field is estimated by a mixture of emission processes, which are the second most complex of the absorption processes. They're fascinating, aren't they? The great thing is, you can use either of the two equations, and you can even mentally eliminate the absorbing body if you want to. This brings us to an amazing discovery. A lagging solution is just as unique as a combination of lagging and advancing waves. The great news is that at any distance, you can simply remove a body that is capable of absorbing radiation from your calculations. No problem at all. And this is true not only for electrons interacting with their neighbors, but also for other phenomena, such as television signals traveling from the Earth to other parts of the universe. Isn't it incredible that these equations always include solutions that describe advanced waves from the furthest reaches of the universe, converging towards the antennas from which these signals were delivered? This is such an amazing discovery. It could reveal a new form of non-locality, either different from what we've observed in the past or the same. Either way, it's a fascinating development. Einstein never thought about this back in 1909, but now we can. In 1940, Richard Feynman, a Princeton graduate student, was one of the few who saw the potential in this revolutionary idea. He was a real visionary. He was one of the very few participants, and what a great participant he was. John Wheeler was his brilliant supervisor, and he helped him come up with the incredible concept that the electron, by its interaction with another charged particle, is, in a sense, emitted half wavelength into the future and into the past. And then, at the point where this wave collides with another charged particle, something truly amazing happens. It's so incredible, you'll be amazed. And then, at the point where this wave collides with another charged particle, something truly amazing happens. The latter discharges its own halves into time in a back-and-forth motion. The Feynman interpretation is truly fascinating. It suggests that two half waves, when they interact, cancel each other out in most places, which is pretty cool if you think about it. But here's where it really gets interesting. In the space between the two particles, these two waves join forces to create a full wave, which is really quite something. It's as if they're amplifying each other, creating a whole new phenomenon. During the presentation, Feynman had the incredible honor of having Einstein and Wolfgang Pauli in attendance. Pauli was really keen to share his thoughts on the concept, but he did have some concerns about whether it would be successful. He was curious to know whether Einstein agreed with this assessment. "Oh, no," Einstein responded with a spark of excitement in his voice. "No way! I truly believe that developing a theory that adequately accounts for gravitational interaction would be an absolutely exhilarating challenge. It's so amazing to think that for so long, no one believed that waves would come from the future. Even though he got support, the idea was still unclaimed for a long time." In a striking contrast, John Kramer, a professor at the University of Washington in Seattle, who had been captivated by Feynman's concept since his graduate days, suddenly saw the incredible potential for it to be integrated into quantum mechanics by the latter half of 1970. Kramer's idea is absolutely brilliant. It's so simple, yet so profound. This is something that happens pretty often, and it's always such a great moment when it happens. Kramer has made a huge impact on how we understand what happens to the probability wave in a quantum system when a particle with which it is coupled registers at a particular place. Isn't it incredible that a wave in one place can know when it's time to disappear and then just do it? Kramer used a really creative example to illustrate his point. He said that if you toss a bottle from Florida Beach into the Atlantic Ocean, it'll be like a quantum particle registering at a particular place. Now just imagine this for a second. What if this is a quantum bottle and it vanishes in a wave that travels over the ocean and reaches Europe? In a truly astonishing turn of events, a bottle that washes up on a beach in England coincides with the disappearance of the very waves that have been traveling over the ocean. Kramer made an incredible discovery. There are waves that are both faster and slower, and they make quantum handshakes everywhere they go. In an amazing feat of physics, the waves from the bottle made a one-of-a-kind connection and eliminated all other waves. It's so cool how they did that. These waves started out in England and then went back in time to Florida, which is across the ocean. Kramer saw a striking parallel between this situation and the pilot wave model, in which the waves guide the particles on their journey. And there's another fascinating thing about this model. There's no time-reversed handshake confirmation. And there's more. And it even helps us understand the mystery of the emergency room. Once the two particles have interacted, they remain connected by a handshake, which is a confirmed contact between them and the location where they had their interaction. I'm so excited to share that everything I've talked about here lines up perfectly with Kramer's amazing interpretation of Schrödinger's famous equation. So, to put the absorption theory of quantum mechanics into practice, we just need to find a quantum equation that, similar to Maxwell's equation, might have two different solutions. And we're going to find it. One of them is like a strong current of happy, positive energy that's moving forward into the future at lightning speed. And the other one shows us something really interesting, a surge of negative energy moving backwards into the past. At first glance, Schrödinger's equation might not seem like the ideal fit for this description, but don't worry. This is because the equation only explains the flow in one direction, which we understand to be a movement from the past to the future. And that's an exciting direction to explore further. Nevertheless, every physicist at the institution is absolutely delighted to be told that the version of the equation that is most commonly used is incomplete. Oh, don't worry about that. And there's more. The pioneers in quantum research made an amazing discovery. The Schrödinger equation didn't fully align with the principles of relativity. Don't worry, it's totally irrelevant in most cases. This is why most students of physics and even most scholars who specialize in quantum mechanics use a simple version of the equation and don't worry about anything else. On the other hand, the complete version of the wave equation, which takes into account the effects of relativity, is significantly more comparable to the Maxwell equation for practical purposes, and it's a total game changer. Isn't it fascinating that it has two different sets of solutions? One of these is just like the well-known Schrödinger equation in its simplest form, which is really exciting. The second equation is a really fascinating reflection of the Schrödinger equation. It's so fascinating. It describes this incredible flow of negative energy into the event that occurred in the past. It's so thrilling to see this duality at work in the fascinating world of quantum mechanics, where probabilities are calculated. Isn't it amazing that quantum mechanics lets us describe the characteristics of a quantum system using a mathematical expression called a state vector? Schrödinger's wave equation is then used to describe the attributes of the system it describes, and it does so in a truly remarkable way. Isn't that fascinating? In general, it is a complex number, which is defined as a number that contains a square root of -1. Isn't that pretty amazing? And there's more. If you take any two ordinary numbers, a and b, and add them together, you get a complex number. Now get ready for something really interesting. I know this might be a bit tricky, but I'm here to help. To calculate the probability of detecting an electron at a particular instant in time, we must compute the square of the state vector that corresponds to that electron state. And now for the really cool part. It's time to compute the probability. Now for the really fun part. Now, here's where it gets really interesting. To calculate the square of a complex variable, we get to do something a little different than just multiplying the variable by itself. Now for the really cool part. You get to generate a second variable, which is a mirror reflection of the first variable and is referred to as a complex conjugate value. And the best part is, you can do this easily by just changing the sign in front of the imaginary part. It's a case of both advantage and disadvantage working in different ways. And now for the really cool part. Guess what? The complex conjugate variables that are a negative and multiplied by b and a plus and multiplied by b are both variables. Now for the really fun part. It's time to multiply these two complicated numbers together and calculate the probability. Have you ever wondered what it would be like to change the sign of the imaginary component and obtain a complex adjoint number? It's like shifting in the direction of time, but in the opposite direction. This is exactly what happens in equations that describe how the system changes over different periods of time. The basic probability equation, which was introduced by the brilliant Max Born in 1926, is truly a remarkable piece of mathematics. It's so interesting how it makes a clear reference to the nature of time and even allows for two different forms of Schrödinger equations. In the first, we get to see the leading waves in all their glory, which is really quite something, and in the second, we get to see the lagging waves in all their majesty. Isn't it amazing that this incredible fact has led to such a wonderful result? I'm so happy to tell you all that everything you know and love about mathematics up to the Schrödinger equation is exactly the same as in the Copenhagen interpretation. This is great news. It means that Cramer's interpretation of quantum mechanics is totally doable from a mathematical standpoint. This is because the Copenhagen interpretation is the most popular and widely accepted one. It's really quite simple. It all depends on how you look at it. In his explanation of a typical quantum transaction, Cramer depicts it as an incredible handshake between a particle and another particle that is located at a different place in space and time. It's a fascinating way to think about it. Isn't it fascinating to think that one electron can emit electromagnetic radiation and that another electron can absorb that energy? It's the perfect starting point for this incredible concept. And there's more. And guess what? This also applies to the vector of a quantum item state. It starts out in one state and then ends up in another, all because of some interaction. Let me give you a great example of this. Imagine a particle is released by a source on one side of a two-hole experiment and absorbed by a detector on the other side. This is a perfect example of a vector. One of the most fascinating challenges that arises when attempting to present such a description using conventional language is how we should interpret exchanges that take place simultaneously in both directions over time. This can be tricky because, as we all know, time moves at a different pace in different places. In our everyday lives, we tend to think of time in terms of hours, but in this case, we're talking about something that happens instantaneously in terms of the hours that are typical in our world. Cramer does this in a really clever way by avoiding talking about time and using some pretty cool semantic techniques. He describes things in terms of a pseudo-term, which is pretty mind-blowing if you think about it. It's a simple yet effective solution that helps most people understand the concept more clearly, which is great. And it works like this. In an amazing attempt, a quantum radiator object tries to interact with the outside world by producing a field that is a perfectly balanced mix of a trailing wave into the future and an advance wave into the past. Isn't that fascinating? This incredible field is created when the object connects with the outside world. If we focus on the latent wave and ignore the advance wave, we can gain a deeper insight into the situation, which is really helpful. And then something truly amazing happens. The object travels into the future until it comes into contact with another thing that is absorbing and with which it can interact. In an amazing turn of events, the second object generates a fresh lag field during the interaction, which precisely compensates for the lagging field that was generated by the first object. Isn't that incredible? And in the future, we'll have no lag field at all. But wait, there's more. The absorber also produces a negative forward wave that travels backwards in time to the radiator, following the path of the delayed wave that was initially generated. Isn't that fascinating? And now, something truly amazing is about to happen. And now for the really cool part. The advance wave is absorbed by the emitter, which causes the first object to react and emit a second wave that travels backwards to the past. This new advance wave is pretty amazing too. It can completely compensate for the advance wave that came before it. This is why, before we even start, we unfortunately can't deliver radiation back to back. Isn't it incredible? In this amazing process, there is only a double wave that connects the emitter and the absorber. This double wave is made up of two parts. One half is a latent wave that carries positive energy into the future. The other half is an advance wave that carries negative energy into the past during negative time. Isn't that fascinating? And now for something really special. this advance wave is added to the first delayed wave, as if it were a delayed wave from the emitter to the sink. And that's why it works. A minus minus gives a plus, so I really think you'll love this method. Isn't it incredible? When you combine negative energy with negative time, something truly amazing happens. It produces positive energy that moves ahead in time. I think Kramer makes a great point. I think it's totally reasonable to assume that the emitter is the one who produces the request wave, which then travels to the absorber. And then, the absolute best part. And then, the best part. The absorber sends a confirmation wave back to the emitter, and the transaction is finished by a handshake that takes place through space-time. But when it comes to pseudo-timing, it's just a series of events. In reality, it's an endless, incredible process. Isn't it incredible that all of these events occur at the same time? In a truly fascinating turn of events, Kramer makes the intriguing claim that it's not the link itself that brings the chain to a close. This link at the beginning of the chain is where the magic happens. The radiator is really clever because it receives lots of confirming waves in answer to its request wave. It then amplifies one of them at random, using the principles of probability. This is the link that gives the chain a little extra oomph and brings it to a happy conclusion. And there's more. This wonderful wave of affirmation is materialized in the shape of a successful transaction. Isn't it amazing that a timeless transaction has no such thing as when? This is a great question. This really gets to the heart of the matter, doesn't it? I find the transactional interpretation absolutely fascinating. This is really fascinating. It suggests that the delayed request wave propagates via both apertures in the installation, initiating an advance confirmation wave from the detector screen. And then, this wave flows all the way back to the source through both holes in the installation. As the truly amazing process of constructing an interference pattern unfolds, each particle makes a random selection regarding which of the suggestions to accept. But what if one of the holes closes after the particle has already left? In that case, the particle already knows what it's doing. This is such a clever variation of the delayed selection experiment. The confirming wave has just one last opening through which it can turn around and come back for a little handshake. When Kramer writes, "This is where things get really interesting," it's totally okay not to worry about when observers choose which version of the experiment to administer. The observer defined the configuration of the experimental setup and the boundary conditions, and the transaction was generated in accordance with those parameters. It was such a fascinating process to observe. And there's another thing. It doesn't matter that a registration event involves measurements, unlike any other contact. This is really great news because it means that the observer doesn't have a specific role in the process. It's so exciting to see how far we have come in understanding the mysteries of quantum physics. It's all thanks to embracing a single concept that challenges the status quo and defies common sense. In this fascinating theory, a portion of the quantum wave has the incredible potential to travel back in time. I think this is a truly revolutionary idea. It challenges our natural inclination, which is that events that produce something always come before the cause itself. But wait a second. When we take a closer look, it becomes clear that time travel, which is a really important part of transactional interpretation, doesn't challenge our basic understanding of causality. Isn't it amazing that timeless handshaking doesn't affect the logic of causality in our world? Even though a quantum wave travels backwards in time, it still works within the framework of cause and effect that we're used to, which is pretty cool. It's totally understandable that our understanding of time and transactional interpretation differs from what we think we know. This is mainly because transactional interpretation incorporates the fascinating consequences of relativity theory, which is really quite amazing. Have you ever tried to explain the fascinating results of quantum experiments that test Bell's inequality from the perspective of the Copenhagen interpretation? If so, you'll know that it can lead to some intriguing contradictions. This is why the Copenhagen interpretation takes a classical Newtonian approach to time. It's fascinating to see these contradictions occur. The best way to solve this would be to increase the speed of light to an infinite value. In that case, it would be like there was no distinction between the local and non-local descriptions of processes that involve Bell's inequality. Schrödinger's ordinary equation would accurately represent the events that were taking place, which is pretty amazing. This is why the ordinary Schrödinger equation is, in essence, a valid relativistic equation. All we need is for the speed of light to be everlasting. Take a moment to think about this. Have you ever wondered what impact a brief handshake has on the exercise of free will? At first glance, it seems like everything revolves around this fascinating connection between the past and the future, which is pretty amazing if you think about it. But wait, there's more. It's truly amazing. Each photon is aware of the exact time and location at which it will be absorbed. In a two-hole experiment, every quantum probability wave that travels through the cracks at the speed of light is already aware of the type of detector that is waiting for it on the opposite side of the experiment. Isn't that fascinating? Isn't that just so amazing? Isn't it fascinating to think about a universe that has been frozen in time and space? It really challenges our understanding of these concepts, and there's more. It's so incredible to think that everything that has ever existed or will ever exist is right there. On the other hand, we have the incredible opportunity in our time period to make judgments based on actual free will without any awareness of the outcome of those actions' consequences. Isn't that amazing? Isn't it amazing how we make judgments, whether they're human or quantum? Take the fascinating decay of the atom, for example. It's the fundamental component of the timeless reality of the tiny world. It takes time in the microscopic world to make judgments like this. Kramer is absolutely delighted to say that his interpretation is in line with the predictions made by conventional quantum mechanics. And there's more. It has the potential to help us gain a deeper understanding of the quantum world. I'm so excited to tell you all about this amazing new tool. It's going to be a total game changer. It's going to help us understand those strange quantum processes in a way that no other tool has been able to do before, which is really exciting. And it's going to help us create intuitive representations that we've never been able to do before, which is really exciting. But there's no need to dwell on the fact that the transactional interpretation isn't as strong as the others in this regard. All of the interpretations offer something truly special, a conceptual model that helps us understand quantum phenomena in a whole new way. And the best part is that they all make the same predictions, which is pretty cool. This is the main point, and it's a big one. I'm happy to say that each and every constellation is beneficial. They're all fantastic, but there's still room for improvement. I'm so happy to tell you all the great news. This is great news. It means you can choose the option that feels right for you and ignore the rest. It's so inspiring to think of all the brilliant minds that have dedicated themselves to understanding the fascinating world of quantum mechanics over the past 90 years. I'm so happy to tell you all about these 6 different types of comforts. They are some of the best concepts that people could think of throughout that period of time. And the best part is that they can all be summarized in a very concise manner. All right, let's dive right in. It's so important to look at the world around us. If we don't, we're really missing out. Let's jump right in and see what we can discover together. In an amazing twist, it's an invisible wave that controls the movement of particles, and yet the particles themselves have no effect on the wave. And now, a third. In one of the many parallel realities, absolutely everything that could possibly take place actually does take place, and it's absolutely amazing. And now for something really exciting. The fourth one. In this truly incredible theory, it turns out that everything that could possibly happen has already happened, and we've only seen a tiny fraction of it. And now for something really interesting. Guess what? It's the fifth one. It's as if space doesn't exist. Isn't that wild? It's truly amazing how everything affects everything else instantly. And now for something really special. It's the sixth one. It's so interesting to think about how the future has had such a profound effect in the past. In his book, The Nature of Physical Laws, Richard Feynman made an intriguing observation that I found really interesting. I think it's fair to say that nobody fully understands quantum mechanics. Please don't torture yourself by asking, but how can it be that this is the case? If you can, try your best to avoid doing so. So if you don't, you'll end up at a point where there's no way out. I know it can be tough, but I'm here to help. And you know what? Guess what? No one's ever been able to escape from it. Oh my, it's so hard to know what it's going to do next.